Yeah, good morning, ma'am. Good morning, Jayanti, ma'am. Good morning, Anasuya ma'am.
Yeah, very good morning.
Morning, ma'am. Jayanti ma'am from JNV Krishna is already there to present yesterday's report, ma'am.
Okay, you can just start. Go ahead with.
Okay, we are just. To start the recording, ma'am, we have to wait for 1 or 2 minutes, ma'am.
No issue for me.
Okay, ma'am.
You can just go ahead. I'll be a part of it. You can just go ahead as per your schedule and program and design.
Okay, ma'am. Okay.
Thank you. Thank you.
Thank you, ma'am.
Good morning, madam.
Good morning, sir. Good morning, sir.
Madam, good morning. Good morning.
Very good morning. So we are into the third and final day.
Yes, yes. Madam, recording, what's the problem?
No, nothing is, sir. No, it's okay, sir. Shall we start, sir? Because Jayanti ma'am is already there. Actually, students are in lesson number today, sir. Only 16 or 15 are there.
9:30 they will report. You told
Yes.
them?
In that case, we can just wait for a few more minutes.
Okay. So, good morning, everyone. We are on the third day of our RCSC. I welcome Honorable G. Anasuya ma'am, K.V. Subbareddy sir, Assistant Commissioner in charge of the program, and our principal sir. And we have among us Madam Jayanti Tiruvepati Jayanti ma'am, PGT Chemistry from JNV Krishna, to present yesterday's report. Okay. So we shall start now. Ma'am, you can present your report, ma'am. Jayanti ma'am.
Right. Thank you, Manjurani ma'am.
Yes, you are audible, ma'am.
Yeah. Anasuya ma'am, Deputy Commissioner, NVSRO Hyderabad region, and the NVSRO Hyderabad region officials, principals and dear students of various JNVs and the guest speakers, a very good morning to all of you. I am Jayanti, PGT Chemistry, JNV Veleru, Krishna district, presenting the Day 2 report of Regional Children's Science Congress through virtual mode. The proceedings started with the Day 1 report presented by V. Raghavendra Sir, PGT Biology, JNV Vijayanagaram. After the report, G. Anasuya Ma'am, Deputy Commissioner NVSRO Hyderabad, addressed the students. She wished the students all the best and appealed the students to attend all the sessions, to participate actively, to get motivated and to make use of the opportunity. Deputy Commissioner Ma'am's message was followed by the first session. This session was taken by Dr. G. Manoj Kumar, Assistant Professor, Advanced Center of Science in High Energy Materials. His research interests were laser spectroscopy, Raman spectroscopy, chemometrics, combustion modeling. His publications include 19 publications in various journals, and he has made the presentation very interesting. The title itself is interesting, like let's throw some light on the garbage, literally. Dr. Manoj explained his plan of action for this session. His presentation included visit to lab and interaction with a DRDO scientist, Dr. M. Sri Ramana. The presentation started by quoting the famous line, water, water everywhere. It is plastic, plastic everywhere nowadays. The students were asked thought-provoking questions like, can you think of any part of life where you are not using plastic? Can you imagine life without plastics? And then he brought the point that as long as we use plastic, it's okay, but after use, it is causing problem because we don't know how to dispose it. The curiosity of students was aroused by asking few more questions like how is the purity of gold measured, how the presence of suspected explosives was detected, how the farmers decide when the fruit is ready to be harvested, and how the nutritional facts of food items are given on packaged food items. And finally, the question, can light throw light on these questions was asked. How we detected the presence of explosives, the blood sugar levels is measured, how we know that Maggi which we are eating does not contain heavy metals, and most importantly, if an item is new, its constituents are not known. The irony is that when we have instruments to measure the type of material present on moon and the conditions on it, we don't have the instruments to measure the materials in our hand. The students were asked the reason why we use plastic, and the information was given that it is easy to manufacture plastic, very less labor or skilled staff are required for manufacturing plastic material, no finishing or painting or polishing is required, and it is low cost. But it has influenced the life of human beings because it is being used in transportation, automotives, aerospace, and many other fields. The plastic consumption per capita in India is 9.7 kg per person. And these plastics are classified in 7 categories based on the polymers that are present. We create plastic pollution, but we are in the way to make new materials which can substitute plastics. The scientist has used Raman spectroscopy to detect the type of the plastic. The hands-on experience or activity was done so that the children can see the spectrum of these materials. He has taken few plastic bottles and showed us the spectral lines that these plastics were giving. And he also mentioned the point that each plastic has a particular line in the spectrum which is specific to that particular plastic, and it is called as the signature line of that particular plastic. To satisfy the curiosity of students, even sugar sample was tested and it was shown that it has specific spectral lines. So this lab activity was very interesting because children, if they would have gone to the labs, they would have surely tested many items which were plastics and they were using. After this very interactive session, students had another opportunity for another interactive session with Dr. M. Sri Ramana, scientist DRDO Hyderabad. He explained how DRDO is working to make the life of soldiers comfortable for those soldiers who are protecting the country at the borders. The research in DRDO is not only to develop indigenous missiles, but it is also doing research on psychological issues faced by the soldiers. Dr. Sri Ramana also explained the various employment opportunities and what is the educational qualification required for various posts in DRDO. He also clarified that not only MPC students but also BPC students have opportunities in DRDO as research is done in life sciences. The session ended with most of the students interacting with the scientists and satisfying their curiosities. The second session was by Dr. M. Hanumantarao, project scientist, Advanced Center of Research in High Energy Material at the DRDO Center of Excellency. The topic he has taken was the role and importance of chemistry in modern science and advanced technologies for the better mankind. The topic was introduced by explaining the importance of position of elements in the periodic table. The main focus was on boron chemistry and its uses in advanced technology. There are many basic areas in chemistry like organic chemistry, inorganic chemistry, biochemistry, etc., and also advanced areas like nanotechnology, in which lot of research is going on. In our daily life, thousands of chemicals reactions are taking place in and around us involving various elements. The element boron and its compounds, which is the speaker's research interest, was explained in detail. The position of boron, its isotopes, and why the study of boron is important was reiterated. Isotope boron 10 is more abundant than boron 11, and boron has characteristic green flame which is used in defense. Boron is used in cancer treatment, in CNBT radiation therapy, but it is not available in India and it is very costly. But in foreign countries, this particular boron 10 isotope is used for treating cancer. Use of boron in manufacturing different type of glass, its industrial importance, and use as rocket or aircraft propellants, and then missile applications of boron were also very nicely explained with the PowerPoint presentation, which included many chemical reactions which were mind-boggling for the students, but still the take-home message was that boron is a very important element which is used in defense. Based on the limitations of using boron, high energy material was made by converting it into nanoparticles. The examples of propellants like dodecaborates, which have high efficiency and cause less pollution, were synthesized by the scientists in the DRDO labs. Dr. Hanumantarao also explained the instruments like FTRI, NMR, HRMS, etc., which involved in the characterization of newly synthesized compounds which he has prepared. The session was concluded by summarizing the main points and sharing the video links to the participants. The session 3, a very interesting session because children were ready with all the material that they were required to bring with them to attend the Science Congress. That is the hands-on learning. The hands-on learning, an easy and effective way to learn physics, was given by Dr. G. Manoj Kumar, Assistant Professor, Advanced Center of Research in High Energy Materials. The speaker emphasized on importance of observation for learning students. Students were told to observe the surroundings using the lenses. And the feedback also was great because students observed the nearby material and also told how it was while observing through the lens. The reason why an inverted image is formed was very nicely explained by showing laser lights and convex lens. The ball magnet and the copper tube experiment was really very interesting. It explained why the movement of the ball was slow and why it was falling down after some time, though the gravity is there. The magnetic effect was explained very nicely. PVC pipe and the woolen cloth experiment to show the effect of charges was demonstrated very nicely, and children also were doing the experiments hands-on. The students also had the experience of seeing and doing the experiment as the list of the materials to be kept handy was informed. The hands-on learning session was concluded by reiterating that in the learning, students' involvement is very important. The fourth session by Dr. Syed Nizamuddin Qadri. Associate Professor, Department of Mechanical and Aerospace Engineering, Indian Institute of Technology, Hyderabad, was on basic experiments in kinematics. Nobody has imagined that a cell phone with a camera, an iPhone, can be used to measure the distance and the position of the object in kinematics. The speaker introduced the topic by giving examples of some basic measurements that can be done by image processing tools. A smartphone with camera is the simple requirement for kinematic measurements. The motion of an object falling down the vertical line and then thrown horizontally was explained theoretically by plotting graphs. Using graphs, it was analyzed that the speed keeps on increasing the accelerating motion. Dr. Syed Nizamuddin explained how we can see accelerating motion by demonstrating the experiment. A video of the vertical throw of the ball from the height to the ground was taken with a smartphone. The MP4 is converted into JPG using computer software. The images are extracted and opened in a GIMP-free software. GIMP-free software, the image number and the position are fed in an Excel sheet and the graph is plotted. The same procedure was followed for a ball thrown horizontally. It was concluded that the graph of a vertical motion of object curved after certain distance, whereas the object in horizontal motion distance was changed vertically with time. The activity using software was very clearly explained by the scientist, and it was a take-home message that this particular GIMP software is a free software, and students also can use this with by taking the movie of a object which is thrown or which is moving, and we can find out the space and time when the object is at a particular position. This very interesting session was followed by the fifth session, the session which the children were waiting since morning, and so many queries were asked that when the paper presentation will be, and very patiently answered by our Manjurani ma'am. The paper presentation by participating students. This task was taken by Sri Kumar Swami Parthiban, Principal, JNV, Hassan, and his team. At the beginning of this last session, Sir said that 44 entries were submitted, and the members of the scrutiny panel selected 13 papers for presenting. A difficult task it was. The judges for the presentation will include a 3-member panel, and the result will be sent to the organizing principal, JNV RR Rangareddy district. The basic rules to be followed by the presenter were reiterated by Parthiban sir. The time allotted for each participant is 3 to 4 minutes, and the number of slides should be not more than 10. The students involved very enthusiastically, and the presentations included latest methods like bioremediation, bioprinting, about millets, treatment of pollutants, subsurface irrigation, recycling plastic waste, nanotechnology, and the concern of the children for the human life and the environment was clearly seen, how they are working so that a sustainable development can be made for the human beings. All the presentations were very interesting, and very nice participation from the students was seen. The day concluded by announcing the reporting time for the third day proceedings of the Regional Children's Science Congress by host Vidyalaya Principal Ratnakumar sir and the program coordinator Manjurani ma'am. I congratulate the NVS RO team who selected such eminent scientists who knew the pulse of students, because they have presented what is required for the students. I thank the officials of NVS RO Hyderabad region for giving me this opportunity to present the second day's report. Over to you, Manju Rani ma'am.
Thank you so much, ma'am. Thank you so much, Tiruvapati Jayanti ma'am from JNV Krishna, for this extensive report, ma'am. Thank you so much.
Thank you.
Okay, students, we are waiting. Still, we have 10 minutes time for our session to start. Okay, so you can get adjusted. Everybody has filled that feedback form yesterday. You guys filled that feedback form?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Somebody asked me for the recordings of day 1. Okay, so the file size is very big, so it's not possible to send you via WhatsApp or via mail. So it's streaming on YouTube also, and we have shared the YouTube streaming. Was shared किया था ना? Not shared. We will share you the YouTube streaming link. Okay, you can watch the day 1, day 2 on YouTube also, because it's big in data, so it's not possible to share in WhatsApp or in mail. Okay. So today's first session will be about scientific curiosity, a way of life. Okay, the topic will be a scientific curiosity, a way of life by Ranjith Ramadurai sir. He's from IIT Hyderabad. And our second session will start at 11:45. Okay, that will be by Dr. V. Chandrasekshar sir, Center Director of Tata Institute of Fundamental Research, Hyderabad. And the topic will be a journey through light. Sir C.V. Raman, his life and science. And our third session will start at 2:30 p.m. by Dr. Sutapa Ghosh ma'am, Senior Principal Scientist, PFM Division. And the topic will be Nanomaterials and Composites for Energy and Healthcare. And 4:30 p.m. we will be having our valedictory function. Can you confirm, please, Ranjith sir, if you are there?
I'm here.
Okay, sir. Okay, sir. 1 minute, sir. Will make you the presenter. Ranjith sir. Okay, warm welcome Ranjith Ramadurai sir in our first session of a 3-day long RCSE Regional Children's Science Congress. We welcome you, sir. About Dr. Ranjith Ramadurai sir, he comes from Department of Material Science and Metallurgical Engineering, IIT Hyderabad. Sir is working there as a professor, and the departments are Material Science and Metallurgical Engineering and Engineering Science. Sir's research interests are in multifunctional thin films, piezo response force microscopy, hybrid piezoelectrics, piezoelectric sensors and actuators. Warm welcome, sir.
Very good morning, ma'am.
Good morning, sir. So, Are you ready, sir? You can start your presentation, sir.
It's 9:53. Is it okay? Shall I start?
Madam, let us wait until 10 o'clock
Okay, sir. Okay, sir.
because some students are not there, I think.
Okay, sir. We'll wait, sir.
Okay. Thank you.
Okay, still we have time. I would like to put some more light on sir's works and sir's experiences. So our Ranjith sir has been an associate professor in the Department of Material Science and Metallurgical Engineering, Indian Institute of Technology, Hyderabad, and head of Department of Engineering Science Virtual in IITH, and as assistant professor in the Department of Material Science and Metallurgical Engineering, again Indian Institute of Technology, Hyderabad. Sir has been a visiting assistant professor in IIT Hyderabad, and sir has done his postdoctoral research from Alexander von Humboldt Fellow Institute of Electronic Materials and Devices and Leibniz University of Hanover. Sir has been a postdoctoral fellow in laboratory at CRIS MAT in France, a research scholar in Materials Research Center, Indian Institute of Science, Bangalore, and sir has done a Master of Science in Material Science, Professor, Department of Material Science and Metallurgical Engineering, Indian Institute of Technology, Hyderabad. A warm welcome, sir.
Thank you. Thanks a lot for a very detailed welcome note. So
Welcome,
I
sir.
think we have another 3 minutes.
Yes, sir.
So in the meantime, I
Yes.
think I can start sharing my screen and we can start
Sure, sir.
interacting. So very
Yes.
good morning to all the students. So before I start with my presentation.
Good morning, sir.
Yeah. So if you have any questions, please raise your hand in between. And if somebody wants to speak, of course, we are going to have it very interactive. So it is not going to be one way. So I want some of you to speak out. And so whenever I want someone is raising the hand, and if I'm not able to see, I request somebody to unmute and simply talk. Because once I share the screen, I may not be able to see whether somebody is raising a hand or not. Okay, so please feel free to stop me at any point of my presentation. So you can have a very discussive 1.5 hours. Okay, so it is not like I'm not a teacher for you to come and teach some syllabus. Okay, so we are going to discuss about something interesting. Hopefully it will be interesting for you also at the end of the day. So feel free to stop me anywhere, raise your hands and put forth your questions. Okay, so I think I will start sharing my presentation. So I'm assuming you're able to see my screen.
Yes, sir.
Yes.
Yes.
Yeah. Okay. So are you able to see my full screen?
Yes.
Yes, sir.
Okay. Fantastic. So we have 1 more minute to go. So whenever it hits 10, we will start. So are there anybody from 8th class and 9th class also?
Yes, sir.
Okay, fantastic. No worries. I've made sure that I talk about things that make sense to 8th standard to 12th class all the way. Okay. Okay. So I think we can start. So once again, a very warm morning to all of you. So myself, Ranjith Ramadurai, I'm currently a professor at Department of Material Science and Metallurgical Engineering at IIT Hyderabad. So today I was hoping to talk in a very generic way, a scientific curiosity, that a scientific curiosity, it becomes a way of life if once someone is practicing that approach towards life. Okay? So can we request others to mute, please, if they are. Can I request somebody who is talking to mute? Okay, thank you. So let us start. Let me ask a question. Somebody to start with. The science, or for that matter, the evolution of human being, or any development that human being talks about today, is based on one particular thing: the curiosity of the human brain. Okay, so you start questioning things, and then you start developing and a culture of finding an answer to those questions. So fundamentally, the human brain has evolved by questioning itself. And what does it question? It questions its capabilities. It questions its understanding about its own surroundings, and it tries to understand things that it does not try to that is not possible to comprehend to the current understanding levels. So the evolution of not only the human brain, the evolution of any knowledge that we call for today is fundamentally based on question marks. Okay, so that is what I have put here. So questioning is a fundamental character of a human being. What should I question? That becomes a choice of an individual. But today we are going to talk about how to frame questions, or how people have framed questions, and how to connect the answers of different questions. You are trained to think in terms of physics. You are trained to think in terms of mathematics. You are trained to think in terms of biology, etc. And you are also trained to use language as a communication tool, and then you are also trained to make tools that are benefit for human beings. And of course, in the school level, you are introduced to various approaches towards thinking in the name of subjects. So, but the end point, does all these subjects connect at one point? If at all, every approach of question, all the subjects that you study, all the curiosity are based on questions that you ask in and around your surroundings and the society, whatever it is. So everything boils down to science. So ultimately, this domain classification is for convenience. The methods and approach of thinking towards a problem is classified into different categories. So the students are comfortable and trained in a given direction to question and approach a problem. So the fundamentals of human evolution, or in other words, the knowledge base that we have created as human beings, is based on questioning and finding answers to those questions. So today we are going to talk about few relevant questions from your textbook, very much from the NCERT textbook of 8th class and 9th class, and if needed be 11th and 12th class also. Then we'll try to make a connection to all of that. And we will see if the connection is convincing for you. Just because I'm saying it, you don't have to believe it. You can question it for yourself. And you can see if you are also able to appreciate that the connection I'm trying to make between different questions. Okay, fine. So we're going to talk about simple things like a moving object. I'm sure Dr. Syed showed interesting videos to you yesterday about moving objects in a very slow moving frames per second kind of a high speed camera, etc. And we will also talk about something of a reverse effect. Is it possible? And then let's talk about something about playing your strings. And after talking about all these three, yeah. Any questions? Anybody? Yeah. So can you please mute if there are no questions? So can we connect all of them to this thing called an atom? And once we connect it to an atom, can we connect it to the current technology? Is it possible for me to do all these things together like a string, connect between this to this, then make a connection to this, and then go inside an atom, and finally whatever we see today as a technology? So I'm trying to framework a certain set of questions for you, which are kind of going to be, I'm assuming it is going to be interesting. Okay. So now let's talk about very simple things. What should you do if you have to move a ball from one point to another point? Anybody can answer?
So I should apply force on it, sir.
Fantastic. If I don't apply force, will it move at all?
No, sir.
It will not move. Fantastic. Thank you. So what I'm asking is, I need to move this ball from, let's say, from here to a different location. Okay. So let's say I want to move this ball from here to here. So so the ball comes here. To bring it here, I need to apply some force. What happens when I apply some force? If let's say this ball is weighing 50 kg. If I press it with one finger, will it move?
No, sir.
No,
No,
of course
sir.
it will not move. So something tells me I have to provide sufficient energy to move this ball from one point to another point. If I have to move a ball from one point to another point, I need to give sufficient energy. Of course, this is a simple, looks like a simple air ball or a plastic ball. So your hand push is sufficient to move this ball. But the underlying thing is you need to apply some force. That's what Newton's law has taught you, that if you don't apply some force, this object which is stationary is not going to move at all. But if I have to make it move, I have to transfer some force. And in other words, I can call it as I have to transfer momentum. If I move it, then I need to apply some force that in terms transfers into momentum. Momentum is nothing but mass into velocity. This is something velocity. Yeah. Sorry? Somebody said something? Yeah. So now the next question comes. That's not the only way. You have seen playing hockey. So you can use a stick and then you can make the ball move from one place to another. Okay. So these are very playful things. Let's say if you have a heavy object, these are all your textbook images which I have taken from 8th class or 9th class. So now if you want to move this object, so now you have to apply some force, and this book is trying to explain friction and competing forces. I'm not going to go into all those details. What is common in all these things? If I have to move a ball from one point to another, you either by hand push or you have a hockey stick and then you have to move the ball from one point to another, or you have a huge object, then both of you are trying to push, two or more people are trying to push from one point to another point, let's say from here to here. What is common in all those things is you are transferring some energy from your body to in the form of force. You are applying a force on this body, and then you are making this body move. So in effect, you can assume that you are transferring some momentum to this body. All of you agree with me on this?
Yes, sir.
So I am
Yes, sir.
transferring some momentum to this body that is stationary. Now let me ask you another question. Yeah. So now here is a tennis ball, and I give you a torchlight. If you shine a torchlight, will this tennis ball move?
No, sir.
No,
No,
sir.
No.
No, sir.
Fantastic. Can somebody tell me why is it not moving?
sir, because no
Sir,
force is applied.
because proper
Because of
amount
no
of force is
external
not
force.
applied on it to move,
Sir,
sir.
no force is applied on the balls.
So no force is applied on the ball.
Sir, the energy supplied
Yes, yes,
Sir,
yes.
from the
working
torchlight
from
will
the
be
water.
converted into heat energy, sir.
Okay, so the light energy is converted into heat energy. So does the ball gets heated up? Will the ball gets heated up because of the shining the torchlight?
No, sir.
No, sir.
No, sir.
Maybe if you shine it for 10 days or 20 days, isn't it? Or,
No, sir.
okay, no, not at all. It will never get heated up at all. Okay. So now if I'm saying that, sorry, I think there is something problem in my PowerPoint. So let me stop this recording. Just a moment, bear with me. I have to add this here. Not working. I think this is recording 8%. Yeah, I hope now it's working. Yeah. So now this is what I'm talking about. So if I have to move this ball from this point to this point, probably you all agree, if I shine a light, it is not possible for me to move. You can say, somebody said it can get heated up. Okay, so heating is a possibility, but it's a very minimum possibility. Probably you have to shine the light for, let's say, 100 days or 200 days to even increase the temperature of this ball by very small degrees, fraction of degrees, if you are using a normal regular torchlight that you are using in your daily life. So, but all of you agree with one thing, that if I shine light on this ball is not going to move at all its position. I think that all of you are agreeing, isn't it?
Yes.
But why
Yes,
is
sir.
it
Yes,
not
sir.
moving? All of you fantastically answered that. Most of you said, we know that if an object has to move, there has to be a momentum transfer. This is again an image from, I think, the 8th class textbook. What it
Ninth class,
says,
sir.
okay, 9th class,
Ninth class textbook, sir.
sorry for that. So I just picked from whatever textbook it's available for me. So if one object, let's say this example is in your textbook. If this object is moving and there is another object that is moving with a different velocity, if it travels faster and it collides, then there is some competing force acting between two objects. And since this is traveling at faster, and then probably the force transfer from A to B is larger, so eventually what happens, they both start traveling in the same direction with a new velocity. So this is something your textbook exam. Your textbook in your conventional mechanics says, if an object has to be moved,
Excuse me, sir.
yeah.
So, is this applicable even for inelastic collision?
Inelastic collisions also there is momentum transfer, except that the conservation of momentum is happening in a different direction. Like, let's say you have a very beautiful question. Let me give an example when this becomes inelastic. Okay, because if this body is moving, we are only assuming in this diagram the momentum is transferred and then they are traveling. But think of it, if one was a fireball, and the other was not a fireball. So let's say, or in other words, fire is something complicated. Somebody mute. Okay, fine. So okay, thank you. So if instead of fireball, let's say there is a lot of friction when these balls are colliding with each other. There is a lot of friction. What will happen? Anybody? Heat will provide. Yes. Where is that heat coming from? So that is where the inelasticity comes into picture. So right now we will talk about inelasticity. It's a very beautiful question as whoever asked it. So right now let us stick to elastic collisions. So what is important for an object to move from one point to another is momentum transfer. Now, like you said, when I shine a torchlight, my torchlight was not able to transfer any momentum to this tennis ball, and my ball was not able to move at all because I am shining that light. Now let's put a new experiment and see if we can try to do something different. Now, what if the tennis ball was moving? What is the meaning if the tennis ball had moved because of this torchlight?
Transfer of momentum takes place.
Fantastic. So a momentum has got transferred. Now, can somebody tell me why do you think this transfer is not possible earlier or even now? Why this momentum transfer is not possible?
Sufficient force is not.
Fantastic. Sufficient force is not there. But is there anything else? Why people think that this cannot be a reality?
We thought that external force is required for that, sir.
Yes. So now if I hit the same ball with another ball, it is possible to move it.
Yes, sir.
But now why this was assumed that it is an impossible event is what we are shining here. Can somebody mute? What we are shining here is light, and light was considered to be simply a radiation or a wave. So light does not have any mass. If I have to transfer momentum from m1 v1 to m2 v2, if this mass is 0, then I cannot transfer the momentum at all. So people originally thought light has no mass. Later, I know some of your plus 1 plus 2 students are studying about photons and particle natures. We will come to that. But right now, I'm taking you back in history. I'm just trying to frame the questions in sequence of history. So now light was assumed. It does not. Can somebody mute? There is a lot of noise. Can all of mute? Yeah.
Sir, you are.
Sir, we can't hear
Your
you.
sound is not audible.
Sir, we can't hear your voice, sir. You are in mute, sir.
Sir, you are in mute.
Participant, wait. Ranjith sir, your voice is not audible.
Now is it okay?
Yeah, it's fine. It's fine, sir.
Okay. So when did you lose me? My screen is visible.
1 minute.
My
1
screen
minute.
is visible.
Yeah.
Visible at all? Is my screen visible?
Yes, sir.
Okay. So now, since we all know light has zero rest mass, so we assumed that light is not capable of transferring momentum to this ball. So that is our assumption. Because light is a wave and then it is not capable of transferring momentum to an object, so it cannot push an object at all. But if it happens, wouldn't be a very interesting phenomenon of its own, isn't it? If you think that, think of it, if somebody shines a light on you and then you are being pushed back 3-4 steps backwards, that would be like, of course it will be a bit of dangerous light also, we don't want that to happen, but such a kind of excitement was seen when this effect was observed. When you shine light on a metal surface, this light was capable of knocking off something from inside the metal. So if you continuously shine light, you are able to knock off certain objects. This is an object, this is an electron which is having a rest mass, and the light was able to knock off these electrons. So this is one of the experiments that was a very remarkable experiment which also fetched the Nobel Prize for Albert Einstein, where light was evidently proven a fundamental property of something that you see around. You know what? People were struggling to understand what is this light. Is it a wave or is it a matter? Everybody were convinced that it is a wave and it is a radiation in the form of waves. But then this effect of photoelectricity came as a surprise, saying that this light is capable of transferring momentum to mass object. Of course, the object mass is very less. So because the momentum transfer is also less, so it is able to knock off electrons out of a metal. And this effect we all know it is called as a photoelectric effect. So this experiment became an unambiguous evidence. This is an evidence for confirming that yes, light has some kind of a particle behavior. That means light is capable of transferring momentum to real life objects which has some mass. Originally we thought rest mass is 0, but light is able to do it. So then we came up with an idea that light travels like a wave packet of energy, and that wave packet was called as a tiny light particle, which was also named as photons. Okay, so this is one question. Yes, we have seen that light is able to transfer this energy into some metal, and then the electron is able to move out. This is one observation. This observation has proven that light does have some kind of a momentum transfer capability to objects. Now, what if I have to pick a ball from the ground? You are picking a tennis ball from the ground and you are grabbing a tennis ball from somebody else's hand who is pulling it. Will it be the same? Will you apply the same force?
No, sir.
No, sir. No,
Okay.
sir.
In which case the force will be larger? In this case, yes.
Second case.
So you have to pull the ball out of somebody's hands who are holding it tight. But here the ball is simply lying on the floor, except for gravitation, there is no other force. So it is easy for you to apply minimum force and just pick it up in your hands. So now I will ask another question. Now I take a torchlight and then I shine it on my metal. Any light, can it knock off an electron out of it?
No, sir.
No. Because, why? Because
Because it
electron,
reached threshold, something threshold.
yeah, my electron is bound inside this metal. This metal is tightly holding that electron for itself. Why? Because this is a negative charge, and this metal also has lot of nucleus which are all positive charge. So they will kind of attract this charge and hold it together. Until you shine a light that is sufficient to break that holding, until you apply sufficient energy to break that holding, you will not be able to pluck it out. So this is where the understanding of that particular photoelectric effect enhances. Why? If I apply some energy, that should be equal to the energy required to break the electron from this metal, plus this electron is getting some momentum, so it is traveling with the momentum in this particular m1 v1 kind of a direction initially, which was inside. So that kinetic energy. Only if you supply energy that is sufficient enough to break this attraction and make this electron travel, you will be able to see the effect called photoelectric effect. Now, you all know when I shine light, the energy of the light is decided by the wavelength of the light. Energy of any wave, for that matter, is inversely proportional to the wavelength. I will come to wavelength kind of definitions later. So right now, if there is a lower class who have not encountered this formula, don't worry. Just believe me that energy of a wave is inversely proportional to lambda. That means if you have larger wavelength, the energy will be lower. If your wavelength is big, energy is low. So I have given some colors here. Red color means larger wavelength, 700 nanometers. Green color means smaller than red color, 550 nanometers. Then blue color means much smaller than the green color. So what this tells me, if you assume that I am using a metal, let's say for example potassium, it is strongly binding its electron. So if I shine a red light, I will not be able to knock off this electron at all. But if I shine a green light, I will be able to knock off an electron with some velocity. But if I shine a blue light, I will be able to not only able to knock off the electron, I can knock off the electron with relatively larger velocity compared to the green light. So what these experiments tell me is light is able to transfer momentum. Okay, but is it possible that it can transfer momentum to any object and you can see the effect of it? No.
No, sir.
Especially if you want to see it inside a metal, you have
Hello,
to.
sir.
Yeah.
Sir, what happens if we shine light on non-metals, sir?
It's a very good question. Non-metals have a much more stronger binding than metals. Okay, so if you want to shine the same light on a non-metal, even this wavelength will not be sufficient to pluck out an electron out of a non-metal. Why? Because it's a beautiful question. Metals have something called as metallic bonding, which is a weaker bond compared to covalent or ionic bonding. So the metallic bond is a relatively weaker bond compared to covalent or ionic bonds. So the energy that you have in these wavelengths, green and blue, is sufficient to knock off electrons from metal. But this energy is not sufficient to knock it off from a covalently bonded system like semiconductors or insulators. Did I answer your question?
Yes, sir. Thank you.
Okay, fine. So the fundamental thing we are trying to have here is light is able to transfer momentum on an object, and the experiment that tells us is called as photoelectric effect. And that is not only that, the experiment is not only telling me that, it is also telling me about the strength of binding that it can have. A material can have what strength of binding that material has over these electrons of its own. That means if I have potassium, then it will have one binding energy. And if I have lithium metal, that will have another binding energy. If I have some other metal like sodium, then it will have another binding energy. So I can also find out what material it is if I know all these numbers. If I know what is the energy that I am applying, and if I know what is the kinetic energy that is coming, then I can simply subtract both of it and find out what is the binding energy. You see, that is the beauty of science. You answer one question and that experiment will help you as a different kind of a tool for yourself. So you can even identify, let's say somebody give you a very shining metal and they say find out whether it is potassium or lithium or sodium. What you can do? You can shine a particular wavelength and you can shine the red wavelength, and if you don't see any current coming out of that metal, then you can say it might be potassium, because red light is not sufficient to knock off the electrons. So a very simple fundamental question about what is light, and an experiment that is trying to explain what is light has now become a very interesting material testing technique. You can also use the technique to test what material you have. That is one aspect of it. Okay, remember this, we'll come back here. Now the next question we are going to ask is, what are the learnings for us now? We have learnt that I can transfer momentum from light to object. Sir, if light is a particle like behavior, you said that it is like a wave packet and it is having photon. Since it is having a particulate kind of behavior, it was capable of transferring momentum to an object. Now, what is the obvious question? Sir, can the tennis ball transfer momentum to the light? Is it possible? If one is a particulate nature, and if it can transfer momentum to another object, is the reverse possible? Isn't it a good question to ask? Yes or no?
Yes, sir.
Yes, sir.
Now what do you think? Is it possible to reverse it?
No, sir.
No?
Yes, sir.
So that is how people can measure and verify such effect is possible or not. Okay. Okay. So now I'm sure this game people might have played. We used to, in our hometown, we used to have long ropes to tie this. No, if you have a cow or a goat that you don't want it to roam around somewhere long distances, what people do, they just tie the long rope so that they just move around and then they don't go away for far distances. But generally, what we do when we go there, after untying that, what we do, we used to play with that rope. This side is anyway fixed, right? So if you move this rope up and down, it will create a very beautiful wave pattern. Agree with me? How many of you have seen that? So that is a best example for something
Yes,
called
sir.
as transverse wave.
Yes, sir.
You take a string or a rope that is, yeah. So you take a string or a rope that is fixed in one side, and then you move this rope up and down, you will be able to create a wave that is called as a transverse wave. So it's a very beautiful transverse wave, what this mean position where there is no displacement of this rope is considered as the mean position. That means the maximum distance it has traveled in the up direction is called as amplitude of that wave. And now the distance between 2 points of equal state of vibration or equal state of movement is, to be technically correct, for convenience
Sir?
the rope that is tied one side. Yeah. Yeah. Yep.
So what's the difference between oscillatory waves and transverse waves?
Hello.
Yes.
No, I think I have a. I'm not sure if I am audible to people. Yeah. Am I audible? Am I audible?
Yes, sir.
Okay.
Yes,
okay.
sir.
Is my screen visible now again? Back again?
Yes, sir.
Yes, sir. It is visible, sir.
Okay. So somebody asked a question. Please go ahead with that. Hello.
Yes, sir. So what's the difference
Sir.
between oscillatory waves and transverse waves?
Oscillatory waves and transverse waves. Not very different. They are the same. You can say that it is the same. But sometimes oscillatory is a common word. You can also have oscillatory movements even in the given direction. So it has to do, transverse waves are mainly any vibration or the displacement is perpendicular to the direction of propagation. If you have an oscillatory motion in which the direction of propagation of wave is perpendicular to the the disturbance or the vibration that you see is perpendicular to the direction of propagation of the wave, you call it as a transverse wave, which means the object is moving up and down here, it is undergoing an oscillatory motion in this direction, but the wave is propagating in this direction. The wave is propagating in this direction and the object is undergoing an oscillatory motion in the perpendicular direction. Then I call it as a transverse wave. But an oscillatory movement is a common word. Did I answer your question?
Hello, sir.
Yeah, please go ahead.
Yes, sir.
Good afternoon, sir. I am Basaraj from JNV Bijapur, sir.
Yeah, please go ahead.
Yes, sir. My question is, amplitude and wavelength have direct or inverse relationship, sir, with each other?
Amplitude and wavelength do not have any relationship. Amplitude is having a relation with the intensity of the wave. What does it mean? I can have a red light. What is that my answer means? I can have a red light that is of very low intense, and I can have the same red light which is of very high intense. That means in one case I can have a red color laser, in other case I can simply have a red color torch light or red color LED light. If I am assuming if both of them may have the same wavelength, it is possible to have it. If both of them have the same lambda, then in one case it will be low intense, in other case it will be high intense. but the wavelength is the same, but the amplitudes are different. The high intense laser will have a larger amplitudes compared to the low intense light, but the wavelength is the same. So intensity is proportional to amplitude. In fact, it is proportional to amplitude square, but the wavelength is only corresponding to energies. Or in other words, this is a very bright light and this is a dull light. See, you can have two different light sources, right? You can have a flash lamp if you want to play a night cricket in a stadium, then you really need a high intense light. But you just want to read a book, then you don't need a flashlight. A small LED light is sufficient. It is possible to make both the lamps with the same wavelengths. You understand the difference? Hello, am I audible? Hello.
Yes, sir.
Yeah.
Yes,
okay.
sir. Yes, sir. You're audible, sir.
Okay, so I think the student, I hope he got his answer. Okay, so now let's play with these strings. Now I'll ask you
Yes,
one
sir.
question. I will ask you one question. In the previous slide, I fixed that side, right? One side was fixed and then the other side I was holding that, okay? I was holding it. So this side is fixed, which means the atoms or molecules or the rope at this point can never experience oscillatory movement because it is fixed, it is clamped there. But instead, if I give a very free end, if one side was free, what will happen? If that side was free, it will be capable
It
of
too experiences.
yes.
Will also
So,
experience oscillatory movements, sir.
Fantastic, fantastic. So if one side is clamped, that side the rope is not able to experience the oscillatory movement at all. But if it is free end, then the whole rope is permitted to have oscillatory movement. Every atom or molecule inside this rope is able to experience this kind of an oscillatory movement of the rope. But if it is clamped on one side, then it is not possible for me to have it's not possible for the rope to have an oscillatory movement at the clamped location. I think all of you understand this, right? I'm sure you have come across this kind of in your waves and vibrations chapters. Okay, so now why am I talking about this? Let us put some constraints on the string. Okay, what does that mean, constraint? So what I have is I am holding this rope and then I am moving it up and down. This is one constraint. I am fixing this point. If I fix this point, I am not letting the rope to experience oscillatory movement at this point. This I call it as constraint. I am constraining the movement of the rope at this point. Okay, is that the only way to do constraint? There are other ways to do it. You see here, you can have a parallel slit, and if you are moving it up and down, you can create the wave traveling until this point. There is a constraint here, but still the wave is able to travel in between. But if you try to move it in the lateral direction, even this becomes a constraint. So after that, the wave is not able to travel at all. So what is possible is I can take a rope and then I can allow it to move in the up and down directions. And if I have a free end, if I don't clamp this end, it can have all, the rope can have all oscillatory movements at every point. At every point, the rope can experience oscillatory movements. But on the other hand, if I take the rope and then I clamp it here, it can have an oscillatory movement. But here it is always clamped. It is always clamped. So it is not possible for it to have an oscillatory movement at this location at all. So now what does it mean? Which means I can play with the wavelength. This is precisely what you do when you are playing a guitar. You are just moving this constraint with your finger. You are making the string to oscillate and then you are moving your finger here and there and then you are trying to constrain the wave or the wavelength that is produced by the string. In this case, the string is vibrating and then it is able to produce a beautiful note of a particular frequency. So by playing with the constraints, you are able to play with the frequency of the sound that is coming out. Why? Because you are able to control the wavelength which the string is oscillating by moving your fingers here and there. This is what happens. Yeah.
Only guitars or all string instruments?
All string instruments. All string instruments. Yeah. Thank you. So now, why do I talk about this? Let's say I take a string and I clamp in both the sides. Okay. Then I give a small upward downward motion. See, the string is always clamped here. So it can only go up and down in the middle region. So this is called as the basic or the fundamental vibration possible for this string. But now, if I increase the frequency, if it is increasing in the frequency, which means the wavelength is reducing, okay, you know the velocity is nu lambda, and nu is the frequency and lambda. Frequency and lambda has an inverse relation. Okay, the frequency is large, the wavelength is very small. The velocity of the wave is constant. Okay, so now for a given velocity, you can have, if the wavelength is reducing, then the frequency is increasing. You can insert correspondingly, imagine like that. I already said if the lambda is decreasing, what is happening to the energy? In a wave, if lambda is decreasing, what happens to energy?
Increases.
Increases.
Fantastic, fantastic. So if the lambda is decreasing, then the energy is increasing. So if I take a string, the lowest energy possible is this. That means the length of that string and the wavelength, the L is going to be lambda by 2. Why? If I complete this wave, this is going to go like this. It is going to go up to this point. So the whole length of the string is equal to lambda by 2. But what is it here? It is perfectly lambda, isn't it? So here it is 2 times of lambda by 2, that is equal to lambda. So what I am saying? I am saying that the fundamental longest lambda possible is L is equal to lambda by 2 for this string. And now if I increase the frequency, or if I decrease the wavelength, the next possible, why sir this is next possible? I have clamped it here. Because I have clamped it here, it cannot have any other wavelength possible except here it has to be a 0 amplitude. In these 2 points, the string has to always have 0 amplitude. So similarly, the next one is 3 times of lambda by 2. So now, if I had a string without clamping, what is possible, sir? From here to here, anything is possible. I can have a wave that is traveling like this also. If I don't clamp here, unclamped, if I don't clamp here, I can have any wavelength possible. I can have smaller wavelengths, I can have amplitude that are non-zero here. So I can have that kind of a situation. But the moment I clamp it, what I did, I have put a condition. What condition did I put? You cannot have amplitude here. Your amplitude of your wave has to be always 0 at these points. That is called as a condition to this system. I call it as a boundary condition. That means I am clamping here and I am not letting you to. That means I constrain my system. That means I am putting a condition on what value of lambda you can take. This string, if it oscillates, it can have lambda values of lambda by 2, it can have lambda, or it can have 3 lambda by 2. Except this, it cannot have anything in between. That is called as condition or a constrained system. Or in other words, I am sure +1, +2 students would have heard about this. I can make the value discrete or discontinuous, which means my rope cannot take any wavelength. It has to break and take only wavelengths that are permitted. Who permits that? This condition, the constraint of the clamping will tell me whether I should have an amplitude or not. Now, sir, is it possible only in strings? No, you can take a drum, you can take a tabla, or you can take something that is a drum or a percussion instrument like this, bongos or whatever you want to take. You can always have a fundamental mode of oscillations that is possible in a disc or in a string. Okay, so this is the fundamental mode. L is equal to lambda by 2, then L is equal to lambda. So then you can have L is equal to 3 lambda by 2. So you can have all of them. So this is how a constraint is putting a condition on what lambda is permitted and what lambda is non-permitted. That is how a condition is put. Okay. So now you can ask a question, sir, how do I find this experiment, whether where it is getting a node and where it is getting an antinode? Okay. So people have done beautiful experiments. They take a drum and then they put sand, fine sand on top of it. Okay. So and then you start oscillating the drum. What you will see is a beautiful pattern of vibration. That sand is getting collected at locations wherever you have nodes, and it is getting disturbed wherever you have antinodes, kind of a situation. And these figures were created by a scientist called Chaldini in, let's say, 1775 on a vibrating or oscillating drum. These are called Chaldini figures. And this will tell me what vibrations are possible and what vibrations are not possible based on the conditions I impose. Sir, why do I talk about this? Let's talk about it more. Now, instead of that string, please go ahead.
Sir, in drums, we are unable to clamp, right?
No, we are clamping at the edges. No, it's a disc, and the edge you are tying the drum, right? The diaphragm of the drum, see, the diaphragm of the drum is tied on all the locations, right? If this is a drum, so let's say this is a drum or a bongos, it is tied here, no? You are tying the diaphragm here. That is the clamp. So in this location, it cannot have any oscillation amplitude. It can only have oscillation in between these regions. In these edges, it cannot have. So I am clamping it around the edges in a circular disc. Okay. So now, can we replace the string with the electrons? Sir, I have done a string experiment. Can I replace it with the electrons? The electrons also can behave like waves. Some higher students will know that. Electrons has dual nature. Sometimes they will act like waves, sometimes they will act like particles. That means you can see both the behavior in them. Now, if I replace the string with an electron, how do I clamp an electron? By binding it with electrostatic force. I cannot clamp an electron mechanically, but I can clamp it by electrostatic force. How is it possible? That means I can have a nucleus. This is my nucleus, and my electron cannot escape out of this region, which is my atomic radius. My electron is going to be only in this location. It can move around in this location, but it cannot escape out of this. So I have electrostatically put a clamp for this electron. And if this electron is a string, if that electron becomes a string, what will I have? This is the largest wavelength possible, and this is the second largest wavelength possible, and this will be the third largest wavelength possible. So I can again have this electron as a wave, can have values lambda by 2, lambda, 3 lambda by 2, and this corresponds to energy 1, energy 2, and energy 3. Replacing the string with electrons, and then now I am putting a boundary condition or clamping at electrons by electrostatic potential, or in other words, binding energy. What happens if I keep on increasing this frequency, or if I keep on increasing this wavelength? higher and higher energy, what will happen? What you will get is an atomic structure. You have a nucleus, and then you put a clamp around that nucleus and you allowed that electron to have only lambda by 2. That electron to have only lambda by 2, you ended up with 1s orbital. Now I increase the frequency of that clamping. In the same clamping, I increase the size and then I also increase the frequency of the oscillation. What will I get? Of course, the electron, there can be 2 electrons of the same state. So I will get a completely filled 1s2 orbital. An electron string that is clamped in these regions. I am just simplifying it for you. It is not as simple as what I am saying. Okay. But what is interesting is the fundamental approach is the same. So if I have L equal to lambda by 2, that is the lowest energy possible for this electron string that is clamped in this location. Now if I increase it to lambda, so this is the next energy that it can have, and that energy E2 for lambda. Sir, now I want to increase more energy, sir. So I will have this possible, I will have this possible. Lambda by 2, lambda, 3 lambda by 2, lowest energy, much higher energy. So the orbitals that I see, like a p orbital, is, if I consider my electron as a string, and that is the wave node or the node of vibration allowed for my electron under this clamped condition. Who is clamping? My nucleus is clamping. Electron orbitals are kind of wave patterns permitted for the atom to have based on the clamping conditions. So this is how an atomic structure can be visualized. Now I am re-showing the Chaldani figure. I'm running out of time. This is the image, computed image of hydrogen atom orbitals images. So you have some of the +1, +2 students might have studied about 1s orbital, p orbitals, d orbitals, etc. sp, df, etc. Okay. So what these orbitals mean is my electron, if I assume it as a string, for this clamping condition, that is the wavelength or the energy that is permitted for my electron. That is how I can visualize them. Okay, fine. I think that is a fundamental approach which I have taken. Okay, so what I have done is momentum transfer between the what I have told you is, and charge movement will give rise to electromagnetic radiation. That is what I have told you earlier. Then I also told you that if I clamped that condition, then I will produce energies as discrete numbers. If I produce a clamped condition, I will produce energy as discrete numbers or wavelength as discrete numbers. Both are the same. But if I only produce sufficient energy, I will be able to transfer momentum. These are some of the fundamental things that I have discussed to you so far. Where are all these fundamental concepts, where are they playing a role for me? Where are they affecting my understanding? I am sure all of you might have studied Bohr's atom model. In Bohr's atom model, your first hypothesis says an electron moves around the nucleus in a non-radiating circular orbit. This word non-radiating is a technically very important assumption. Why, sir? My fundamental approach is I have a positive charge, I have a negative charge. If it is undergoing an oscillatory motion, it should emit energy in the form of electromagnetic wave, but it is not happening. That is why hypothesizing his atomic model as non-radiating orbits. Okay, point number 1. Then point number 2, my orbit is quantized. Why is it quantized? Because I have put some clamping. I have put some boundary condition or a clamp condition for my electron. It cannot escape out of my atom by itself. So my orbit is, my wavelength permitted for my electron is discretized or quantized, lambda by 2, lambda 3 lambda by 2, or n times of lambda by 2, where n is a 0, 1, 2, 3 integers. So the second postulate comes because of my boundary condition. I put the boundary condition, then this is the cause and effect. So now energy coming out of it. Energy coming out of it, when will it come? Only if there is a specific amount of threshold energy coming out of it. What does it mean? This nucleus is grabbing the ball. So you have to spend some energy to grab the ball out of this nucleus, like photoelectric effect, threshold in the photoelectric effect. So all these fundamental things are what is reflecting in the basic postulate of Bohr's atom model. This is how one can make a connection between what you study in one chapter, you can make a connection to another chapter. So fundamentally all of them are linked. A fundamental phenomena of momentum transfer is linked with the behavior of system that you are dealing with. And a fundamental phenomena of momentum transfer can be used as a Raman effect to test materials. And the same fundamental concept of boundary conditions can be visualized to even understand atoms and electrons inside atoms.
Sir, can I know what is photon?
A photon is a quantized or a wave packet of electromagnetic waves. So it's like a quantization of an EM wave. So it's like a wave packet. The light travels in the form of a wave packet, and that quantization of wave packet is called as photons. Now, I think I have another, I just take 1 minute or 2 minutes to tell what we do in our lab so that the students will be able to appreciate. So now, what we do is, you see I talked about dipoles with different atoms together, right? I have put 2 different atoms, I will get different dipoles. So now what we do is we find a way to arrange atoms in the way we want it. Okay, so we have certain techniques that we do, and then we create new kind of materials by putting one particular atom in one particular plane, and then putting another type of atoms in another particular plane in a regular and periodic fashion. And then I will be able to create my own material with the required dipole moments. Yeah, because the moment I have 2 dissimilar atoms, I will have dipole moments in it. So how do we do that? That is okay, it's a bit of technology relevant. So you can build materials of your own. Today there are techniques that can facilitate you to build materials of your own. What is that my own? I want to have a specific dipole moment based on different materials. So I have a blue atom here and I have a green yellow atom here. Then I will get a particular dipole moment. And then I want the dipole moment to be repeated continuously. You see, this is a picture that is magnified several lakhs. Okay, this is called an electron microscope. And what you see here as bright spots, can be assumed as column of atoms. What you are seeing is column of atoms arranged. So I can have blue type of atoms. I'm just telling blue because I'm just assuming it as a schematic. I want to relate it to schematic. This region is like yellow type of atoms. This region is like blue type of atoms. So I can arrange atoms in a specific fashion to get the required dipole moments for me. Sir, what do I do with dipole moment? Sir, dipole moment oscillations are attraction of my, this is again a zoomed version of atoms. So you can see column of atoms here more clearly. Okay. Now what do we do here in our lab? We change the dipole moments, and I already told when I have an oscillating dipole, I will get an electromagnetic wave. So if I play with the dipole moment which I have, I can play with the electromagnetic radiation that is coming out, or in other words, I can play with the radiation that is present in the atmosphere, I can absorb it. So I can use that dipole material as antenna or a receiver of electromagnetic wave. So now this is a material which we have prepared where you see lot of dissimilar things arranged like green and yellow atoms are arranged. So what will they do? You see this video. I am sure, I hope the video is visible. This person is bringing a mobile phone very close to this material and you see the light starts blinking here. You see this region, focus on this region. There is a LED that will start blinking the moment the mobile comes closer. You see the mobile comes closer and the LED starts blinking. So we have made a nano material which is all of the order of nanometers. Okay, you see these atoms are arranged in a few nanometers range. That is what you call it as nanotechnology. Okay, so we use nanotechnology to engineer a material and create a dipole moment of our interest. And if I create that, I can use it for microwave communication, radio wave communication, etc. Sir, is that what you do? Is there any other way I can change the dipole moment? I can pressurize my sample. If I have positive charge and negative charge, if I apply some force on it, and then the distance will change. If I change the distance, then also I will change the dipole moment. The fundamental electrostatics is telling me that. So if I pressurize my sample, see I am creating a mechanical vibration on my sample and my sample is creating a signal here because there is a change in dipole moment. This effect is called as piezoelectric effect or piezoelectric effect. I can change the dipole moment of a sample under application of some mechanical vibrations or pressure. And then I can make vibration sensors. I can sense vibrations, or I can even, if somebody is tapping on a table, I can find it out if I put a sensor there. This is also another example of what we do in our laboratory here at IIT Hyderabad. Sir, is that the only thing? No. I said we can play with the dipoles. So I can have a material where I can arrange all these dipoles in a given fashion. If I arrange all these dipoles in a given fashion, I can even use the electrostatic force of these dipoles to kill or drive away contagious microorganisms. Now you know what this symbol means, like coronavirus, right? If I use a polymer material where I can have these dipoles arranged in a specific fashion, I can prepare a mask of that material which can actually kill the virus itself. So we have done some experiments and we have found a new polymer, not new material, but a new phenomena where you can use these dipole arrangements to kill microorganisms like bacteria, virus, fungus, including this coronavirus, etc. So if you have an understanding about atoms, you can play with them. If you understand the fundamentals of atoms, you can arrange atoms in the way you want, and then you can play with their property and use it for any application. Okay, fine. So I would like to summarize the whole talk. The soul of research, whatever I have spoken today, not only research, the soul of the scientific inquiry starts with a questioning things. Okay, why is this happening? And how do I test it? And how do I understand this? So science is a subject of what, how, and why. Okay, unlike history, which is a subject of when and where it happened, when it happened. That's a kind of information. But science is a subject of what is happening and why is it happening and how is it happening. And how can I make it useful for me? That is technology. So the soul of research lies in the question. Okay, so you should start questioning. I'm using a famous example of a scientist and his conversation with his mother. So this person who is an inventor of nuclear magnetic resonance, he is a great scientist called Isaac Rabi. He got his Nobel Prize for it. And his mother, it seems, scientist without knowing that she is making him a scientist. After every day he comes from school, his mother would have asked a question. Instead of asking, what did you learn today? Her mother has asked, did you raise a good question today? What question did you ask today? Which is an unknowingly that mother has made him a scientist. That is what he comments. So his mother unknowingly made him a scientist by asking, what question did I ask today? that has enhanced my intelligence, or that has enhanced my understanding towards the surroundings. Yeah, fine. So another image I want to show, this is Madam Helen Keller, who is blind and deaf by birth. Okay, so she has understood something, and look at the pleasure in her face just because she understood something by touching this Braille book. The Braille is the font that is for the invisible, for the vision impaired people. Okay, and she doesn't have any sense of sight or sound. By touching that Braille book, she understood something, and look at the pleasure in her face on learning something new. So I want you people to have this pleasure and enjoy this pleasure. And this pleasure of learning will take you throughout your life, and it will make you a very passionate student, or for whatever you do in your career. The passion of learning and the passion of pleasure to learning is important. So that's why I say the scientific inquiry becomes a way of life for you if you start understanding things in a questioning pattern. And I would like to acknowledge the team and for giving me this opportunity. I think I slightly took more than allotted time. Sorry for that. I think I will stop here and take some questions. I hope some audience are left. Everybody is tired?
No, sir.
Yeah, students, you can ask your questions if you have any queries or any doubts.
Excuse me, sir.
Yeah.
Sir, how can we arrange the dipoles, sir?
How can we arrange the dipoles? You are asking about that, right? What we do is, I think I have stopped the sharing it. So in this, you are talking about the slide where I said arranging the dipoles, right? Okay. So what we do is vaporize these materials into a vapor form, and then we transfer it inside a vacuum chamber. It is possible to do all those things today with the technology. Okay. So we vaporize this material, and we allow very small amount to travel towards the location where we want. What does it mean? I will have a vacuum chamber. I will have a vacuum chamber where I can transfer this, where I can vaporize these materials. I hope you are able to see my screen continuously. Are you seeing my screen?
Yes, sir.
Okay. I take a material, and then I vaporize this material into a small fraction. By shining, and I do all very reduced pressure inside a vacuum chamber. Then I have something called as a substrate here, and I allow this vapor to condense on this. So I vaporize material A first, and then I vaporize material B next. Then I reverse this continuously. So I will have vapor of material A condensed, then I will have vapor of material B condensed into a solid. Then I will repeat this process as long as I want it. So in that way, I can arrange these atoms in a fashion that they will give me the required dipole moment from these different charges. So that is how I can arrange the dipole moments in the way I want. Did I answer your question? Okay, so I do not know if everybody is from Hyderabad, and if once the situation improves, we are very happy to have a in-person visit of JNV, Jawahar Navodaya, to our campus in our lab, etc. You are always welcome to do that. And me as a teaching learning center coordinator of the institute, I will be very happy to organize an event for in-person visit for the Hyderabad students.
Sir, what is nanotechnology?
Nanotechnology is, see, let's say you take a material, and what you see visibly is, let's say, what you are seeing is in millimeters or centimeters or meters scale, right? You take the same material or a device, and then you try to make them the size as small as possible as nanometers. Then you arrange those devices as much as you want in the form of an array. Then that technology that you use to make a device of the length scale of nanometer, is called as nanotechnology. The nanotechnology means you take a material of different length scales and you reduce the length scale of the device to nanometer range. Nanometer means 10 power minus 9 meters. And 1 millimeter is, you know, that 10 power minus 3 meters. So it's 6 orders of magnitude smaller. You cannot even see it with naked eyes. You need a microscope, powerful microscope like electron microscope to see that.
Sir?
Yeah.
What is the use of nanotechnology, sir?
See, today most of your computer and your mobile phone that you are using is working because of nanotechnology.
Hello, sir.
The core processors that are present in your computers, in your mobile phones, or in any of the gadgets, electronic gadgets that you are using, which can do some kind of calculation or computation, is because of some processor that is present there. And that processor is having a transistor which is of nanometer size. So the mobile phone you are holding and the computers you are having is all applications of nanotechnology.
Sir?
Yeah. Yeah, please go ahead. Somebody had a question. Yeah, somebody had a question.
Sir, can I know what molecules have permanent dipoles, sir?
That's a very beautiful question. Who was that? Okay, so it doesn't matter. So there are certain, they call them as polar molecules. The classic example is water itself. Water can have its dipole moment. Did I answer your question?
Excuse me, sir.
Yeah.
Sir, what is the meaning of quantization?
Okay, quantization. It's a very deeper question. It can be answered in a much deeper way also. You imagine I showed you a string that is clamped, right?
Yes, sir.
And in that string, if I clamp it on both the sides, I said only certain wavelengths are possible and certain wavelengths are not possible, isn't it?
Yes, sir.
And that you can consider it as a phenomena of quantization. My wavelength became discretized based on the condition I gave for that string. That's consider it as quantization in a very simplistic, yeah.
Yes, sir.
Okay, I think I am already hitting 11:46. I do not know if I am taking the time of other speakers, so please.
Thank you so much, sir. Ranjith, sir, can I share your mail ID to the students, sir? If they have any doubt, they can ask you straight away,
Absolutely,
sir. So I
absolutely
will
no
share
problem.
your mail ID to them, sir. And if still they have some doubts, they'll clarify it with you, sir. And thank you so much, sir, for being here. And you have been here for more than your time, sir. Thank you. Because of their doubts and all, it's long. And it's a pleasure, sir.
I'm happy there were a lot of questions in between, and only thing is I have to apologize to the next speaker for taking the time. Thank you.
Thank you so much, sir.
Thank you, sir.
So I'll share you sir's mail ID. Okay, you can ask your doubts directly to sir. In our next session already time is there, and we have among us Professor V. Chandrasekshar, sir. Welcome, sir. Am I audible, sir? Please unmute yourself, sir.
Muting. Yeah. Am I audible?
Yes, sir. Yes, sir. You are audible, sir. So we have among us Professor V. Chandrasekshar, sir, and sir's topic is today Journey Through Light. Sir C.V. Raman, his life in science. Sir is the director of Tata Institute of Fundamental Research, Hyderabad. And Chandrasekshar sir was born in Calcutta in November 1958. Sir obtained his MSc from Osmania University here, Hyderabad only, in India in 1977. And he received his PhD degree in 1982 from the Indian Institute of Science, Bangalore. under the supervision of Professor S.S. Krishnamurthy sir. Chandrasekshar sir worked as a postdoctoral research associate with Professor R.R. Holmes at the University of Massachusetts Amherst, USA during 1983 to 86, and then as a senior research officer in the Indian Petrochemicals Corporation at Vadodara for 1 year. And sir then joined the Department of Chemistry at the Indian Institute of Technology in Kanpur in 1987, where sir has been a full professor since 1995, and sir served as the head of the Department of Chemistry, IIT Kanpur, and then as the Dean of the Faculty Affairs, IIT Kanpur. Sir also worked at the Tata Institute of Fundamental Research, Center for Interdisciplinary Sciences, Hyderabad, as a senior professor dean and as the director, National Institute of Science, Education and Research, NISCR, Bhubaneswar, India. And currently, he, as I told earlier, sir is the center director of the Tata Institute of Fundamental Research, Hyderabad. Most welcome, sir. We are, it's an honor to be with you, sir, and your presence will definitely be beneficial for our students, sir. You can proceed your session, sir. Yeah. Thank you so much, sir.
Thanks a lot. Thank you so much. Is my slides visible?
Yes, sir, it is visible.
Yes, sir. Yes, sir.
Thanks a lot. So thank you, and in fact, I'm hoping that this talk will enable young children who are in their formative years to understand the life and work of a very famous Indian, and in fact, he's the only person so far who has received the Nobel Prize from India in science. There have been other Indians people of Indian origin who have received the Nobel Prize, but these people have either worked outside and they got the Nobel Prize outside, or they have been Indian origin but have been of citizenship of different countries. So let me just talk about C.V. Raman, also because typically every year on the 28th of February, we celebrate 28th of February as a Science Day, because it was on this day that Raman announced his Raman effect to the general public through a press conference. So therefore, this is a talk on his effect as well as on his life. So there is also a history, a bit of a history of it. So therefore, it's a light talk. So there's some pun and also it's a talk about light. Okay. Let me just without let me just take a where is my pointer? Yeah. So the Raman effect was announced to the world through a press conference on 28 February 1928. And what is the Raman effect? I'll tell you in a in a nutshell right at the beginning, and then we will later look at it in some detail. So what Raman discovered was when you have a beam of colored light means all wavelengths. Then this fraction of this light which is scattered is of a different color. So let us say a particular color is put into the liquid. Most of it retains the same color, but some fraction of it, a very small fraction of it, is of a different color. So why is this such a big deal? Well, we'll see that. This is called the Raman effect. And in fact, it is so sensational that he announced it on 28th February 1928, and in 2 years' time, he got the Nobel Prize in 1930. And today in India, all across the people, like for example, various laboratories and universities and colleges, this day is observed as the National Science Day. Okay. Of course, before I kind of start, I have to thank my colleagues, Professor K. Bhattacharya from the Indian Association for Cultivation of Science, and Dr. Alagar, who was my student at the Department of Chemistry when I had originally prepared this talk, and then later, of course, subsequent modifications also. Okay. And I also have to thank this particular book, which was commissioned by the Indian Academy of Sciences and written by Professor G. Venkat Raman. This is a journey into light, life and science of C.V. Raman. It's a wonderful book. I mean, those of you who have interest in reading books should be able to get one book and please read it. It's really a wonderful book, both in terms of the history as well as the actual science. Okay. Now I'll start this talk with the statement that oftentimes we look up science and technology as something different from the people who do them. They are not. Science cannot be done in isolation, and it's a social activity. It is connected with people. Therefore, we cannot disregard its history. And therefore, oftentimes we find that although these are all pigeonholed into different sections, science and scientists in one section, history as one section, the people who do science and their lives and how they have come to do about science is also a very important matter. And therefore, we can't disregard it. So in this talk, therefore, I'll be kind of mixing up the personalities, their lives, and then subsequently how the science was carried out with that. Okay. So let's start by first getting a complete glimpse of what Raman did. So Raman was born in 1888 and he died in 1970. So, you know, he lived a full life, lived for 82 years, and he worked at various places. He worked in Calcutta for about nearly 25 years at the Indian Association for the Cultivation of Science, also the University of Calcutta. And after 1933, he worked in Bangalore, first at the Indian Institute of Science, and later in the Raman Research Institute. And later he worked, during this time, what did he do? He worked in various areas of physics, experimental physics, in acoustics, in optics, scattering of light, crystal physics, color and perception. So a wide range of interesting topics. We will be, concentrating on light, scattering of light primarily, although he worked in various other areas. Okay. And why is that my slides not moving? Okay, so let's just get started with. Are you able to still hear me? Just need a. Hello.
Yes, sir. We can hear you.
Yeah, and you can see my slides also,
Yes,
right?
sir.
Okay, great.
Yes,
So Raman, let's start at the beginning. Then Raman was born on 7th November 1888. And as is the Indian tradition, born in his maternal grandfather's house in a place near Trichy, a difficult pronunciation, Tiruvanai Kaval, in Trichy, Tamil Nadu. And this is his maternal house. So you can see that this house, like a typical sort of a lower middle class type of a family, thatched roof. And this is where Raman was born. Unfortunately, this house has not been preserved. I think now this is, there are other buildings on it or so on. That's a pity. His parents were Chandrasekharan and Parvati Ammal. So these are his parents. Raman's father was Chandrasekhar Iyer and Raman's mother was Parvati Ammal. And they, because of the fact that Raman's father was working in a job that moved him different places, Raman also moved at different places. So Raman, for example, studied in Visakhapatnam in Mrs. Avian College, did his BA in physics in Madras Presidency College. And so typically after the BA, the ambition of all the young people who were doing well during that time was that they wanted to study for the Indian Civil Service. And the examination was in UK. And in order for you to write the examination in UK, you have to, of course, travel by a ship. And the civil surgeon, that is the doctor in a government hospital, has to certify that you are fit to travel. And the civil surgeon of Madras in 1904 examined Raman and said that no, this person is not healthy. He cannot travel on the ship. And of course, later Raman told that I will be ever grateful to this person. Otherwise, I would have ended up as a bureaucrat. So because he did not have this opportunity to go to England for writing the examination for the Indian Civil Service, Raman then pursued his MA. So, at that time, everything was called arts. The classification of science, arts, commerce, which we have done after independence, was not there. Bachelor of Arts Physics, Master of Arts Physics. And this he did it again in Madras Presidency College. And, he had a reasonably good laboratory. I don't know how well you can see this picture, but fairly good laboratory where one could perform experiments that were of that particular type, which were known in science, and do quite well. And this is a group photograph that was taken in the Presidency College of the BA class in 1903. And you can see Raman here, a very young boy here. And all the teachers are, there in the first row. And you can already also see, those of you who have a keen sight, that these are the English teachers. And you can see that, they are far more relaxed. And it's quite clear who are the bosses compared to the Indian teachers. The Indian teachers are more sitting straight, but these people have their legs crossed. And that these are our bosses. So he finished his MA in physics, and in fact, even during his masters, he was doing research, and his first paper was published in an international journal called the Philosophical Magazine. And this was published in 1906. That is, even during, so for example, when he was just 18 years old, he published this paper and he finished his MA. Now the question is, what do you do? After MA at that particular point of time in 1907, there were no opportunities for a person with a background in physics to carry out research or do something connected with physics in India. So he could not go to England because there was no Indian civil services, because the surgeon told that you are not fit enough to go there. So the thing that he could do was the financial civil services, which is not the Indian civil service. It is today, for example, it would be called the Indian Financial Service. And he stood first in the examination in 1907. So he was selected for the Indian Financial Services, and the salary was 400 rupees, which is a very large amount of money. And to get an idea about how much this money would be today, you have to approximately say that during that time, about 10 rupees or 14 rupees would be the cost of 10 grams of gold. So you can calculate and, and say what is the price of, what is the salary he would be getting. So a very huge salary. There was also a marriage allowance of 150 rupees. So, but of course he was not married. But as soon as he came to know that there was a marriage allowance, he promptly married. And his wife's name was Lokasundari. And this was a picture in early days of their marriage. This is Raman, and this is his wife Lokasundari. So he was selected in the Indian Financial Service, was working at different places, and was posted as Assistant Accountant General in Calcutta after some, after his initial period of service. So one would have assumed that, he would have perhaps, done very well in accounts and completed his career and maybe retired as a big person in accounts, but nobody would have remembered him and we would not have talked about him. So he was all set to get lost in obscurity and oblivion. Oblivion in the sense of, he would have been a very important person in finance, but nobody would know about him as we know about him today, not just in India, but across the world. But he did not. Why? Because he went to Calcutta, and also fortuitously, he got a house in a place called Scott's Lane. And the Scott's Lane was adjacent to a place called Bow Bazaar Street. And the Bow Bazaar Street had a place called the Indian Association for the Cultivation of Science. So you have to believe in coincidences, because how much of a coincidence does it mean that you are firstly appointed in an accounts office in Kolkata, but you take up a house which is in Scott's Lane, and then that house is close to a place where there is this very obscure looking place called Indian Association for the Cultivation of Science. And not only that, at that particular point of time, Bengal was the place to be, because Bengal was leading the Indian Renaissance. So India has been, not just political freedom. Even India was suffering from a great deal of inferiority complex, because we were, for nearly 200 or 300 years, we were suffering from this, and Bengal was trying, the people in Bengal, leading people in Bengal were trying to lead the Indian Renaissance. You can easily recognize the people's name, like Raja Ram Mohan Roy in the in the 1800s. Ishwar Chandra Vidyasagar, a very famous educationist, Bankim Chandra Chatterjee, a novelist, J.C. Bose, a scientist, Mahendralal Sarkar, a doctor, and even on the spiritual side, like Dr. Sri Ramakrishna Paramhamsa, Swami Vivekananda. So Calcutta was a place bustling with activity, and Raman found himself in this very important location at an important time. And he happened to be, as I told you, adjacent to this place called Indian Association for the Cultivation of Science. So what is this Indian Association for Cultivation of Science? It was started by this patriot called Mahendralal Sarkar, and he was a medical doctor. Was there a question? Okay, so he was a medical doctor, very deeply nationalistic, and he was very much aware that in Indian educational system, the science was not taught, and he was aware that if India had to make progress, then Indians had to learn science, and so he wanted to create an environment, a place where science could be done, experiments could be done. So he thought in terms of mimicking royal society, where in royal society you could do such kind of experiments. So he thought to create a place like this, a place where you would have lectures, you could have illustrative experiments, and in fact people can come and perform experiments if they wanted to. And it should be managed by Indians and controlled by Indians, and not by by people who ruled us, which is the English people. So he had this vision, and he really struggled hard and created this. And he had some very famous people come and give lectures, like Ashutosh Mukherjee, then J.C. Bose, who is known for his experiments in biology as well as experiments in electrical engineering, and P.C. Ray, who was India's arguably the father of the chemistry in India. And in fact, people were charged money for attending lecture, and 8 annas, 16 annas made up 1 rupee, and they would be charged 8 annas for a lecture. And with the help of Maharaja of Vijayanagaram, a laboratory was created, and this was called as the Vijayanagaram Laboratory. So everything was set. A laboratory was created, looked quite, huge, palatial laboratory. And this was called the Indian Association for the Cultivation of Sciences. Facilities were created, and Sarkar hoped that people would come and do experiments here in science, and science would flourish. Unfortunately for him, this was virtually nobody was there to do research. And this was understandable, because people did not have any, training in physics or for that matter any other area of research. We did not have any training at all in India during that time. So there was nobody to do research, and Sarkar was really disappointed. So he said, firstly, he thought that people in India are not interested in science. So he said, I do not know how to account for this apathy of our people towards the cultivation of science. So he thought that people should embrace science, because science allows you to think rationally. It allows you to question things and find answers to those questions. And in fact, during the time he passed away, he was really quite disappointed. He said, I have wasted a life. Because I struggled so hard in creating this institute, but there is nobody to make use of this particular facility. And this was what he wrote in 1902. And in 1904, he really passed away, and he did not really see this institute that he created being utilized at all. But as I said, this was darkness before light. And because in 1907, Raman meets A.L. Sarkar, and A.L. Sarkar happens to be the nephew of M.L. Sarkar. This is A.L. Sarkar, and Raman meets Sarkar because, as I told you, Raman was living in Scott's Lane, and one day when he was coming back from office, he noticed this plaque on the front of a building which was in Bow Bazaar Street called Indian Association for Cultivation of Sciences. He goes and asks this person, what is this? Then A.L. Sarkar tells him that, this is a place where one can do experiments. There are certain basic facilities if somebody is interested. And Raman is very excited because he had his master's in physics. So he wanted to do something part-time and in this particular place. So he asked whether he can do that. And of course, A.L. Sarkar is only too eager. He says, nobody is using this. Please come and use this facility. And in fact, there is an assistant to him whose name is Ashutosh De. Raman used to call him Ashu Babu, who would assist Raman in his experiments. And this is, a picture, a photograph of Ashu Babu. And but Raman had a regular job, and his job was from 10 a.m. to 5 p.m. That was his regular job in the Accountant General's office. So that was his actual job. And this, what he was doing, he was not getting any money. This was just part-time. And so his weekly schedule was this. This is Monday through Saturday, because at that time we had a 6-day week. So he would get up very early, probably at 4:30 or so, and be ready and go to his laboratory, which he now developed slowly through his own personal money. 5:30 a.m. to 9:45 a.m. he would work there and immediately rush off to his office. 10 a.m. to 5 p.m. in the office which actually paid him the money, which is the Accountant General's office, and come back again, take maybe a very quick break and work till almost 9:30. This was his whole schedule in the from Monday to Saturday, and Sunday, because it was a holiday for him in the accountant's office, he would work the whole day in IACS. So this was alone with just Ashu Babu was working with him and nobody else. But he was so interested, he worked on vibrations. He worked on why Indian music instruments like tabla gave out those notes, and on the violin and various aspects of this, and published around 50 papers. And 15 of them are in the most prestigious journal called Nature, and another 15 in Philosophical Magazine, another prestigious journal. And almost all of them are single authored because he had no co-workers. And so he established a very vigorous experimental laboratory, but he was all alone while working in the Accountant General's office. Okay, so this activity carried on for nearly a decade, for 10 years. You can imagine, a very hectic sort of an activity starting from 5:30 a.m. to 9:30 p.m. Of which which he used to do his regular job and the job that was his hobby, for which he used to spend almost equal time like a regular job. During this time, the Calcutta University had a very visionary vice chancellor, and his name was Ashutosh Mukherjee. So he was a mathematician, and later he was also the judge, and he was appointed as the vice chancellor of Calcutta University. And he wanted to create a science college in Calcutta University because there was no science at that time in Calcutta University. And the way one could do this was to gather money from rich people, create chairs, and invite people to occupy those chairs. These would be eminent people whom you can occupy to have those chairs. That is, for example, a chair in physics or chair in chemistry, etc. So he was keenly interested that science should be done in Indian universities and Indian colleges, and this was his big attempt to do this. So he collected money from rich people, and these people's names are Taraknath Palit and Rash Bihari Ghosh, who had earned a lot of money, and they were willing to donate money. And he created a chair called Palit Chair in Chemistry, which he offered to Acharya Prafulla Chandra Ray, who was, as I told you, the father of chemistry in India. He also was able to hire young people, Sachendranath Bose, Meghnath Saha, and S.K. Mitra as lecturers in physics. But he had his eye on Raman. Although Raman was working in the accountant's office, and probably by this time he was the accountant general, but Raman's research in physics, which was published in 50 papers, was already catching the eye of people. Even non-physicists, non-scientists in India already knew about it. But Ashutosh Mukherjee was not sure. Well, Raman, if I offer him a professorship in physics in Kolkata University under this Palit chair, would he offer it? Would he accept it? The reason was financial, because at this time Raman's salary increased to 1100 rupees. But at university, what the maximum they could offer was 600 rupees. Now 600 rupees was a very good salary, but it was nearly half of the salary that Raman was getting with the government. So later on, Ashutosh Mukherjee actually wrote this. He said, I should fail in my duty if I were to restrain myself in my expression of the genuine admiration I feel for the courage and spirit of self-sacrifice with which Mr. Raman has decided to exchange a lucrative official appointment with the professorship, university professorship, which I regret to say does not carry even liberal emoluments. This one instance encourages me to entertain the hope that there will be no lack of seekers after truth in the temple of knowledge, which it is our ambition to erect. So Raman was offered this position and he accepted it. And because Raman felt the other way, Raman felt that, you know, to be offered a professorship to a government official was a great act of courage. This was a big risk that the university was taking based on his research. And so he immediately accepted it. But the finance department was very unhappy because Raman was one of their best officers. And so they said that, you know, you are unnecessarily jeopardizing your career. Because you have the chance of becoming a member of finance in the Viceroy's Council. That is the biggest position any young Indian could aspire for. This is, you know, the Viceroy's Council today would be like, for example, the Prime Minister's cabinet. You can end up there. But Raman was so much interested in science that he did not, he actually sacrificed financially because he lost half of his salary, but he also sacrificed the prospects that he had if he continued in the same job. There was one final hurdle. The donors of the chair stipulated that anybody who would occupy this professor of physics should have had a European training. You know, because the concept was that unless somebody had training in Europe, you would not be good enough to occupy a professor of physics. So Raman, of course, was completely, I mean, he did not even have a PhD. He had a MA in physics, and later whatever he did was his own work, which was, of course, more than sufficient to get a PhD and a Doctor of Science. But there was, because of the stipulation, there was this discreet suggestion to him that, you know, why don't you go to Europe for a few weeks? We'll pay you. You just go and visit a few labs and you return back. Then we will say that, you know, he has gone to different labs and that we will take care, saying that he has spent time in Europe and that should be good enough. But Raman refused. He said no. He said, in fact, if you want, I will train Europeans in my lab. And I'm so confident that I will not go anywhere to get trained. I'm perfectly well trained. So the university finally had to relent, and Raman was appointed as the Palit Professor of Physics at the University of Calcutta, with the condition that he can continue to do his research at the Indian Association of Cultivation of Sciences. So what were his duties? His duties were, you please devote yourself to original research in your subject. Just keep doing what you're doing to extend the bounds of knowledge. But now you please guide PhD students, stimulate and guide research by students so that you hand over these capabilities to a new generation of people to supervise the laboratory in the College of Science and then carry out your research. So now, of course, Raman was free because he didn't have this job in the Accountant General's office. So it was a full 24/7 work that he could carry out at the Indian Academy of Sciences, at the Indian Association for the Cultivation of Sciences. And this is basically what he could do. So Raman, 1919, A.L. Sarkar, who was, as I said, the nephew of Mahendralal Sarkar, he passed away, and Raman actually became the honorary secretary of this association. And because of his research, which was so well known, he finally got invitations to visit abroad, and he met very eminent people like J.J. Thomson, who was the discoverer of electron, Bragg, who was the discoverer of the use of X-rays for diffraction, Rutherford, the Rutherford model of atom. So he met all these people. And when he was traveling by the ship, which was called SS Narakunda, he was immensely impressed by the deep blue of Mediterranean Sea. So far he was working on sound. So he changes his research area to light, particularly on scattering of light. And because of his trip to UK to visit all these people, and then this was very important because this was what gave him the big the rewards. And in 1924 he was elected as the Fellow of the Royal Society. So during the reception that the city of Calcutta arranged to honor him, the mayor of Calcutta asked him, Professor Raman, now that you're elected as Fellow of Royal Society, what next? Then, of course, he, in a tongue-in-cheek, replied, of course, I should get the Nobel Prize. What else? So he had now a large number of students.
Sir, Chandra was also elected as the Fellow of Royal Society, no, sir?
Pardon me?
Chandra was.
Yeah, I mean we can answer these questions little later if you have these doubts. SN Bose also was elected to the Royal Society, but little later. Jagdish Chandra Bose was elected before Raman. Yeah. So here is a picture of some of his students, and one of the students I'm pointing out is at that particular time Mr. K.S. Krishnan. Later it was to become Sir K.S. Krishnan and Professor K.S. Krishnan, who was a co-discoverer of the Raman effect. So what did Raman work? So Raman worked, as I told you, on light now. He changed his direction from sound to light, and he had several students. Ramanathan, who worked in 1923 on feeble fluorescence, and Krishnan and Venkateshwaran, all of them were working on light. And what they were working on light without knowing was a phenomenon that I will explain to you in the coming slides, which was to do with scattering of light. But they were also working on a phenomenon that is different, that's called fluorescence, where molecules absorb light and then they give back light of a different wavelength. So what they were observing was scattering, and this was so feeble that they had to really kind of, in order to observe that, they had to enclose themselves in a small sort of area where the observer would be in a light tight wooden cage, and this would and then see what's happening, because otherwise the light that is around them would not allow them to observe. So this research, which I'll explain to you, was led to several papers, but the most important one, which was gave him the Nobel Prize, was first submitted to Nature on February 16th, and then first announced to public on February 28th. So what was this paper? So this paper's title is called A New Type of Secondary Radiation, and the authors were C.V. Raman and K.S. Krishnan, published in Nature in 1928, volume number 121 and page number 501. So here, this is basically what they're describing. So it's a beam of sunlight. So this is just completely with the natural sources. Sunlight was converged and placed on a scattering material. So the scattering material is a liquid, and this liquid, which is by carefully purified by repeated distillation or a dust-free vapor. So it's very important. The liquid had to be completely pure, and then this light was allowed to pass through the liquid, and this would scatter that. And what happens after scattering was observed. So to detect the modified scattered radiation, complementary light filters were used. I'll show you in the next slide how this was done. So what you would see was light that came out after this particular scattering was done. And then what was observed was then noted down by the observer. So this is basically the experiment. So this is sunlight. This is white light that is coming through. There is a violet filter, and in this violet filter, that is what this violet filter does is that only violet light will be allowed to pass through. The rest of the, as you know, the sunlight consists of the Vibgyor, violet, indigo, blue, green, yellow, orange, red. So by putting a filter, only the remaining 6 are not allowed, only violet is allowed. And that is allowed to interact with this liquid, which is the scattering liquid. And then this scattering liquid that is present, is allowed to scatter this, and then the observer is here. Now you put a violet, a green filter here.
Now remember that this filter allows only the light of that particular color. So green filter would allow only green light. Because we only have violet light here, if nothing happened, you should not observe anything. But here something is happening by the scattering liquid. It is scattering light. Now there are two types of scattering. There is Rayleigh scattering and there is Raman scattering. Now I'll explain to you what these are. So in the Raman scattering, you have a mixture of violet and green is the Raman scattered light, and that is passing through the green filter and the observer is watching that. The remaining light, which is violet color, that is not passing through. Therefore, the observer won't observe it. Only the new light, which is the green light, is observing. So what is happening? Now, material, there is, light can undergo when it interacts with matter, different things. It can be absorbed, it can be scattered. And when it is scattered, typically its wavelength is not modified. So that is called as Rayleigh scattering. So the light is just simply scattered off by the medium, but the wavelength of the light is not changed at all. What Raman observed for the first time is that in addition to the normal unchanged wavelength of the light by Rayleigh scattering, a very small fraction of it now changes the wavelength, and that changed wavelength is what Raman has observed, and that is what is the green color that he observed in this. It is not necessarily that it is violet and green. Essentially, the wavelength of the light has got changed for a certain fraction of the photons. So we'll come back to this and describe it in more scientific terms. So this was published in several papers. It was published in Nature, and then it was published when immediately Raman went to an association in Bangalore and gave a talk, and then published in Indian Journal of Physics, published again in Nature, published in Indian Journal of Physics, and so several papers were published, and in fact also in press. So this is an original press cutting which is called as New Theory of Radiation, Professor Raman's discovery, and you can see this February 29th, 1928, and it says Professor C.V. Raman, FRS of the Calcutta University, has made a discovery which promises to be of fundamental significance to physics. And of course, it also quotes A.H. Compton, which is the Compton effect, who was awarded the Nobel Prize for his discovery of, Compton effect is neutron scattering. So, and also Raman gave the lecture 16th March 1928 in Bangalore, and you can see this schedule, inaugural address by Professor C.V. Raman, FRS, subject a new radiation. This was the first scientific address by Raman on his discovery. So why did Raman do all of these things? Because even at that particular time, Raman was quite aware that this is a very competitive field. Unless you establish your credentials first, you would not be recognized for what you have done. Because in Russia and in other places, people were investigating similar phenomenon on quartz, and they did observe similar results, but they were a little late in communicating their results. They communicated their results on May 6th. Remember, Raman communicated on February, and by then Raman published at least 9 papers. But in Soviet Union, which is now Russia, this effect was known as the Smekal-Mandelstam-Raman scattering. But of course now, even in Russia, now they call it as the Raman effect. So what is this? And this is the original Raman spectra which are there, which I'll explain to you more pictorially what's happening. And this is the Raman spectrograph, which is preserved in the Indian Association of Cultivation of Sciences today. Of course, it's a very primitive tool today, but at that particular point of time, this was what Raman used to observe his spectrum. Okay. And Raman, of course, was known for his public relations. He would invite all the people in Calcutta and show his discovery to the important people, and already there was a big buzz going on about this experiment. So typically, Nobel Prizes are announced in November. For example, now it's a standard pattern. In October, they'll be announced. During that time, they would be announced the second week of November 1930. And it was already announced, and and Raman was awarded the prize. But the problem is that you have to go physically to Sweden to receive the prize, and there were no flights. You have to go by ship, and typically the bookings for the ships you have to make much in advance, otherwise you can't get bookings.
So Bhagavantam, who was a student of Raman, who himself later became very famous, including he was the director of the Indian Institute of Science. So he came to know about this thread. There was a telegram from the Swedish Academy of Sciences saying that Raman got the Nobel Prize. But Bhagavantam came to Raman, congratulated him, but told him, how will you go? Because there is no time. Because this announcement is in second week and you have to be there on 10th December. How will you go to receive the prize? Then Raman opened the drawer of his table and he had already booked 2 tickets in July 1930. He had the full confidence that he's going to get the prize this year. So Raman was much well in ahead of time and he booked one for himself and one for his wife, tickets on this particular ship where he would reach Stockholm to receive the prize. And this was the prize that he was given, the Nobel Prize in Physics 1930 for his work on the scattering of light and for the discovery of the effect named after him. So it's very important. The prize is for scattering of light. Scattering of light, which is Rayleigh scattering without change of frequency or wavelength, is Rayleigh scattering. Change of frequency is Raman scattering. And the prize was given to him, is already knighted by this time, and he was affiliated with Calcutta University. So Calcutta University is the only university in the country to have a Nobel laureate in science in its ranks. Okay, so when Raman received the prize, he was very composed, but when he actually got the prize, he broke down. So this was a remarkable statement that he himself had told. So he said, when the Nobel Award was announced, I saw it as a personal triumph, you know, an achievement for me and my collaborators, because a bunch of work that has been carried out with a lot of creativity, for which I have been recognized. But when I sat in that crowded hall and I saw the sea of Western faces surrounding me, and I, the only Indian in my turban and closed coat, it dawned on me that I was really representing my people and my country. I felt truly humble when I received the prize from King Gustav. That was the name of the king at that time, King of Sweden. It was a moment of great emotion, but I could still restrain myself. Then I turned round and saw the British Union Jack under which I had been sitting. So you know what happens is, just like the Olympic medals, when you get the medal and the medal ceremony is there, you know, they raise these flags of the country to which you belong. India, of course, was not independent. So the flag for India was the British flag. So he realized that what he was sitting under was the British Union Jack under which I had been sitting. And it was then I realized that my poor country, India, did not even have a flag of her own. And it was this that triggered my complete. So Raman broke down and he cried. Okay, now that was the historical part of it. So now let me just tell you a little bit science. As I was mentioning, when light is scattered by molecules, most of the photons, you know, if you consider that light is made up of photons, most of the photons are elastically scattered. Elastically means there is no change in their energy. There is no change, if you consider it as a wave, no change in their wavelength or frequency. So the scattered photons have the same energy as the incident photons. So this is called the Rayleigh scattering. Now a small fraction of light, supposing you are counting the photons and you have 10 million photons. 10 million photons, that means 10 to the power of 7 photons. One of them in 10 million is scattered at optical frequencies different from the original, and usually its energy is lowered than the incident photons. That means you are having incident photons of a particular frequency and energy. The scattered photons, most of them 10 to the power of 7 photons, they have no change in frequency, no change of energy. 1 in 10 to the power of 7 has a change, and the change is usually lower. Some energy is lost, and what you're seeing is a photon of a lower energy. This process is called as the Raman effect. That leads to, now this is called inelastic scatter. Elastic scatter means energy is not changed. Inelastic scattering means that there is a change of energy. So Raman scattering, why is this occurring? Because this small change of energy corresponds to the change in vibrational energy in molecules, in rotational energy or electronic energy. But typically what we see in Raman is a vibrational energy. So the difference in energy between the incident photon what we have placed the molecule in front of, and the Raman scattered photon is typically the energy of a vibration of a scattering molecule. And so this gives you the plot of the intensity versus scattered light, gives you what we call today as the Raman spectrum. We can take a Raman spectrum and that gives us information about the vibrational aspects of molecules. So in pictorially, this is basically what's happening. This is the Rayleigh scattering. Light goes, the molecule is scattering, it just comes back with exactly the same frequency. There are two types. One, there is an increase of frequency, which is very rare. Typically decrease of frequency, which is normally what's happening. There is a Stokes-Raman. Okay, and well, this may be a little more, beyond. If you are not studied physics of this, I will skip it. There is the reason this happens is because of what is known as a change in polarizability in the molecules, the bonds that are connecting the molecules, and you have the dipole that you have to induce within the bonds. If that is not there, of course, you can't have this effect, but that will have all the components, and Raman's components can pick it up, and you can have this particular Raman spectrum. Okay. So, for example, you can take carbon tetrachloride, which is a liquid, and if you study the spectroscopy of this, the Rayleigh scattering, which is there's no change in frequency. So, for example, if your incident beam is 488 nanometers, Rayleigh scattering will be exactly same thing. It will be 488 nanometers. But the Raman ones, where this energy has changed, 218, 314, 459, are the difference between this and this is because the energy that is lost is the energy that has been absorbed by the molecule because of the molecular vibrations that are occurring. So Rayleigh scattered peak, very high intensity because most of the light is elastically scattered. But there is a series of Stokes shifted lights with longer wavelength, that is lesser energy, which is because of the fact that molecular vibrations are present which absorb this light. There is a series of anti-Stokes shifted which is much lower, which is a shorter frequency, which is at where energy has been gained. And spectrum independent, this is whatever you see, it does not matter whether it is 488 nanometers or some other light that you shine light. This is independent of that. You see the same lines, and these correspond to the vibrational energy. Therefore, the Raman spectroscopy, the Raman effect, is extremely important, not just from the curiosity point of view, because it allows you to study molecules in their fundamental nature. What are the vibrations in molecules and how you can relate to the structures of these molecules. That is why it becomes very important. Now, so for example, a little bit more detail, and if you do not understand, you can ask me in question answer session. There is a phenomenon called fluorescence. So you have to be careful that your fluorescence and Raman spectra are not overlapping with each other. So the fluorescence, for example, would depend upon the frequency. Therefore, you have to use typically long wavelengths of light, because if you use short wavelengths of light, fluorescence is enhanced, and fluorescence can mask the Raman spectrum. Therefore, you have to use longer wavelengths of light so that fluorescence is not induced. This is a matter of detail that I can explain to you if you have questions on it. So what are the advantages of Raman spectroscopy? So this phenomenon of inelastic scattering, where some energy is lost, that energy is picked up by the molecular vibrations. So you can know about the molecules. What are the molecules that are there? So it is a non-destructive technique to know about molecule. You don't have to burn the sample. You don't have to do anything. The sample, what you have, you can know about it by a non-destructive technique. And you can use visible light. And sample preparation is very easy because you don't have to have very difficult sample preparation technique, and you can probe through containers which are transparent, and particles which are very, very small also can be probed routinely. So there are several advantages of Raman spectroscopy, and in recent years actually it has become extremely important. It's one of the most powerful analytical techniques today known because of various other phenomena. Because there is a phenomenon called resonance Raman. And resonance Raman supposing there is the absorption of what Raman light, when a molecule takes up the Raman light, it actually is going to a state which is virtual. But supposing there is a real molecular state, that means there is an excited level, then that is close to this virtual state, then this transition probability of Raman increases enormously. So this is called as resonance Raman. And that means what happens is the sensitivity by which you can detect becomes tremendously improved. Even very low concentrations up to 10 to the power of -8 molar can become, you can detect it. So that becomes a tremendously great, a big advantage in terms of detection capability. Okay. So this is another important thing, is that Raman process is called coherent. Now, this is of course a lot of physics behind it, but very briefly, qualitatively, the excited state where this, this excited state is going, where this light is going, it exists only as long as the light is being shined. I remove the light, then it is not there. This is different from if a molecule actually absorbs light. If molecule absorbs light, then this light then can re-emit. That is called fluorescence. Here it is not like that. I shine light, the molecules are scattering this light, so it's called coherent. Only when the light is present, this process is there. When the light is switched off, it is shut off. And of course, a little bit slightly deeper, because I'm speaking to class. I think I've been told that I'm speaking to class 9 to class 11 students. So the sources of light must be strong sources. So typically today you have lasers which are utilized. When Raman, unfortunately, when he did his experiment, the sources were very weak. It was actually sunlight, which was so difficult for him to, in fact, to have observed it. And the sources can be monochromatic, that is single wavelength, so that the spectrum is uncomplicated. And there is a law of physics which says that the scattering efficiency increases as with the 4th power of frequency. So the bluer the light, the more the scattering. But of course, this will interfere with fluorescence, as I told you. So one has to have a compromise of this. So bluer the light, the greater the chance of producing fluorescence. So this is a complication, but this also gives you the better Raman scattering. And today, mostly lasers are used exclusively. Okay. So typically, this is how it will look like. You will have a setup where you have an argon laser with a certain power, or you can have krypton laser or helium neon lasers or diode lasers or neodymium YAG lasers and so on. So several types of lasers with various frequencies. So for example, if 488 is not good enough, you can go to 782 or 830 and so on. So different lasers are available. And you can have different detectors. So even if the scattered light is of low intensity, you can use photomultiplying tubes so that you can detect it. This was what was done in the past, but now you have much better detectors. So these are used, and the experimental can be done in a much more sophisticated way. Okay. So for example, I'll give you some exotic examples. Where can you use it? You can use it in most analytical techniques. So in fact, this is the most widely used technique now for analytical purposes. So one of the very exotic applications. So this was a painting in Italy. It's a 12th century painting on a church wall in Italy. Now this needed to be restored because it was fading. So what was this particular? So they didn't want to use any paints. They wanted to use the paints that were used by the original painters, so that it can be restored back as if the original painter was involved in it. What technique can give you this? So Raman analysis was done, and the original paints and pigments were identified by this Raman spectrum, and then those paints were utilized to restore this application. So this, of course, a very exotic application. I'll give you another application. These are two chemicals. This is a morphine, and morphine is given to people who are under extreme pain. I mean, unimaginable pain. Like, for example, somebody is in the 4th stage of cancer, and the suffering is so much that you want to give something like morphine, which will put you to sleep. But there is a drug which is heroin, which is in fact a drug which can take you to addiction, and this is illegal. So, but you can see the structure. If you're not careful, you'll see that both look same, exactly the same. But the only one difference is there. Here, this has got just this phenolic OHS here on the morphine. Here, this has got an ester group. Now, the Raman spectrum of the heroin, which you can see over here, and the Raman spectrum of morphine, which you can see in the top, if you see, both look very similar. But you know this here, there is this difference. This ester, the C double bond O stretching frequency, you can observe in the Raman shift at around 1740 centimeters inverse, which the morphine doesn't show. So by Raman, you can detect both are white powders. So how do you know which is what? So you can detect these two by simply by taking a Raman spectrum. And you can have applications, more sophisticated application. So for example, let us say you are converting cyclohexene to cyclohexane, you're reducing cyclohexene to cyclohexane by hydrogenation, and you want to follow this reaction in situ. So the reaction is occurring, you want to know when the reaction is over. So you are monitoring the disappearance of cyclohexene and the formation of cyclohexane. So again, Raman spectrum can tell you whether this C double bond C is present or absent, and once you know that it's absent, you know it's been converted to cyclohexane. And in fact, this is one of the, like for example, this is where this is a reactor where it's occurring, and this is an in situ Raman analyzer that is present, which can tell you what's happening. And this is called an immersion probe, which is along with the reaction. This is there, and as the reaction is occurring, you can see the disappearance of cyclohexene. So this is the this is how the monitoring is occurring. You start with 0. You go at every 17, 28 minutes, 38 minutes, you keep monitoring what's happening. And you finally realize at 1122 minutes, completely the reaction has been completed. Okay. So you can do it by also, like for example, you can see how cyclohexane intensity is increasing, how cyclohexene intensity is decreasing as the reaction is occurring. Okay. So I mentioned to you that regular Raman effect can be augmented with new techniques. One of them I told you was resonance Raman, when a real state is very close to this virtual state. But there are also other techniques which are now becoming available, particularly with the advent of nanotechnology. And this is called, one of them is called surface enhanced Raman effect, SCRS. So what happens when your molecules you take the molecule of interest and they are adsorbed on nanoparticles of silver, gold or copper. This Raman signal is enhanced by 10 million times nearly. So there is a lot of theory behind this, why this occurs, because one of the attributes is because the nanoparticles around them have enhanced electrical fields which allow a greater sensitivity. So you can couple SCRS with resonance Raman, and your amplification signal can go up to 10 to the power of 12. That means your detection range can go to concentrations of the picomolar. You know, micromolar is 10 to the power of minus 6, nanomolar is 10 to the power of minus 9, picomolar is 10 to the power of minus 12. So in that range, you can detect entities that you want to detect using Raman spectroscopy. Okay, so for example, again, I'll give you one more example, because again, all of you are probably aspiring to be chemists. So this is 8 femtomolar, okay, of benzotriazole, which you can detect without any problem, but because it has been on silver colloids. And see, this is 100% just benzotriazole and without anything. And but with 8 femtomolars also, the fact that benzotriazole is present, you can detect it. So this is a very, very powerful technique. And in fact, several years ago, when NASA sent their exploratory missions to Mars and they wanted to detect chemicals, they put this Mars microbeam Raman spectrometer on the payload, so that whatever are the chemicals that are present on the Mars surface or which have been coming out can be detected. So this is Raman spectroscopy for planetary exploration, because of the power that this particular technique has. Okay, so that is almost what I wanted to tell you about the science of Raman. But I just wanted to complete the history of Raman. So Raman left Kolkata in 1933. Why did he leave? like typically when people are involved, always there are controversies. When multiple people work together, there is always this unavoidable in all places, all situations. So Raman and another great figure, Meghnad Saha, was another giant of a scientist in India who discovered the Saha ionization in stars. So there were a lot of problems between them. And in fact, a lot of questions were about Raman, whether Raman knows about modern physics and so on and so forth. And there were also questions whether, lots of politics were there in terms of personalities. And when Raman appointed Krishnan as a professor at IACS, again, there were questions that Raman is appointing his own students and so on. So there was, a political sort of a struggle, and they forced Raman out of this place. And Raman had to resign from Indian Association for Cultivational Sciences. I mean, he could still be with Calcutta University, but he didn't want to continue. So at this time, he had an opportunity to go to Bangalore, where the Indian Institute of Science was being established. And so he was offered a professorship and a directorship there. So when this happened, of course, already there was a prediction by one of the science historians. So he said that Calcutta's loss will be Bangalore's gain. And he made a prediction which turned out to be very prophetic. At present, Calcutta may be regarded as the center of scientific research in India. At present is 1930s. But with the transference to Bangalore of one of her leading investigators, she will have to guard her laurels. She is Calcutta. And of course, later, as time would have told, Bangalore became the center of Indian science. And today, of course, Bangalore, with all its scientific establishments, truly is one of the centers of science. Okay, this is the Indian Institute of Science, where Raman spent from 1933 to 1948, where he formally retired at the age of 60. And even at Indian Institute of Science, he had some difficulties because he thought that the institute, they were highly paid, but they were not productive and not comparable to what was there in the rest of the world. Also, what was there at IACS. So he started a new physics department. And in fact, several brilliant people were recruited, like Bhabha, Sarabhai, G.N. Ramachandran, and so on. And he created many new things. So, but typically what happens is when you're stirring up and creating new things, you bring in controversy. Existing people are immediately threatened. So they feel threatened by this. And also Raman wanted to bring faculty like Max Born or Schrödinger. And this was creating a lot of trouble for existing people there. And therefore, there were a lot of controversies that were created. And two of the professors, both of them belonging to not physics, one of them was Britisher and the other was an Indian. Both resigned because of these new experiments that Raman was doing. And they had a petition against Max Born's appointment. And Raman was accused of being arbitrary. And he was also accused of being, financially, that he was committing financial impropriety. So the government of India actually appointed a committee called an Irvine committee. And this Irvine committee found that Raman was guilty of some of this, but so Raman had to resign as director, but he continued as professor of physics till 1948. And finally, he had to retire from Indian Institute of Science. So during the last phase, but after his retirement, he had a support from the Maharaja of Mysore. So he was quite supportive of him. So he donated land quite close to the Indian Institute of Science, and he allowed Raman to create a new institute called the Raman Research Institute. And Raman did some fantastic work there. And one of his greatest students at this particular time was the Pancharatnam, who did work on what are now called as Pancharatnam phases. But Raman was very bitter about the last years of experience at the Indian Institute of Science. So he planted tall trees that he could not, which would prevent him from seeing Indian Institute of Science from Raman Research Institute. Of course, today that problem is not there. There's so much of traffic and buildings in between that you won't see it anyway. And and also India became independent. The new people had come into picture into the thing, and Raman was not particularly approval of this particular thing. And so while he wasn't particularly happy at the direction at which Indian science was going, and then he chose to close all the doors to himself, except on Gandhi's birthday, he would open up all his laboratories, welcome young people, young students like you to his laboratories, show the experiments, and give a Gandhi lecture every year. So finally, to conclude this entire thing, what did Raman do? Raman, I will just kind of summarize, he was not a trained physicist. He was an accountant general, but he trained himself in physics on his own, published papers of quality comparable to the best in the world, working independently as an amateur. Then he was picked up by Ashutosh Mukherjee as a Palit professor. He discovered Raman effect, which is a scattering effect, which is an inelastic scattering. Now this effect has enormous applications today as an analytical tool. And he was a colossus on the Indian science scene without a question. He was associated with Indian Academy of Sciences, Indian Institute of Science, Raman Research Institute. He formed the Indian Academy of Sciences. His contemporaries were Saha, Bose, both SN Bose and JC Bose. JC Bose probably was a senior, Homi Bhabha, Sarabhai. Most remarkably, physics runs in his family. These are his nephews. S. Chandrasekshar, who won the Nobel Prize in 1983. S. Ramaseshan, who was the director of Indian Institute of Science, was well-known expert in crystallography. Another S. Chandrasekshar, who was an expert in liquid crystals. S. Pancharatnam, who discovered new phases. And his students, K.S. Krishnan, who was the director of the National Physical Laboratory, and G.N. Ramachandran, who was one of the greatest physicists post independent India. In fact, he established what is today called as biophysics in India. Okay. So Raman's effect, both not just in science, but in the Indian science scene, has been enormous. Finally, Raman had this message for Indian people particularly, and it's very important even today. So what he says is, I can assert without fear of contradiction that the quality of the Indian mind is equal to the quality of any Teutonic, Nordic or Anglo-Saxon mind. What we lack is perhaps courage, perhaps the driving force. We have developed an inferiority complex. This is particularly true of the era where he was. I think what we need in India is the destruction of the defeatist spirit. You know what, in India today also, so-called Chelta hai type of spirit. We need the spirit of victory, a spirit that will carry us to our rightful place under the sun, a spirit which will recognize that we, as inheritors of a proud civilization, are entitled to a rightful place on this planet. If that indomitable spirit were to arise, nothing can hold us from achieving our rightful destiny. I think most of these words are even relevant today. Most of the, in terms of our capability to do science is second to none. We have the capability to think, minds that are second to none. It's simply the question of applying and reaching the right direction. Okay, Raman died in November 21st, 1970, and his was cremated, and the place where he was cremated was planted a tree, and this tree is still there. So if you go to the Raman Research Institute, in the lawn that is present in a corner of a lawn, you will find that this particular tree is there. So with this, I'll end this talk, and if there are any questions, the last 15 minutes I'll spend on that.
Excuse me, sir.
Yeah.
Hello, sir.
Sir, why does the blue light gives more scattering in Raman effect?
Can you please repeat the question? Am I not clear?
Sir, why does the blue light gives more scattering in Raman effect?
Okay, so not just typically, why is our sky blue? Our sky is blue because when for example the light that is coming from the sun is scattered by the particles and molecules present in our atmosphere, And typically the light which has got the lowest wavelengths that are present, those are scattered much more to larger directions, to larger much more efficiently. And therefore it is a light consists of different forms, like for example you have the blue light with the lowest wavelength, the red light with the largest wavelength. So this scattering of by molecules occurs with the lowest wavelength. Things get scattered the best, and that's why our sky is blue. And the same thing is applicable to Raman. Raman scattering is not anything different. It is simply that there is a loss of energy which is attributable to the absorption of that energy for all the vibrational modes present in the molecule.
Hello, sir.
Yeah.
Hello, sir. Can I ask a doubt, sir?
Yeah, please go ahead.
Yes, sir. Sir, what is the basic principle of Raman's spectroscopy and fluorescence, sir?
So I mentioned to you.
Basic principles of that.
Yeah. In Raman's spectroscopy, yeah. Can you hear me?
Yes, sir. We can hear you.
Also hear a okay. So in Raman spectroscopy versus fluorescence, light is absorbed by the molecules and then okay. So once again, let's try again. So in in fluorescence, light is absorbed by the molecule and then re-emitted. This absorption takes populations present in the lower energy state to the higher energy state, and they then come back to the ground state by emitting that light. In Raman, light is scattered, and light is scattered by molecules, and the scattering occurs. Most of the light is scattered elastically, no change in wavelength. Small particles, small amounts of light is scattered by inelastically, that is, there's a loss of energy, which corresponds to the vibrational modes of molecules. Molecules are comprised of atoms. They're not standing still, they're vibrating like this. Supposing, let's say water, there's O and H. The O and H are not static as we write here, they are vibrating. Then the HOH, they're bending. So all of this, all these motions that are occurring in the molecule, if light of the right energy is absorbed by the molecule, then they will be shown up as a spectrum. So that is basically this loss of energy by the scattering is picked up by the molecule as vibrational, corresponding to the vibrational energy. That is why you are seeing those vibrational bands in the spectrum. So that is the fundamental difference between Raman spectroscopy and fluorescence.
Sir, I have a doubt, sir.
Yeah.
Sir, in what ways are Raman spectroscopy useful in the modern days, sir?
Well, I showed you. This is the modern day only. I showed you. We sent this thing all, and it's an analytical technique. It can you can detect molecules by this. So it's all its uses are in the modern day only.
Sir?
Yeah.
So why the scattered lights is low in intensity?
Because of the probability of if I have 10 million photons, only one of them is scattered inelastically, obviously the intensity will be low, right? The rest of the intensity is very high. That is which is scattered elastically is very high, but the ones that is scattered inelastically, which is a loss of energy, is very low. That's why you find that it is low.
Sir?
Yeah.
Sir, if sky is blue, then why do we see sky in red or orange color in evening, sir?
Yeah, you have to tell me now. Why do you see that? I mean, I would like to put the question back to you. Why do you see it red or orange in the blue?
Sir, because the light given by the sun in day afternoon times are less in the evening, sir. So that, sir.
What? Say it again.
Sir, the light which is given by the sun in the afternoons are more, sir, so that it will give us a bluish color, sir. But in the evenings, as it becomes very less light.
No.
So that that's how it changes, sir.
Then maybe due to rotation of the earth.
Yeah, sun gives the same amount of light. It is the angle of sun versus
Sir, in
Earth
the
that is different.
afternoon, in the noon time, the sun is just above
Directly above us.
us, and at the evening it is
Right.
far away.
So
So
if
the
it is
red,
far away, what happens is
so
that
the red,
all the blue and the green, they are scattered off to, because they are scattered so well, they are just scattered off, and what remains is
the
the
red
red
light
light. That is what we see,
with
therefore, because
high
of this
wavelength.
particular thing. Okay.
Yeah.
Sir, this occurs during sunset and sunrise, sir.
Yeah. What?
Because red color has longer wavelength, sir, and its intensity reached to observer is more compared to other colors, sir.
Because of the fact
And
that
hence
the rest of the light which is scattered away, we are not able to see that.
Yes, sir. Hence the sun appears
Yeah,
red during
exactly.
the sunrise and sunset, sir.
Exactly. Any other questions?
Sir,
Yeah.
how the one photon in those photons will be responsible for the changes in wavelength, sir?
No, yeah, once again, to just answer the question, why is change of wavelength occurring? Because there are fundamental things happening in molecules which absorb that particular energy. The fundamental things is that when, let us say you take a molecule that is like oxygen, water, hydrogen, those atoms that are connected to each other, they are not standing still, they are moving, they are vibrating, and that vibration, that vibrational energy corresponds to the energy of this particular inelastic scatter. Therefore, in molecules, suppose you take a complicated molecule, let us say you take benzene. It has got carbon-carbon bonds, carbon-hydrogen bonds, hydrogen-carbon bending modes. All of this energy that is there, that can be, if for example, energy of a suitable energy is given, then that can be absorbed. That is basically why you are able to detect it. You are able to, I showed you the detection of morphine versus heroin. The reason you could do it is in heroin, you had this carbonyl unit, C double bond O. So that C double bond of frequency, you can detect it. And that is the energy of absorption. That is why you are able to see that loss of energy of the scattered photon is picked up by this vibration.
Drone is used for which purpose, sir?
Sir?
Excuse me? Yeah.
Sir?
Yeah.
Sir, see. Sir, why C is only blue color, sir?
I couldn't understand the question.
Sir, why C is only blue in color?
Yeah, again, this is something that you should know. I mean, you please check it out. Why sky is blue, why sea is blue? Please check it out. If you don't, you go to the NASA web page and check it out.
Sir,
it is definitely not due to. It is not due to reflection. I can tell you this much. It's not due to reflection.
Sir, what purpose the heroin drug is used for?
Heroin should not be used. It's a narcotic. That means that you get hallucinations when you take heroin, and it's a banned substance. It's illegal to use heroin. Morphine, on the other hand, is used as a sedative. Morphine is used as a sedative in hospitals for patients suffering from incredible pain.
Sir, can you explain about nanotechnology, sir?
What do you want to know about nanotechnology?
I want to know the advantages of nanotechnology, sir.
No, it's a, It's a question that it's there are many aspects to this. There is no general answer to this. Nano means firstly you are reducing the size of the species that you are interested in into dimensions which are small. So depending on the application you have in mind, there will be different types of physics comes into play. So physics that cannot be accessible by using bulk materials are accessible by using nanomaterials. That will allow new types of applications to emerge from that. But beyond that, one has to really look at which particular application that you're interested in, and then you can go into that particular physics. But broadly, physics that is not acceptable, which is not accessible to you in bulk materials. I'll give you one example. Supposing you take gold. So gold, is like this lustrous blue color in its native state when you wear it in ornaments. But you take this gold and subdivide it into nanoparticles. Its color becomes violet. So the properties that are accessible to you at the nano range are different from what they are available in the bulk range. Then there could be several applications. Depending on the application, you can tune this. Any other questions? If there are no other questions, then I think we'll close the session. Wait for a few seconds. I don't see any other questions, so
thank you. Students, if you have any question, you can ask. Any doubt or sir, can I share your mail ID, sir, if they want to?
Sure, absolutely. Yeah, you can do it. Yeah.
Is there any question, students? Any doubt? I think it's not there, sir.
Okay, that's wonderful.
I'll share your mail ID, sir, with the students.
Yeah.
Thank you so much, sir, for being here for such a long session, sir. It was wonderful to have you.
Thank you.
And definitely the students will be benefited by the same.
Sir, I have a doubt.
Yeah, you have a doubt? Yeah. Who is that? Name yourself.
I'm Minhas from JNV West Godavari.
Can she ask, sir?
Yeah, please.
Sir, is there any limitations of Raman effect?
So so Raman effect depends. That is, to use it in spectroscopic tool depends upon the molecules having vibration. So monoatomic species can't be detected by Raman. There has to be a vibration or bending, right? So none of the monoatomic species you can detect it. But if there is anything diatomic or beyond that, you can detect it.
Okay, sir. Thank you.
Okay, thank you so much, sir, for
Thank
being
you.
with us.
Thanks a lot. Thank
you, sir.
Bye.
Thank you so much. So, students, we have our next session at 2:30. Okay, 1 minute. Yes, it's 2:30 to 4 p.m. That is by Dr. Sutapa Ghosh. Okay. And some of the students are asked to present their reflections in this valedictory function. Have you prepared it? Master Allah Prashant?
Yes, ma'am.
JNV Krishna? Allah Prashant is there? From JNV Krishna, are you there?
Yes, ma'am.
Have you prepared your reflection? Hello, but am I audible?
Ma'am?
Yeah, Allah Prashant, you have to present, you may be asked to present a reflection in the valedictory section. Like, how did you like the program? What did you like in the program? So
Yes,
and so. Okay, next we ask from Kumari Ananya. Of 9th class. Ananya is there? Ananya?
Yes, ma'am.
Okay. prepare yourself. One more is there, Dr. Master Alan George. Alan George from Kerala, Kannur.
Yes, miss.
Yes, Alan, have you prepared your reflections?
Yes, miss.
Okay, fine. So we can leave the meet now, okay? I'll share the mail ID. We can leave the meet and we'll meet at 2:30. What?
Ma'am, do you have the link of the first day of the
Link of the
program, ma'am?
first day for YouTube, na?
Yes, ma'am.
Yeah, wait,
Yes,
ma'am.
ma'am.
Let me ask. We will send you, okay? After 2:30, during that time we will share it, okay?
Okay, ma'am.
Okay. Now you can go for your lunch.
Ma'am.
And be here sharp at 2:40, 2:30, 2:25. What?
Ma'am, what where results of quiz competitions, ma'am?
Results of what?
Quiz competition.
Quiz competition.
Which competition, madam?
Okay. That we don't know. Maybe we will send you the details later, or maybe in the valediction it will be there. Definitely, you will be acquainted with whatever is the result. Okay, don't worry about that. Yes. You want
The
to say
result
something?
of yesterday's PPT presentation.
Yesterday's
PPT presentation.
Ma'am, you also want to present.
Who's PPT? You want yesterday's PPT presentation? Of whose presentation you want?
Results of yesterday's presentation, ma'am.
Yeah, quiz results are with us. They will be declared in the valedictory. Okay, don't worry.
Ma'am,
We have got the results.
did all students get the chance to present PPT?
That 6 p.m. to 7 p.m. you are asking about that paper presentation, no?
Yes, ma'am.
Only 17 students they were selected for that PPT presentation out of 77, I think. Okay, so it's up to the principals are from Hassan, and it's done yesterday, no?
Ma'am, we have prepared a lot, ma'am. So
you have prepared. You do one thing. You can send it to us, right? You can. You know our mail ID.
Yes, ma'am.
Yeah, I'll type our mail ID. Yeah, I'll type our mail ID. Janvi Rangareddy.
Represent my school, ma'am.
You send it to our mail under the head of RCSE 2022. Okay.
Yes.
Your name, your school name should be mentioned clearly.
Okay, ma'am.
Okay. Shall we wind up now?
Yes,
because we have to come back.
Yes, ma'am.
Yeah, thank you. Yeah.
Thank you, madam.
Okay, beta, bye. We'll see you at 2:25.
Hello, bro.
Hello. Hello. Mute. Unmute your mic.
ಜನ ಮಾತಾಡೋದು
ಹಾ
ಕನ್ನಡ ಬರುತ್ತಾ?
ಬರಲ್ಲ.
ಬರಲ್ಲ. ಯಾವ ಸ್ಕೂಲು?
ಅಯ್ಯಪ್ಪ, ಜೇನು ಬಿಜಾಪುರು.
ಜೈನಿ ಬಿಜಾಪುರ್. ಹಾ. ಅಪ್ರ ಸರ್ ಗೊತ್ತಾ?
ನಿಮ್ದು? ಹಾ
ಅಪ್ರ ಸರ್ ಗೊತ್ತಾ? ಅಪ್ರ ಸರ್
ಯಾರು? ಹಾ ಗೊತ್ತು. ಹಿಂದಿ ನಾನು 6th ಬಂದಾಗ ಬಂದಿದ್ರು, 6th ಇಂದ ಟ್ರಾನ್ಸ್ಫರ್ ಆಯ್ತು ಅವ್ರಿಗೆ.
ಹೌದು. ಯಾ ನಮ್ದು ಜೇನು ಕೊಪ್ಪಳ.
ಗೊತ್ತಾಯ್ತು.
ಬಂದಿಯಾ ನಮ್ಮ ಸ್ಕೂಲ್ಗೆ?
इसका हाउस मास्टर से भेजिए.
ಬಸ್ಸು ನಮ್ಮ ಸ್ಕೂಲಿಗೆ ಬಂದಿಯಾ?
ಇಲ್ಲ, ನೀನು?
ನಾವು ಕೇಳಿದೀವಿ ಅಷ್ಟೇ, ಬಂದಿಲ್ಲ.
ನಾವು ಬಂದಿಲ್ಲ. ಯಾವ ಕ್ಲಾಸ್?
11th.
Boys, why you are here? You are not going for lunch? All of you go for lunch. Leave the meeting. All of you leave the meeting immediately. Why this boy is here? हेलो, ये मीटिंग खत्म नहीं हुआ? अच्छा, मैं बोलते मीटिंग खत्म हो गया, तो मैं एम टेलिंग देम टू गो. हाँ जी, ठीक है रहना. ठीक है विल गो फॉर लंच. ओके. मैं सोचा था फालतू से बैठे इसलिए जाओ बोल रहे हैं. ओके.
Good afternoon, madam.
Good afternoon, Ambur. What's your name
Madam,
exactly? What is
madam, my Madhusudan Reddy, madam.
Okay, okay. Your name is Madhusudan Reddy. Okay.
Madam, have you received my mail, ma'am? I have sent to Jane Viranga Reddy. Ma'am.
You have already sent? Okay. I'll ask our principal, sir. Huh? I don't have access to the mail. I will ask madam. Huh?
Okay, ma'am.
Your name, once again, you tell me your name?
Madhusudan Reddy, madam.
Madhusudan Reddy. Janvi?
Prakasham 1.
Prakasham 1. Okay.
Madam, can you give me an opportunity to share my reflection on RCSC, ma'am?
But that already 4 students are still there. Have you prepared something?
Yes, ma'am.
Can you share it? Can you tell me now if there is any grammatical mistake? I can check. Can you speak
Okay,
now?
Okay, ma'am.
Yes, yes. Yes, Madhusudan. Quickly you do it.
Respected dignitaries and my dear friends, a glorious good afternoon to you all. Myself, L. Madhusudan Reddy of class 9th, studying in Jawahar Navodaya Vidyalaya, Ongole, Prakasham 1. Since 3 days, we are having RCSC 2021 to 2022. It was a good opportunity for me to participate and to be a participant in RCSC 2021 to 2022.
Okay.
I collected much information through these sessions and through some activities. And also one of my favorite session is Sir Manoj Sir session. He inspired us and also he motivated how to learn physics easily.
Okay.
Through this, somewhat I turn my course into science, and I also like to have some researches on science.
Okay.
Since 3 days, it is a wonderful journey for me, and also it is a memorable day for me, and it is a memorable moment for me.
Okay.
Thank you, one and all.
Okay. You pen it down. Okay, Madhusudan. You write it down. At the end, once the 4 are done, no, then I will give you a chance. Okay, speak. Okay.
Thank you, ma'am.
Don't make any grammatical mistake. Okay.
Okay, ma'am. Ma'am, I will write down, ma'am, the top.
Okay.
Ma'am, can we also give a feedback, ma'am?
Good afternoon, everyone. Am I audible?
Yes, madam.
Good afternoon. You had your lunch?
Yes, ma'am.
Yes, ma'am.
So now again we are there after our lunch for the post-lunch session, and we have with us our Dr. Sutapa Ghosh, ma'am. Ma'am, am I audible, ma'am? Let's welcome Dr. Sutapa Ghosh ma'am, Senior Principal Scientist from CSIR, Indian Institute of Chemical Technology, Hyderabad. Hello ma'am. I think some network issue. Let's wait.
It is getting muted again and again, my microphone. I don't know what is happening.
Okay, okay ma'am.
Can you hear me now?
Yes ma'am, I can hear you ma'am. I can hear you now.
Okay. Shall I upload my presentation?
Yeah, okay ma'am. You can upload ma'am. So we have Dr. Sutapa Ghosh ma'am with us, who is working as the Principal Scientist in Polymers and Functional Material Division. Madam's research interest are on specialty polymers, nanomaterials and nanocomposites, with new understanding on fundamentals and technology for developing self-assembled structures, morphologically evolved interface, and multifunctional materials for energy storage, solid polymer electrolytes, adhesives, and biodegradable packaging by tailoring the formulations and chemical structure of materials to exquisitely control materials properties using extensive experience in polymer synthesis, nanomaterials, and nanocomposite synthesis, and molecular modeling. Madam has completed several research projects via clay-based nanocomposites for biodegradable food packaging, that is DBT, conducting adhesive DST, polymer nanocomposite based solid polymer electrolyte for battery and solar cell DST, graphene composites for energy storage, synthesis of stereoregular polymer using metallocene catalyst, polymeric scaffolds of proliferation of adipose derived stem cells. In the Global Hospital Hyderabad, Madam has published her scientific work.
I'm interrupting you 1 minute, but there is some problem. I think network.
Yeah, what happened?
I'm not able to upload. Why it is?
We can see it, ma'am. We can see your presentation, ma'am. It's very much visible, madam.
Okay, it is visible?
Yes, ma'am, it's visible. Yes, ma'am.
Okay. Okay, is it okay?
Yes, ma'am, it's okay, ma'am.
Okay.
It's visible, ma'am. Yes.
Okay, madam, carry on.
Okay. Okay, ma'am. Ma'am has published her scientific works in high impact journals that are more than 50 in number and guided 8 PhD scholars and 20 dissertation students, among them 4 scholar awarded PhD so far. And Madam Ghosh has been awarded with AIST Fellowship Japan in 2007, Bicast Fellowship DST in 2008 and 9, ALA Fellowship Australia in 2010, and Raman Fellowship CSIR in 2013. A warm welcome, ma'am. We welcome you, ma'am, and our students will definitely be benefited by your session, ma'am. Now, am I audible, ma'am? You can take over the meeting, ma'am.
Yeah.
It's visible, ma'am. No issues.
Yeah. Yeah. Good afternoon to all. I am Sutapa Ghosh, working as Senior Principal Scientist at CSIR IIT Hyderabad. Who are from Hyderabad may be knowing it. Previously it was a regional research laboratory. Afterwards it was named like Indian Institute of Chemical Technology. Why CSIR? Because it is Government of India, Council of Scientific and Industrial Research. We are coming to this group. So we write like that. We are under CSIR and our lab name is Indian Institute of Chemical Technology, that is IICT. So today I will be speaking about nanomaterials and composite for energy and healthcare. I think you must have heard nowadays that nanomaterials are people are much attracted towards nanomaterials and composites because of their practical applications for our day-to-day life. I'll be talking on that today. If any question is there, you can ask me at the end. First, what is nanoparticle? What are the nanoparticles? So coarse particles are smaller than 10 micrometer. Finer particles are smaller than 2.5 micrometer, and ultra-fine particle whose particle size will be 0.1 micrometer, that is 100 nanometer. So the particles whose dimensions are between 1 nanometer to 100 nanometers, those we call nanoparticles. So nano devices from the Greek word nanos, which means dwarf or extremely small. It can be used as prefix for any unit to mean the billionth for that unit. A nanosecond is a billionth of a second. Nanoliter is a billionth of a liter, and nanometer is a billionth of a meter, or 10 to the power -9 meter. Now, in our day-to-day life, how we were utilizing, we can see the average width of our human hair is on the order of 100,000 nanometers. A single particle of smoke is in the order of 1000 nanometers. Nanotechnology is nowadays very important to us. Various applications we can see in all fields, almost all fields, means medical, pharmaceuticals, chemicals, automotive, energy production and distribution, aerospace, environment, defense, textiles, agriculture, information technology, of course materials and telecommunications. About some of them. So nano materials and nanotech inventions is not new. We are using, since long time we are using those. So nanowares of silicon and other materials have remarkable optical, electronic and magnetic property. We are using in solar cells and all since long time, electronic devices, we are using silicon based nanomaterials. Then people use nanomaterials of soot in tires to make it black. From 19th century, we used to make the tire black. We used to use that soot. Not only that, our ladies people used to apply that kajal and all. Those are also from the soot. And then we used to use the color pigments, the stained glass of means gold and silver nanoparticles we used to use for coloring to stain the glass. You must have seen, who are in Hyderabad must have visited, who has visited in Salarjung Museum and all. You have seen colored glass, Nizam's all vessels and all are colored glasses. Those are made by silver, gold nanoparticles. So nanoparticles we cannot avoid. The sugar molecules are also in nano size, and in milk, food which is full of milk which we drink every day, which is full of nano size particles of casein. And our blood, means our full body, living body, we are a living proof of nanotechnology. So nanomaterials are used for appliances, automotive, coatings, electronics, food, beverage, health, fitness, children goods, home, garden. How means in windows, our windows means in the car windows and all, we put titanium dioxide coating. Why? To repel the dirt. For ladies makeup, that the colored things, sometimes we see that who are girls using nail polish, some shining thing is applied in the nail polish or lipsticks. That shining thing can be made used, or sometimes some coloring, red color, blue color, those are used nanoparticle. Clothing, our clothing, water repellent or dust repellent, we use nanoparticles. And bulletproof jacket, paint nowadays you must be seeing that they are showing that dark proof paint and all these things. They are adding in the paint that nanoparticles. Even in sunscreen, even in concrete is a composite based on, sometimes based on the nanoparticles. Sometimes we see that nanoparticles, some people say nanoparticles are hazardous, but the best approach should be the precautionary principle. We should take precaution and do our research. But all the nanoparticles are not hazardous. Classification, we are having zero-dimensional nanoparticles, as we are seeing that particles. One-dimensional means this kind of nanowires, nanorods and nanotubes. Two-dimensional is this kind of nanocoatings, nanofilms, and three-dimensional is a bunch of nanocoatings, nanofilms are called three-dimensional nanoparticles. So classification of nanoparticle, dimensionally we can do one-dimensional, two-dimensional, three-dimensional. Simply I have shown, you can see that simply one-dimensional, two-dimensional, three-dimensional. One means thin films of surface coatings. Two-dimensional fixed long nanostructures on the sheet. It can be two. And 3D means bunch of films, membranes, bunch of membranes. These things do not pose any health risk. Sometimes we see that free long aspect ratio nanowires means big nanowires. This can have health issues. And this free small aspect ratio nanoparticles also can show the health risk. Then coming to the morphologically, there is high aspect ratio, nanowires, nanohelix, nanozigzags, nanopillars, nanotubes, nanobelts are depending on the high aspect ratio. Morphologically, we can divide high aspect ratio and low aspect ratio too. And low aspect ratio materials are nanospherical, nanohelix, nanopillars, nanovires, nanopyramids, nanocubes, and various others. So another we can go for compositional division, where it is compact, means inside is filled. Another can be hollow, inside is hollow. And composition, another can be composite. Composite means composed of more than one material. That can be coated, means one material can be coated on another material. That can be encapsulated, means one material can be encapsulated in that. Another can be barcode, means one after another. Another can be mixed, simply mixed. And depending on the uniformity and agglomeration state also we can divide them. That can be isomeric and inhomogeneous. Inhomogeneous means there is no order. Just like that they are distributed. And isomeric means some orderly distributed. So in isomeric and inhomogeneous, they can be dispersed or they can be agglomerated. Dispersed means they are nicely dispersed, and agglomerated means they are coming close together. And then when agglomeration is happening, their nanoparticle property we have to sacrifice. So always to get the best nanoparticle properties, dispersion is we should make it in dispersion mode, and we should avoid agglomeration. Classification of nanomaterials, we have taken so many same pictures. You can see different variety. This is cubic. Sound is please. This is hollow tubes. You can see, and these are the fibers. You can see these are something like cubic type. You can see, and here you can see the fibers. You can see some nice brush type structure. You can make whatever you want by changing your synthetic methodology. And in the scanning electron microscope, from the scanning electron microscope, we can make out what is the morphology of this material. What makes it so important, so useful? So here we can see large spherical particle do not cover much surface area. When we are taking bigger particle, you can see only this much portion is touching the surface. But in this big 10 micrometer particle, only this much surface is covered. But when nanoparticles of equal mass of small platelet particles provides thorough coverage. Here you see small particles, if you see, it is showing thorough coverage. Full surface is covered. But if you cover with this big particles, so much place will be vacant. But here, if we cover it with a small particle, all surface will be covered. It will be 106 times more coverage. So by patterning matter on the nanoscale, it is possible to vary fundamental properties of the materials without changing the chemical composition. So without changing the composition, if we make the material in nano size, then we can see the property changing. Unique characteristics of nanoparticle, they are having surface to volume ratio. Just now I have shown that surface to volume ratio is large for nanoparticle. Then high percentage of atoms or molecules on the surface. As it is small, so high percentage of atom and molecules will be there on the surface. Then surface forces are very important, while bulk forces are not that important. Metal nanoparticles have unique light scattering properties and exhibit plasmon resonance. Semiconductor nanoparticles may exhibit confined energy states in their electronic band structure, can have unique chemical and physical properties, and same size scale as many biological structures. In that size, many biological molecules will be matching with this. So that can be utilized in biological application. So what are the unusual properties of nanoparticles? Lower phase transition temperature, increased mechanical strength, different optical properties, altered electrical conductivity, magnetic properties, self-purification and self-perfection. Here you can see as the percentage of atoms on the surface increases, the mechanical, optical, electrical, chemical and magnetic properties change. Obviously, when it is nano, as we have said, the many number of percentage of atoms on the surface will be increased. So obviously the properties, different properties will be changed. For example, here we can see that gold and silver. Here you say silver nano prisms. Color is orange kind of things. Here you can see silver nanosphere, color change. Again you see these three are silver nanospheres. When it is 120 nanometers, it is yellow. When it is 80 nanometers, it is greenish. When it is 40 nanometers, it is fully blue. For example, gold spheres, you can see. Gold spheres 100 nanometer is orange type. And when it is 50 nanometers, it is becoming green. And you can see the shapes also. Silver nanoprisms structure is morphology is like that. Gold nanosphere 100 nanometer, gold nanosphere 50 nanometer, smaller. And color is changing because of the size. And here also you see the size, this is bigger, this is lower than that, this is lowest. Color is changing from yellow to blue. Why we need nanomaterials? Nanotechnology exploits benefits of ultra small size, enabling the use of particles to deliver a range of important benefits. Small particles are invisible. Say for example, just now I spoke about the coating, paints. In paints, if we add this nanoparticle for dirt repellent, as a dirt repellent, it is not visible because it is nano size. Naked eye you cannot see, but property enhancement will be there. So this is the very important thing. And small particles, they are invisible, they are weight efficient. Okay, the behavior of nanomaterials may depend on more surface area than particle composition itself. So relative surface area is one of the principal factors that enhances reactivity, strength and electrical property. Main thing is relative surface area. More surface area is making it more efficient. So various type of nanomaterials I have listed out. You must have seen gold, silver, gold, palladium, copper, etc. Then metal oxide, zinc oxide, copper oxide, TiO2, iron oxide. Then organic nanomaterials, you must have heard micelle for emulsions, and then liposome, hybrid material, dendrimer, nanosphere, nanocapsules. Then carbon nanomaterials are very much popular nowadays. Under carbon nanomaterials, graphene, fullerene, CNT, carbon dot, carbon nitride, so many. So synthesis of nanomaterials, I will not go in depth. I will just tell you the outline. So it can be two ways. Means from bigger we can start smaller, that is called top down. Means basic unit say big, we will break it. This is medium and this is nanoparticle. So by breaking big unit to smaller unit means top down approach. What are the different procedures? Mechanical milling means that mechanically you can break the things. Then electro explosion, arc discharge, lithography, exfoliation, chemical etching, laser ablation, sputtering. You may not have heard all these things. Main thing you should remember that top-down approach means from the bigger you are going to smaller. Okay, that is called top-down synthesis methods. Means we are starting with bigger particle and we are chopping it and coming to the smaller nanosize. Simple. And then bottom-up approach means we are starting from atoms or molecules, then we are going to nuclei or nanoparticle, then finally we are going to various morphologies. It is directly from atoms you can start. So whatever blue things are there, they are there in liquid phase. Most of the things, most of the reactions are going on liquid. Only this brown, whatever brown are there, this synthesis can be done in solid phase, and this gray things we can use in gaseous phase. For newer stage, no need of remembering all these things. Only two things you remember: top-down synthesis methods and bottom-up synthesis methods. Here I have listed out that which is beneficial in which district. For example, say ball milling. Here yield is high, but and cost is also low. By milling means like mixture, how you chopping with the force ball milling, we can get, so cost is very low. This is mechanical procedure. Efficiency very low means how much you can mill. When you need a large scale production, you cannot use ball milling. Controllability is also not there. Means depending on the ball milling process. Means some can be small, some can be big. Means there is no control. Similarly, many procedures are there. I am not going to this. Just I have listed out to show you the names. Ball milling is there. Electrospinning is there. Etching is there. Very easy thing you can do. You can take a graphite thing and put a sellotape and peel it up. So one layer is coming out. Okay, like that also etching you can do. These are all mechanical, means physical process. Then chemical vapor deposition, physical vapor deposition is also there. Molecular beam epitaxy is there, sputtering, deformation, wet chemical routes are there. So more popular is nowadays wet chemical routes because people can get whatever they want, but there are some loopholes. So that's why some cases, graphene synthesis cases, CVD, PVD are very, people are taking up more for high production and commercialization. Now in my lab, I have shown some, brought some video. You see from green tea packet, we are making this, can be interesting to you. Just see this video.
Ma'am, you are not audible, ma'am.
Not audible?
Now it's audible, ma'am. Now audible.
I am not talking. My video, can you hear?
Okay, okay. I'm sorry, ma'am.
I am not talking. My video.
This video in this video, no sound. That's why.
Can you hear the video?
No, ma'am. It's only visible, not audible.
Oh, video sound you are not getting?
It's visible only, ma'am. Audio is not there.
Now also not there, madam?
No, ma'am.
Are you understanding? Okay, I will tell. So from green tea extract, we are making nanoparticles. Okay? Here they are taking green tea packets. They are pouring green tea in that beaker. They have taken deionized water. So they are pouring these green tea packets. Now this is deionized water they are adding. 200 ml water they are adding. The measuring jar, they are taking 200 ml water. So to take 200 ml, 100 ml jar, they will take 2 times. 100 ml plus 100 ml. Can you hear me? I'm audible?
Yes, madam.
Yes, ma'am.
Yes, ma'am. Yes, ma'am. You're audible, ma'am. Yes,
So
ma'am.
now in that they have added water 200 ml and putting one magnetic bead. That white uh, is, is called magnetic bead. So if you keep the bead for the stirring, this is stirrer. So temperature at 100 degrees centigrade. She is controlling the speed of the stirrer. So this is magnetic stirrer. On magnetic stirrer, they are putting the beaker with a bead. That bead inside will stir. So now stirring is going on. You can see with the bead. So this is the process we are making green tea extract. So for 25 minutes they will continue like that at 100 degrees centigrade to get the tea extract. Then they are stopping the stirring and stopping the heat. They are taking away the beaker. Now they will filter it out. We will be utilizing the extract, water extract for the nanoparticle synthesis. Filtration using this filter paper. So they are filtering it into the flask, and that top one is called funnel. I think you must be knowing which goes here. So she has folded filter paper in proper way to do the filtration. See, this is the process of making the filter paper, folding, putting the filter paper, and now they will filter it out to get the green tea extract. Now she is filtering out. So filtration is started. You can see it's coming out. So make copper. So now we have taken 2 molar of copper nitrate and we are adding this copper nitrate 2 molar 0.2 molar solution into this green tea extract. See in the tube green tea extract is there. We are adding copper nitrate. See in the hand, right side is green tea extract and the left side is copper nanoparticles. You can see the color change. Why color change? Because copper nanoparticles are what is the now she's making uh, iron oxide nanoparticles. See the extract. She is adding ferric chloride solution in the green tea extract, and you can see the color. So now it is moved to black. Green color became black. So because of iron nanoparticles is formed, particles are formed, but color is changed. So what is the activity of here? Is it as reducing agent. So ferric chloride, ferric is converted in this ferric plus 3 is getting reduced on the nanoparticle. Yes. So here the green tea extract is working as a stepping agent. Means towards now first see the single nanoparticle, then I take. So they are adding the green tea extract one nitrate solution. So here silver nitrate will silver nitrate plus silver nanoparticle. So we are adding silver nitrate solution to the green tea extract. Right side is our green tea, and left side silver nanoparticles. See. You can see switch to black color, left side. So here, our what for we are using this thing because it is working as tapping agent as well as the reducing agent. First it is reducing. What is the tapping agent? Because once nanoparticle is formed, it is having a tendency to be agglomerated. Okay, it is not functionalized. It is a bare nanoparticles. So they are having tendency to again join together to come to the main starting material. Okay, please join together, make a ball. That's why to avoid that we need a tapping agent. So this plant extract is helping us for the tapping the nanoparticle number one, and for reducing the metal salts, whatever metal chlorides, metal oxides we have used. It is used as reducing agent as well as tapping agent to stabilize the nanoparticle. Now that we have shown synthesized from the using the plant extract. Now this is another iron. Can you hear the voice? Can you hear?
Yes, ma'am.
can see after 5 minutes iron nanoparticles form. So likewise it is very easy, but here we have to remember while nanoparticle synthesis, the particles after formation you have to stabilize it. There are many ways, I will come into it. So now coming to carbon-based nanomaterials, nowadays people are very much attracted for carbon-based nanomaterials because they are safe, low cost. Because when we are coming for daily use or technological importance, we see obviously that that system should be low cost. First priority will be that. Otherwise, that cannot be popularized. So carbon-based nanomaterials, different materials are there. You must have heard. sp bonded carbines, linear carbon chains are called one part, and similarly sp2 bonded are there, graphene, nanotubes, fullerenes, carbon onions, nanohorns, nanocones, so many things are there. See here 1D when nanotube, graphene 2D, fullerene 0D, diamond is 3D, graphite is also 3D when it is layer structure, and some amorphous, porous, disordered, activated carbon, carbon fibers, glassy carbon, carbon black. You must have seen carbon black means kajal. You have seen those things, kind of nanoparticles. So now graphene is very much popular nowadays because it is having some great properties of highly thermal and thermal conductivity and electrical conductivity, and it can be utilized for various applications. So graphene is a 2D layer of carbon allotrope from graphite with sp2 bonded carbon atom. Say this is graphite. Very easy, at home also you can do it. So one graphite you can take, and on that you can put a scotch bite, scotch tape. Scotch tape is there available, means some strong tape. You pack luggages and all, you put the tape on that and peel it out. Then some layer will come out. That is called graphene. So single or few layers of graphite. So it is called graphene. Okay. So actually it should be single layer, but single layer graphene formation is very tough. But 2-3 layers graphenes are also having very good electrical conductivity and thermal conductivity, and they are being utilized in many purposes. So graphene was first isolated in the lab. These two scientists, they got it first in the University of Manchester in 2004, and they got 2010, they got Nobel Prize for that. See, here I have shown graphite micro-mechanical cleavage. The cleavage I have told you using scotch tape. You are getting, see, layers are getting separated. We are getting graphene. So this is same like before. Other nanoparticles, graphene is also can be synthesized top-down and bottom-up procedure. So here how we generally make, because graphite we first oxidize it. So when we will oxidize, what will happen? It will happen OH or COH, means acidic or alcoholic group in the side. Now if we some hydrophilic solvent if we add, what will happen? Interaction between the layers will be, what we have to do? We have to, for separating the layers, something has to come out, insert in between the layers, then only layer will be separated. How it can be separated? When the interaction between two layers will be lesser than the interaction between a single layer and the material what we are adding, maybe solvent, maybe polymer or some other particle. So like that we call it exfoliation kind of thing. So what is happening? Their layers will be separated like that. That is called, from graphite we are separating the layer, that is called top-down approach. Similarly, we can do bottom-up approach. Here carbon nucleation we have started, and growth will be on metal foil, and finally we will get the graphene. But it is tougher. This process is easier, and most of the people we are using for the lab scale thing. So top-down maybe mechanical exfoliation, solution-based exfoliation, chemical oxidation. Exfoliation means these layers are separated. Graphite layers are separated. I will come. What is exfoliation? Exfoliation at present you should know the layers of graphite will be separated out fully. That is called exfoliation. So when it is separated out, we get single layer. That is called graphene. So chemical that can be done. Exfoliation can be done in very many ways. Mechanical I have shown with scotch tape. Solution exfoliation means with solvent we can do this exfoliation. By chemicals we can do this exfoliation. By electrochemically, by passing charge also we can do this layer separation. Similarly, from the bottom up approach we can do epitaxial growth, chemical vapor deposition, physical vapor deposition. So many are there. So now classification of graphene nanostructure. So graphene also can be chopped off. Graphene also can be broken. So graphene is two-dimensional. When it is broken, it can be zero-dimensional. This is called graphene quantum dot. It is having nice fluorescent property and some other very good properties. It is zero-dimensional and it is having quantum effect. So graphene quantum dot nowadays is used for photocatalysis, used for biological applications. It is showing good colors. So and similarly, from it can make carbon dots. Carbon dots, 60 types of carbon type of dots are there. From graphene we can make graphene quantum dot. From carbon material we can get carbon dots, zero-dimensional, and from polymers also. From polymers we can get the polymer dots. These are all zero-dimensional carbon dots. These are nowadays very much popular for various applications. So now 1 dot carbon nanotubes, if you fold the graphene 2D sheet, it will be carbon nanotube. You can see, you are just folded. So carbon nanotubes can be single wall, it can be double wall, 2 walls, it can be 3 walls, it can be multi-wall carbon nanotubes. Carbon nanotubes are also very much popular because of its conductivity for the battery and supercapacitor applications. So 3D graphene. 3D graphene, how we can make? Means you can take graphene oxide and you can hydrothermal reaction. What is hydrothermal? Means in a Teflon jar, we can take the material with solution and then under pressure we can apply heat. And then we can go for freeze drying and we can get 3D graphene based structure. Sometimes we are mixing 2D graphene with polymer. It can also give you 3D graphene based composite structure. So these are very popular specifically nowadays for biological applications. So now we have shown here from the natural resources we can make carbon dots from apple, from banana, from whatever, from leaves, anything. So from the source by heating we can get carbonization, we can get fluorescent carbon dots. And this is bioimaging, we can apply optoelectronic, we can apply biomedicine, we can apply biosensing also we can apply. So the same thing I have shown how fluorescent structures you can see. All are fluorescent. Means from the all materials, carbonization will give different colors. So what type of fluorescent you need, whatever range, you can take accordingly. You can change the reaction condition. You can change the starting material to get the material whatever you want. So this from the small molecules also. This I think you have understood. By the top down, by chopped layers thing, we are getting carbon nanodots, graphene nanodots, and here from bottom up approach we can start with polymer molecules, small molecules, then dehydration, assembly, further dehydration, depolymerization, we can get this kind of nanoparticles. So I am not going to details. Here also we have shown in the schematic diagram. So now this is our lab work. So simply here our specialization of this work was people are taking from single layer graphene, people are taking, and from that they are making graphene quantum dot. Do you remember what is graphene quantum dot? That just now I told. When we are chopping graphene, it is zero dimensional. From graphene, when you are chopping graphene into small particles at zero dimensional, it is called graphene quantum dot. So what we have done, directly we have started with graphite, layered graphite, not from the graphene. So multi-layered graphene we have made graphene quantum dot, and from this graphene quantum dot you can see the color. This is beauty. They can be used for photocatalysis and other application, and it is metal free. Metal free material. First of all, metal if you use, it is costly. Second thing is metal free materials you cannot use for biological applications and some other application. It will have some negative effect, side effect. But this is metal free graphene quantum dots are very safe. Similarly, from the carbon dot biomass, here see carbon dot how much good fluorescent it is showing. So here also we have seen, you must have seen on road that yellow colored flowers you get. That from the flowers and from the leaves, from the neem leaves, also we can make this carbon dot and see how good the color is. Some example of utility of our material I have shown. See, we have injected this inside this DU-145. Okay, this is prostate cancer cell. So it is showing anti-cancer effect. And so wonders you see, directly it can show anti-cancer effect in this prostate cancer and breast cancer we have observed. And this is see without our nanoparticle. And this is you see with our nanoparticle. Nice fluorescence it is showing. What will happen if it can be used as fluorescent tag? Say if you want to send some medicine to the cancer cell, how it will go? If you attach this drug molecule into our molecule, then wherever it will go, it will show the fluorescence. So you can see that where that drug molecule is going, whether the drug molecule is reaching to the particular place. Not only that, as the size of the molecule is small, it can go to brain also. I will show you. It can show brain also when there is some brain tumor for glioma, brain cancer. There also this kind of material can be used. And another point is we can target to the nowadays cancer therapy main problem is what? There is no targeting, means but now much improved than before, but still it needs to be improved. So normal cells also it kills because the drug cannot specify the particular cancer cell. So with the normal cells are also dying. So if we can trigger to the cancer cell line only, then only the treatment will be excessively good. So in our case, we can target specifically the cancer cell and we can follow its wherever it is going by the fluorescent tag. So in our material showed also it is fluorescent and it is showing anti-cancer activity also. Now it is GQD, means from graphene we have made this graphene quantum dots. You can see this is zebra fish. It has gone to brain. It is show. It is. Can you see? It is fluorescent, and it has gone inside the cell. So some material, our material, if it goes inside the cell, if you can make some nanomaterial, if it goes inside the brain and inside the cell, then you can send through it many drug molecule or other protein molecules, whatever you want. Not only that, its advantage is it is fluorescent. Sorry. Here you see another interesting application. We have done it in the fingerprint. So if you are putting your finger in the this is done with the zinc oxide. Here we have zinc oxide we have made from the natural leaf, and that zinc oxide is using in fingerprint determination. See, fluorescent image in latent fingerprint is developed by dusting ZA nanoparticles under illumination of fluorescent microscopy. We have kept under fluorescent microscopy, and you can see the this is grayscale image without zinc oxide, and it is with zinc oxide. After putting your finger in the zinc oxide dust, it will show your fingerprint, means person to person this fingerprint will be varying. So for determination of fingerprint, these nanoparticles, our nanoparticles can be used. So as I have discussed, nanotechnology in drugs provide new options for drug delivery and drug therapies, enabling drugs to be delivered to precisely the right location. This is more important. Drug can go anywhere, but it should not kill normal cells also. It should go to specific place in the body and release drug doses on predetermined schedule for optimal treatment. Attach the drug to a nano-sized carrier. So we can attach the nanoparticles can be used directly as for the treatment, or it can be used as nano-sized carrier. Means you can attach your drug in the nanoparticle and send the nanoparticle to the proper location. They become localized at the disease site, that is cancer tumor. Then they release medicine and kills the tumor. First they will carry the drug there, and there they will release the medicine. Means they should not release in between. You have to take care. You have to attach in such a way that in the cancer location only there should be in the chemical situation it should release the drug. We will make in such a way that drug will be released in the cancer position. That chemical condition will allow it to release the drug, not in other place. So current treatment is through radiotherapy or chemotherapy. Not only that, presently we are working on some project in that we are attaching it, say iodide or gallium. So we are attaching those radioactive material with our graphene quantum dots, and we are sending to the brain tumor, because brain tumor treating is very tough, because most of the materials cannot go, because material to go to the brain, it has to cross the blood-brain barrier. So our material is showing to cross the blood-brain barrier. So if we attach the radioactive material, just you have started the work, so with bark, Bombay. So if we attach the radioactive material in that, radioactive material, what they do, it can detect cancer when the concentration is very low also. And it can be used for, radioactive material can be used for detection as well as therapy also. First your job in cancer is, first you have to detect whether cancer is there or not. If you can detect when it is low percentage cancer, if you can detect is great. So that is our intention. We should detect, be able to detect is when small amount of cells are getting affected. And second thing is targeted treatment. So current treatment is through radiotherapy and chemotherapy. Chemotherapy means with drug and radiotherapy means with radioactive materials. So nano robots are also used. Nano robots means that nanoparticles which will act as a nano robots. The full thing, detection and therapy, all the things, it will be like working like robotic. In fabric, just now I have told you, we used in the nano-sized whiskers in the cloth. What will they? What it will do? It will water repellent, dust repellent. You can make the clothes water repellent, dust repellent, and we can make it bulletproof jackets. Okay, so making steel and dust resistant, antimicrobial, antibacterial fabrics also you can make. Nowadays, antimicrobial and antibacterial fabrics are very popular nowadays. So silver nanoparticles people are using because they are having antibacterial activity. And even if antimicrobial also they are having. So in mobile also we use nanotechnology. More for nanotechnology concept done by Nokia Research Center in University of Cambridge. Here morph is a super hydrophobic, making extremely dark repellent. In the mobile, it should, if it is, we can make extremely dark repellent, it is great, no? So this morph they have made in Nokia as well as University of Cambridge. It will be able to charge itself, means directly we will make it from solar light. It can be, we take the charge from the light sources. It will be able to charge itself from available light sources using photovoltaic nanowire glass covering its surface. Nanowire glass will go and that will be having photovoltaic effect. So from solar light it will absorb energy and we don't have to charge it separately. And nanoscale electronics are also allow the stretching, means you can fold it. It will not breakable. If you use polymeric type molecule, flexible material, it could be foldable. So that means it is a stable molecule. Simply it will not break. Then nanotechnology in electronics also, that nanowires, electrodes are also made from nanowires, graphene. And for the chips, we can for fabrication of chips, nanolithography can be used. Transistors are also used. See here I have shown the flexible plastic, e-paper, displays, sunglasses, car windows. Those can be made from the nanoparticle, from the nanotechnology. So from the for computers also nanotechnology is used. Carbon nanotubes are very popular. A carbon nanotube is a molecule in form of hollow cylinder with a diameter around a nanometer, which consists of pure carbon. Carbon rod is the upcoming technology in the displays technique also, due to less consumption of electricity and less heat emission. Size of the microprocessors are reduced to greater extent because of using nanoparticle. Previously microprocessors were very big. Microprocessor is big, means computer will be very big. Nowadays you can see the chips are getting so small because of this nanotechnology interference. Researchers at North Carolina State University says that arrays of magnetic nanoparticles called nanodots, nanodots all can be used. Now, as you see, that HP company, they have done memory device using nanowires coated with titanium dioxide nanoparticle. When one group of these nanowires is deposited parallel to another group, and then these perpendicular nanowires are laid over a group, that is called memristor is formed, and this memristor can be used for single component memory cell. Why now these things are becoming so lightweight? Because of these nanoparticles. So then this having high memory capacity as well as occupying the less space. And magnetic nanowires made of alloy of iron and nickel are being used for create dense memory devices. Magnetic nanoparticles are also used for dense memory devices. So chips produced by Intel before I series processors were between 65 nanometer to 45 nanometer. Later, with the help of nanotechnology, now 22 nanometer chips were made, which itself is a milestone. So faster and smaller advantages using carbon nanotube, it is becoming faster and smaller, can be used to produce smaller and faster components. This will also result in computer that consume less energy, and high speed and high capacity memory allows circuits to atomic level. Other uses, what are the uses? Silver nanoparticles, I told you, that can be used embedded in the bandages to kill bacteria, can be embedded in the cloths. Using nanoparticle and their composite, I will come later. We are using bone replacement. Then aerogels, lightest known solid due to good insulating property. Aerogels can be used as spacecraft because it is having insulating. Some gels, composite gels, also used using nanoparticles that can be used in aerospace. Why you use nanoparticle for energy storage, energy devices? Because of its efficiency, size, performance, lifespan, and it is easier. So now, as we told, that graphene is a very interesting material nowadays. We can use for stem cell therapy, we can use for supercapacitor, we can use for biosensor, we can use for solar cell, we can use for organ transplant, we can use for cancer therapy, so many applications. We said graphene, from graphite mostly, graphene is said that, I don't know you understood or not, graphite is like that. We have to do oxidation. Why we need oxidation? Oxidation will give all functionalization here, OH, COH, OH, COH. Now when exfoliation means another material, say water is coming, what will happen? Because of this functional group OH and COH, that I think you must be knowing hydrophilic, hydrophobic. So when it is coming, this hydrophilic group will have interaction with water. Then what will happen? Water will go in between the layers. It can come in between the layers. Water will come in between the layers because of this functional group. Then what will happen? These layers will be separated out. These layers will be separated out. In place of water, you can add polymers, you can add other molecules. So by that we do the layer separation. This is called exfoliation, and then we are getting single layer graphene oxide. Then further by reduction, we are getting single layer graphene. Graphene oxide is having inferior electrical properties than graphene. So from graphene oxide, we are reducing to make, because already OH and CO oxidized, we have done oxidation, no? So now we have to reduce it to get graphene, single layer. So now the 3D graphene we have spoken. This 3D graphene, you see, interesting. This 3D graphene can be used as scaffold. What is scaffold? Say for spine injury nowadays, you must have heard that old people or some accident that your spine cartilage is damaged. What we do? We can inject this nanoparticle gel there. Their new cell will be grown, and like that you see. But with this nowadays, to get the proper structure, 3D printing has come to get the proper structure, and like that we can this is scaffold. From this organ transplantation, another specific organs are developed, and then it can be implanted in the patient. So interdisciplinary technology. Nowadays in research there is nothing like chemistry, physics, biology. So it is interdisciplinary technology. Say any drug molecule you are inventing. So you have to invent drug and then you have to know the means you have to go to biology and you have to see how it is going. Of course, for the measurement and the property determination, of course you should be good physicist and mathematician also, and engineering background also. So nowadays all group of scientists are working together to come out with a good product. Now, challenges in nanotechnology. What are the challenges? For the fabrication and processing of nanomaterials and nanostructures, the following challenges must be made. What? Overcome the huge surface energy as a result of enormous surface area or large surface to volume ratio. Means we should be able to control. Not just like that, we are making nanoparticles, we don't know how to control. No, we have to control that. And next, ensure all nanomaterials with desired size, uniform size distribution, morphology, crystallinity, chemical composition, microstructure that all together result in desired physical properties. So what property I want? Say for particular application, say I want for cancer therapy. So I should know it should have good fluorescent property, it should have small size, what size I need, and it should not be toxic. How to control the toxicity, everything according to that. Whatever purpose I am using, according to that I have to make the nanoparticle and I have to control its property. Then prevent nanomaterials and nanostructure from concerning through either oswald ripening or agglomeration. We have to, just now I have shown in our video that we have to stop agglomeration. You can make nanoparticle and another, after making nanoparticle, your great challenge is you have to stop the agglomeration. If it is agglomerated, then you will not get the benefit of nano size. And another thing is morphology control. Whatever morphology, do you need particle? Do you need nano ribbon? Do you need hollow sphere? Do you need tube? So depending on your synthetic procedure, you will get different morphology that you should be able to control. Means if I give this condition, reaction condition, only this morphology should come, others should not come. When we are going for large scale production or something, if there is a mixture, it will be now not useful, no? So now to control this, our functionalization of nanoparticles is coming into the picture. So control of the dispersion of nanoparticles in different matrices and the interaction between the nanoparticles and other molecules, it is necessary to explore their full potential for biomedical, nanocomposite, sensing, imaging, energy, electronic and other applications. This can be achieved by proper surface functionalization and modification of the nanoparticles which enhance their interaction with surrounding environment. Just now I have shown you, graphite, it is layered, cannot be separated. But that's why what we have done oxidation. When we have done oxidation, functional groups are there. So to send nanoparticles somewhere or to attach something, we need to do functionalization of the nanoparticle. By functionalization, we can control the efficiency property of the nanoparticle. Not only that, say I am having some dispersion of nanoparticle in water, but I need dispersion in some other solvent. So what I have to do? I have to do the functionalization such that it can be dispersed in the organic solvent. Okay, so like that. So for functionalization of nanoparticles consequently influences the colloidal stability, dispersion and control assembly of nanoparticles. Surface modification can also provide selectivity or specific recognition and biosensing and targeted delivery in biomedicine. By tailoring the surface of nanoparticles properties such as hydrophobicity, hydrophilicity, conductivity, corrosivity can readily be introduced by adjusting the surface environment. Various development of synthesis strategies for functionalization of nanoparticles. How we can do functionalization? The use of chemisolution. Thiol groups can be attached, hydroxy group can be attached, and also physical absorption also possible. Then electrostatic interaction, negatively charged nanoparticles can attract positively charged small molecules, vice versa. If your nanoparticle is positively charged, you can attract by negatively charged by charge. Covalent interaction using by conjugation chemistry by exploiting functional group, both nanoparticles and different molecules. Non-covalent supramolecular affinity based on receptor ligand system. We can attach some ligand. Just now I told drug molecule. Weak interaction, we can utilize some weak interaction also, and mainly surface surface engineering. Surface of the nanoparticle we can engineer by attaching different material. You can see types of modification can be done. First of all, what property we have to monitor: morphology, chemical composition, crystallinity, solubility, surface charge. This has to be controlled. Types of modification, how physical can be done, and you can do by charges, and we can do inorganic molecule you can attach, organic molecule can be attached, biomolecules can be attached. So here adjustment of roughness and topology. Surface charge you can do, surface energy you can modify. See, reactivity, catalytic activity also you can modify. Biocompatibility or bioactivity you can modify by functionalization. So now I am coming to composite. Why composite? Just now we told that simple nanoparticles sometimes cannot serve the purpose. That's why composite material is coming into the picture. What is composite? It is a material system composed of two or more physically distinct phases whose combination produces aggregate properties that are different from those of the constituent material. Generally, one material forms a continuous matrix and another provides a reinforcement. Okay. So here you can see epoxy polymer is there and glass fiber is embedded in the epoxy. Here graphite is embedded. See, this is graphite in the resin. Graphite is introduced in the resin. So like this, if we mix two materials, what will happen in the composite? We will get the benefit of the two materials in the properties. Applications, you can see automatic parts, sinks, bathtubs, hot tubs. Even if nowadays you are using specs, that we are nowadays not using glass, we are using plastics. There's plastics and not simple plastics, all are composites. Composites will have more strength, more stability, different properties. Say nowadays we use, I don't know, photosensitive sunglasses you are seeing. When you are going in sunlight, it is becoming black. So in the plastic, we are dispersing nanoparticles to make it like that, which is responsive to the solar light. Okay. So golf fishing poles, hockey sticks, everywhere, even if our car body, flight body, tractor, cycle, everywhere composites are used. Composites are all around us. See, different part is using this thing you can see, and this rackets, these cylinders, why not? These boats everywhere. So engineering application, aerospace, automobile, pressure vessels, pipes. Pressure vessels, pipes means it is why some places if you add metal, it will be very heavy. Not only that, it is corrosive. So why you use metal, and it is costly also. So nowadays polymer composites, it will be heavy strength, it will be lightweight, and it will be long lasting also. See, turret end, industrial spring, medical table also, these are, whoever has gone through MRI and all, you must have seen, all are made with plastic. So traditional composites, wood is composite, concrete is composite. Concrete is nothing but cement and sand composite. Asphalt is composite. These are synthetic composite I have shown. A is plywood, is a laminar composite of layers of wood varner. See, layers of wood varner is there. And then fiberglass is a fiber reinforced composite containing stiff, strong glass fibers in a softer polymer matrix. And then see, concrete is a particular composite made with cement and sand. You know, concrete made house is much more stronger than simple brick. So why composites are important? Composites can be very strong, stiff, weight, very lightweight. So ratios of strength to weight and stiffness to weight are several times better than steel or aluminium. It is having more strength, but it is having less weight. Fatigue properties are generally better than for common engineering metals. Toughness is often better too. Composites can be designed that do not corrode like steel. Just now I told you, it will not be corroded like metal. Possible to achieve. Metal is having high strength, but metal is costly. Can be corroded. If it is if our atmosphere is humidity is more, then it will be in eastern side, Calcutta and all. You cannot use iron things because it will be corroded after some time. So that's why in that case composites will be useful. Limitations. It is also having some limitations. Properties of many important composites are anisotropic. The properties differ depending on the direction in which they are measured. This may be an advantage or disadvantage. We sometimes say, for example, if you are using fibers and tubes, that in which way it is placed, it is very tough to make the fibers in one direction. You can understand 3 fibers, 1 nanometers, 2 nanometer size, and in the polymer is so thick material. In that making it in proper direction, arranging in proper direction is really tough. Sometimes it is an advantage, sometimes it can be a disadvantage also. Many polymer-based composites are subject to attack by chemicals or solvent, such as polymers themselves are susceptible to attack. Sometimes whatever polymers we are using for making composites, they are affected by chemicals. See, where we are using there, we have to see those chemicals should not be there. Then only it can be used. Then composite materials are generally expensive because two material cost is there, but not of course more than the metals. Manufacturing methods for shaping the composite materials are often slow and costly. So now I told you there is mainly two things should be there. One is matrix, another is particles. So matrix can be different: metal matrix, ceramics matrix, polymer matrix, organic matrix. Different can be there. So what that matrix does? It can protect the nanomaterials inside it from the environment, transfer the stresses to phases, holds the embedded phase in place, usually enclosing and often counseling it. When load is applied, the matrix share the load with the secondary phase. In some cases, deforming so that the stress is essentially borne by the reinforcing agent. You can see the car body is nowadays all composite materials. So all the stress, the matrix outside it, the polymer, whatever, or ceramic, or whatever matrix is there, that can share, that can take the load, such that nanoparticles inside the embedded particles should not be affected. So composite can be different type. Particle reinforced, if in the matrix particles are there, that is called particle reinforced. If fibers are distributed, called fiber reinforced. Another is structural. So particle can be large particle or can be dispersed. Fiber also can be continuous, can be discontinuous. Structural can be laminate or sandwich. Discontinuous also aligned or randomly aligned, as I was telling you. Here I will not show because time is not there that much. So the laminates I want to show. This sandwich panel is very important. See, this honeycomb structure is in between. Honeycomb core in between two facing sets. This is having so much strength, you know. If 10 elephants stand on that, no, it will not break. So nowadays for the flight and all, this kind of structures people are preferring. It can take high load, this kind of structures. In between, this structure is honeycomb structure. And top, it is phase sheet, adhesive layer. In between adhesive layer, this is polymer sheet, and this is honeycomb structure. Nanocomposite. If the filler material, if the particle inside material is nano size, then it is called nanocomposite. Till now, I was talking about composite. Now, composite, if in the composite material, at least one material is in nano size, then it is called nanocomposite. So applications as electrocatalyst, lightweight materials for less fuel composition, artificial joints economically beneficial. Nowadays, who is having knee injury? Previously, people used to use metal-based materials. Okay. Nowadays, people are using. If at your home, your grandmother, grandfather, if anybody is going for surgery, you inquire with the doctor. They can tell you. Nowadays, nobody is using these amalgams. Nowadays, they are using artificial joints. They are using polymer composites. Very rarely they use nowadays metal-based material, because metal-based materials longevity is very less. Then carbon nanotubes, most widely speaking nanomaterials, which can be made as nanocomposite fibers. In place of fibers, directly carbon nanofiber we can use. And aberration and wear applications, marine application for marine, where all the time you are in water. There it is very useful. Metal is previous days, you remember, we used to ship and all, we used to make with metal. Nowadays, no. So what are the various applications? Food packaging, fuel tanks, films, environmental protection, flammability reaction, erosion, corrosion applications we can use nanocomposite. So now preparing composite. So what we do? You take polymer, or just now I have explained, this is layered clay or layered graphite. Here we are adding polymer. This is exfoliated. When layers are completely separated by other material, it is called exfoliated nanocomposite. And when the layers distance is little bit increased, first when the material is going in between the layers the separation will be less, and then further more and more polymer will come, then layers will be completely separated, then you will get exfoliated nanocomposite. For any application, exfoliated nanocomposite is preferred because it gives the maximum enhancement of the properties when layers are completely separated. Here car body we have shown the graphene polymer nanocomposite in the car body, car charging also see. But the nowadays, petrol car, people are don't want petrol car because of pollution. Nowadays, battery operated cars are coming. Graphene based materials are used for supercapacitor or in the car battery. So in our lab, we have made some supercapacitor applications, some graphene based composites we have made. Here we have got some capacitance value 416 Faradays per gram, and with number of cycles 10,000 up to 10,000 we have done. It is showing very good stability of the material. So when if you add some other material in the graphene, nitrogen, sulfur, you can dope in the graphene. Then another property enhancement is there. We have doped graphene with nitrogen, and we have seen that it is giving better supercapacitor activity. It can give better efficiency. So here applications of graphene and polymers for the electronic device, for the application in conducting films, application in solar cells. We are having a couple of applications in this, and this is used for cancer therapy. Just now I have spoken to you that we are working on some project graphene quantum dot based materials for treating brain tumor. So very much popular nowadays. So many research work, many research activities are going on in the various labs. So characterization, how we characterize these materials. Microscopy is very important. Scanning electron microscopy, different microscopies are there. Scanning electron microscopy, transmission electron microscopy, scanning tunneling microscopy are there. The picture of the scanning electron microscope. Here what we will get in this microscopy, here we can see the texture and surface of the sample, size, shape and order of the particles. We can see elemental composition of the sample. We can see arrangement present within the sample. Because if we want to tailor the material, I have to see by after my synthesis what is going on. So we use different kinds of microscopies to see what is going on. So these are the things we can get from scanning electron microscopy. When the beam of electrons here, this is the sample, you see, this is the sample here from electron beam is coming. When the beam of electrons strikes the surface of the specimen and interacts the atoms of the sample, signals in the form of secondary electrons, then it will come out as secondary electrons, backscattered electrons, some will be scattered and then come. And then characteristics X-rays are generated that contain information about the sample surface, topography, composition, etc. Here two things it is important. Here you will get the topography, morphology and composition, crystalline structure. Main principle is by electron beam, electron gun you are getting, and here sample has to be conductive. If sample is not conductive, one conducting layer you have to use for the scanning electron microscopy. These are the principles. How is this picture? Here crystalline lattice particle, polymer how it looks, wood fiber how it looks. This is our lymphocyte. This is our blood cells, how it is looking under microscope, scanning electron microscope. So it is having advantage. Bulk samples can be observed and larger sample area can be viewed. Here we can see larger sample area. It can generate photo-like images. Very high resolution images are possible. Scanning electron microscopy can yield valuable information regarding the purity as well as degree of aggregation. Why? Just now they told, in the previous slide we have shown that it can show the composition type. So you can see if any agglomeration is happening or impure material is there, Disadvantage, sample must have surface electrical conductivity. This is the disadvantage. If you want to see the material which is not having electrical conductivity, then sometimes you have to use a conductive material coated layer. Then what to do? Non-conductive samples need to be coated with a conductive layer. This is extra work. This is the problem. If your material is non-conductive, you have to use a conductive layer. And then it is time consuming and of course expensive. Instrument is very expensive. Sometimes it is not possible to clearly differentiate nanoparticle from the substrate, because substrate and nanoparticle, on what substrate you have taken, sometimes you cannot see the substrate, and SEM cannot resolve the internal structure of these domains. Internal structure you cannot see. Another microscopy is there, that is called transmission electron microscopy. Here we can see shape, size, order of particle sample, crystalline structure we can see, composition also, elemental composition of the sample we can see. Here how it see 10, and another high resolution 10 is also there. Here you see standard same interlayer, silicon and copper oxide interlayer is looking like that in 10. When it is high resolution, better 10 we are going, you can see that is how it is showing interlayer. So that's why microscopy gives us very good inputs for our research. Advantages, additional analysis techniques like X-ray spectrometry are possible, high resolution is possible, image construction possible but aberrant. Changes in the nanoparticle structure as a result of interaction with gas, liquid, solid phase substrate can also be monitored. And disadvantage is what? Sample preparation is necessary, mostly use 2D images. It is also time consuming, and sample must be used to withstand the electron beam, also high vacuum chamber. It is done in high vacuum chamber, so sample should withstand. Now why we need SEM and why we need TEM? SEM is high resolution of bulk specimens. So no need to make very thin sample. If sample is 20 to 50 angstrom, most commercial instruments less than 10 angstrom for research instrument. Research instrument, it is less than 10 angstrom we make the sample, and here in 10 high resolution of thin samples. Here 1.2 to 1.5 angstrom should be there. Here 3D appearance of the specimen image as a result of the large depth of the field. Depth of the focus you can see. Here no 3D appearance of the specimen image. Here we cannot see, in TEM we cannot see 3D appearance. Here we can see. Here we can see big. Here we can see very minute thing, 1.2 to 1.5 angstrom. Capable of very low magnifications, complementing the information available from optical image. It is kind of optical image. Optical image, whatever we are not getting, we will get better, we will get in SEM. And here technique that provide crystallographic structural information, lattice arrangement, orientation, relationships, dislocations, everything we can get. Another spectroscopy, what we can do, X-ray diffraction, small angle scattering, X-ray photoelectron spectroscopy, UV visible spectroscopy, FTIR spectroscopy. These are also gives us information. X-ray diffraction, I am not going to slides again because it will be too much for you. XRD means crystallographic structure we can get. X-ray diffraction, small angle X-ray scattering also it can give if any material is there in say some metal oxide is there, means how it is distributed, the X-ray scattering result it can give. Then XPS will give us the surface property, means say there is some bonding from sp2 to it will go sp3, then bonding energy will be different. So that can be done from XPS. UV spectroscopy also can give us the information about absorption and emission spectroscopy we can get, and then FTIR will give us information about our functional group. In our lab, this is the UV spectrometer. Here we need to use a sample. Our sample as well as sample is done with a reference sample. So one reference solvent we have used, and along with that we can use our sample. Sample will be kept here, and we can start running the thing, and here we can the picture will be like that. We will get a spectra like that print. So now another characterization in thermal analysis means when you are making some material, we have to see whether it is thermally stable or not. So thermal stability we can do by thermogravimetric analysis. What will happen if you heat the material? There will be weight loss. Say from 1 to 50 some weight loss, 50 to 100 some weight loss. From the weight loss at different temperature, we can predict about the composition of the material. And what is differential scanning thermometry? Basically, it is used for polymers. Polymers were glassy to rubbery-like. So that is called glass transition temperature. So for specific, it is very specific for polymer. Any polymer is having specific glass transition temperature. So for the composite, what kind of polymer is there? To know, we need to determine the TG, and for that differential scaling thermometry is required. So what are the possibilities in future? Nanotechnology may make it possible to manufacture to lighter, stronger and programmable material that can require less energy to produce than conventional material, and that promise better fuel efficiency, land transportation, ships, aircrafts and space vehicles. The future of nanotechnology could very well include the use of nanorobotics. These nanorobotics have the potential to take on human tasks as well as tasks that humans could never complete. The rebuilding of the duplicate ozone layer could potentially be able to be performed. If you are having any question, now you can ask me.
Hello, ma'am. Good afternoon, madam.
Good afternoon.
I am Basavaraj from JNU, madam.
Please introduce yourself. I'm not able
My
to
question
hear.
is this.
Okay.
I am Basavaraj from JNU Bijapur, ma'am.
Okay, tell me.
Yes, ma'am. My question or doubt is these nanoparticles, nanorobots, and these nano sensors, are they exist in our present day dates, ma'am, or they are hypothetical in present day, ma'am?
No, nano, yes, there exists, but nano robotics, yes. If you are you see Discovery Channel, National Geography, those things, please, my suggestion is sometimes you see those channels. Whatever research is going on, you can see. Of course, nanorobotics, too much research is going on. Nothing is just imagination. Of course, you can take
Yes, ma'am. It is going
nanorobotics.
on.
It is not commercialized. That is true.
Okay, ma'am. Yes, ma'am.
But sensors and all are there. Cancer therapies, it is there.
Ma'am, my doubt is in future nanotechnology is harmful to us.
Please repeat the question first. Introduce yourself. May I know who are you? Shall I remove this slide?
I'm Jashvita from JNV Prakasham 2, madam.
Yeah, tell me.
My doubt is if in future nanotechnology is harmful to us.
Nanotechnology harming?
Harmful to us.
No, of course not. For example, I will tell you. Say, I have shown you, know, our material is it can be used for anti-cancer activity. I told you, right? There, what is happening, you know, you have to see how much concentration you are using. Okay, up to some concentration, it is perfectly safe. You have to see that within that concentration, is your material is effective for cancer therapy? Of course, anything more is poisonous. Everybody knows that.
Nanoparticles.
Any question? Who is that?
Ma'am.
Yes, tell me.
Ma'am, what are the advantages of merging carbon nanoparticles in cancer treatment?
Advantage I told you, no. Previously, you see the metal-based nanoparticles. If you, I don't know, you have gone through it on a cis-platin kind of. Specifically for cancer therapy, you cannot imagine how much improvement is going on. Because previously, all metal-based materials they used to use. I will give you one example for me. I had some accident time and my neck joint there was some problem. Okay, what they have done, you know, the cartilage was gone bad, so they have put on carbon fiber. What they have done, you know, spinal cord. Our spinal cord is made with many nerves. So what they have done, because my cartilage is spoiled, they have done some operation surgery. In that, what they have done, they have pushed all the nerves through the carbon fiber, and then they have placed in my neck. So 2016 my operation is done. Till now no problem, and it won't be there any problem because carbon won't be affected. Previously people used to use metal based materials. Metal based materials, after some days it will be corroded and pain will be started and it will be affected, that will be spoiled. You must have heard in olden days, but you are too young. In our young age time, people used to use in metal rods. If somebody's leg is spoiled or neck is spoiled, people used to use some metal based material, and you have to remove. They used to tell after few years you have to remove, otherwise it will have some side effect. You have to change. Nowadays that is gone. Means I am sitting in front of you. As you are telling, no, it is there is some practical example, and that's why I told this story.
Ma'am, why the carbon is taken as a source for the nanomaterials, not other metals or non-metals?
All are used. Who told you? I told you example of titanium dioxide. I gave you example of gold nanoparticles. Many gold-based drugs are used for rheumatoid arthritis, for cancer therapy. Do you know? Specifically for arthritis in Ayurvedic, people are using gold nanoparticle-based medicines. All are used, but carbon-based materials are very cheap, and abundance of carbon materials in this world, right? Everywhere carbon, carbon, carbon.
They are available easily.
But gold, silver, they are limited, right? They are costly. That's why people are trying to make more and more carbon-based materials effective for the usage, replacing those metal-based materials. Even if for the battery, people have used platinum-based, this costly ruthenium-based, this kind of things for the solar cell and all. But all these materials are not existing in this earth. No, means unlimited, not unlimited. They are not unlimited, but carbon is unlimited. That's why they are trying to replace, if it is possible, everywhere. But of course, some places carbon is showing inferior results than metal nanoparticles. In that places, still we are using the metal nanoparticles, and we are doing research whether carbon can be metal can be replaced by the carbons. Okay, but still in many places, many places, metal nanoparticles are utilized.
Why not?
Good morning. Anybody? Question?
Ma'am,
Yeah.
what is the biggest problem of graphene, ma'am?
You tell me. I discussed in the presentation. Do you remember? Who are you? Where from you are?
It doesn't have any band gap, no?
What?
Good afternoon, madam. I'm Harish
Yeah.
from class 12.
Yeah. Tell me.
At the start of the session, you talked about something about agglomerization, no, madam?
Yes.
Can you please tell me again, madam? I could not able to understand it at that time.
Agglomeration means once you make the nanoparticles, they are having a tendency to joining with each other.
Okay.
That is called agglomeration. Agglomeration means again they will be joining with each other and making aggregates. Got it?
Okay,
So
ma'am.
we have to stop them for aggregation. For that only what we will do, just like that I have shown you that tea extract. Okay, this
Yes,
is
ma'am.
made of various biopolymers and all, no? That tea extract.
Yes,
Okay, so what they will do?
okay, ma'am.
They will be functionalized. I talked about functionalization. So whenever that
Yes, ma'am.
say copper nanoparticle, as soon as it is, first of all, it is reduced the copper. Okay, number one. Then as soon as copper nanoparticle is formed, it is having interaction with the copper nanoparticles, and it is surrounding, the polymers are surrounding the copper nanoparticles, and it is getting stabilized. So it cannot come across with another copper nanoparticle and agglomerate. That is called stabilization. So, yes. So if you are covered, say if you are entering some place Just to, you are, when they are having, they cannot come closer with each other, then they can agglomerate, no? Because they are surrounded by the polymers, biopolymers from the plant texture. Is it clear?
Okay, thank you, ma'am.
Ma'am,
Yes, ma'am.
Yeah.
ma'am, what are the uses of latent fingerprinting?
What? This is not DNA fingerprinting, this is simple fingerprinting.
Yes, ma'am.
You understood? This is not DNA. This is simple. If you put your hand, okay, if you put your hand there, your finger there in the nanoparticle bed, and then you can fluorescence. If you can pass the light, fluorescence light, and there you can see your fingerprint. You put your hand, you put your finger and take out. Then put it under fluorescence light. You can see the image of your fingerprint. Your fingerprint will be different than my fingerprint. From that, we can determine who is the culprit.
Ma'am,
Yeah.
ma'am, does forces like gravity have effect on nanoparticles?
Gravity means I did not answer. Means understand your question.
That means
You
if
say this
are
agglomeration and all these things are affecting gravity.
no, I mean, does nanoparticles are affected by gravity? Means does it have any effect on it? Nanoparticles.
No, ma'am. I think they are very small size. 10 raised to minus 9 meter, ma'am. They are negligible, ma'am. So I think they are not
That's why.
affected,
That's
ma'am.
why. Yes. Yeah.
అంటే అవి 2 టైప్స్ ఉంటాయి అని మెథడ్. డైరెక్ట్ వాళ్ళు అంటే మైకాన్ తీసి ma'am.
Yeah. Tell me.
Sir, ma'am, what do you mean by
slide? It is okay, no? Because I cannot see your face. I have removed slides. Anybody needs slide to see? Want to see the slides again? Because I
You guys
cannot.
have doubt? Students, may I interrupt, please? Because we have already taken 1 hour, 1.5 hour ma'am's time. So, if you have any doubts, you can ask ma'am on her mail ID. Ma'am, can we share your mail ID, ma'am?
Yes. Mail
Okay.
ID. Phone is a little because sometimes I am busy. I cannot attend the phone. You give my mail ID.
Yeah, sure, ma'am. Sure.
I will answer you.
Sure, ma'am. So if they have any doubt, they will contact you or via mail, ma'am.
Yeah.
And,
Surely.
Okay. Okay. Thank you so much, Sutapa Ghosh, ma'am, for this interactive session, ma'am. And definitely the students will benefit. Yes, it was an interactive one, ma'am. Thank you so much, ma'am. Hello, students. You want to say something to ma'am? At least say thanks.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
And we are so lucky to have a lecture from you, ma'am.
I want to give some information. Whoever is there
Hello,
in
ma'am.
12th class, CSIR is conducting, I think I forgot the name. There is one exam that is, I forgot, All India exam. This year it is done. You please go to the CSIR site. You can see if anyone of you wants to opt for the research area, general line, they can sit for the exam. If you can qualify from your graduation to up to your PhD, CSIR will give you fellowship. Okay, little tough exam. You should be well prepared and give you fellowship. Not only that, after your PhD, there will be a chance to get absorbed if you are doing well. But not sure. But up to PhD, fellowship is sure.
Thank you so much for sharing this information, ma'am. The students will definitely try, ma'am. We will convey this to the students.
Me and there.
Yeah, sure, ma'am. Sure, ma'am. We will go through CSIR.
CSIR HRTG, they can see and they can
Okay.
get the information. This year exam is over. Next year they
Okay.
can apply.
Sure, ma'am. Sure. Ma'am. Thank you so much, ma'am. Thank you once again, ma'am.
Thank you.
So, students, we have our valediction at 4:30. So, till that time, we have 15 minutes. So, two students, they have requested us
Ma'am, shall I, ma'am?
to show their presentations. So, first I'm asking
Ma'am,
from
I want to
Prakasham.
show my
So, are
presentation,
you
ma'am.
there? Okay, I'll
Ma'am,
give
I
you a
am also
chance.
want to
See,
present, ma'am.
okay, Basavaraj,
Ma'am,
you
all
are
my
right.
presentation is also ready, ma'am.
Basavaraj, you are from which school? JNV Bijapur, right? Okay.
Ma'am, I am giving them.
Yes, ma'am. Thank you so much, ma'am. Yes, ma'am.
Okay,
Thank you,
ma'am.
ma'am. Bye, ma'am. Bye, ma'am. Yeah, Basavaraj, is Madhusudan is there? Are you there, Madhusudan?
Madam, only 10 minutes are there. In 10 minutes,
10
everything
minutes.
should be completed.
Yes, ma'am. Yes, sir.
Ma'am, can I,
Okay,
ma'am, show
Basavaraj,
some my presentation?
yes, Basavaraj, you can present. Just take your time. Use it very cautiously. Okay, don't kill the time.
Yes.
We have very limited time. We'll give you 3 to 4 minutes only. Okay, present.
Please, you have a muted, ma'am.
Present बना दीजिए Mr. Basavaraj. 1 minute. Basavaraj from JNV Bijapur. ये बच्चा जो है ना Yes, you are a presenter now, Basavaraj.
Yes, ma'am. Can I?
Yes, please.
Yes, ma'am. Yes, ma'am. Where my voice, ma'am? Hello, madam.
Your voice is breaking. Your voice is breaking, Basavaraj. Yes, what were you saying?
Okay, ma'am. Ma'am, can you hear my voice, ma'am?
Yes, we can hear it. Please continue.
Yes, ma'am. I will start now. Good afternoon to everyone. I am Basaraj from class 11, Jawahar Navodaya Vidyalaya, Bijapur. I would like to introduce myself and I would like to continue my topic. I selected nanotechnology as my topic and I would like to start. With your permission, can I start my PPT presentation, ma'am?
Yes. Please.
Yes, ma'am. Introduction. What is nanotechnology? Nanotechnology is the study and manipulation of matter at incredibly small sizes. Their sizes may be around 1 to 100 nanometers. Means a nanometer contains 10 raised to minus 9 meters. You just think if our head is, to put this in perspective, a piece of paper is about 1 lakh nanometers thick. And nanotechnology encompasses very broad range of materials, manufacturing processes and technologies that are used to create enhance many products people use every day. This nanotechnology is having very important role to play in modern day medicine. As nanotechnology is revolutionary technology, and you can to show off the size of a nanotechnology nano particles. You just think when the ball is compared to a earth, how much small the ball is when compared to earth, that much small the nanoparticle compared to ball. And nanotechnology, a new frontier in modern day medicine. We can apply this nanotechnology in modern day medicine to improve our efficiency, and we can treat the diseases in more effective way. American Society of Mechanical Engineers said that nanotechnology will leave virtually no aspect of life untouched and is accepted to be widespread by 2028. It means that the nanotechnology will not leave any aspect of life. It will touch everyone. No, before starting, I would like to introduce a brief history of nanotechnology. Richard Feynman. His wonderful statement is there is plenty of room at the bottom. This is the statement of Richard Feynman, and he said that nanotechnology are the study and application of extremely small things. They are around 1 to 100 nanometers thick. These can be applied in physics, maths, material science, automobiles, etc. And I would like to start nanotechnology in medicine. Have you heard about a nano car? It is a very small car and it is having many applications. It is used by many peoples and it is available cheaply to all the peoples. And the same way we have our nanotechnology. It is also small and very good, and it is having more effective way to treat these diseases. Nanotechnology has many applications in many fields. It has its applications in electronics, medicine. One such application of nanotechnology is in medicine. Nanotechnology has very important role to play in this field of medicine. It, our our biological or medicine research community of the world is focusing mainly how they can make the drugs more cheaper, more effective, and how they can reduce the side effects from these drugs. How, and also they are trying to do how they can treat the diseases like cancer in a more effective way. And nanotechnology is used developing new tools and new devices which can be reduced the pain and bleeding which is seen during the and they are trying to reduce this pain and bleeding during this. Tissue engineering, nano tissue engineering, it means these carbon nanotubes, as already madam told, carbon nanotubes which can penetrate the cell membrane of a human body like conventional injection needles does. We have all gone to a doctor and you have checked the conventional injections, they penetrate our skin. As like that only carbon nanotubes can penetrate our cell membrane. They can reach to our affected cells and they will deliver the drugs in small amounts, and the specific they will deliver this drugs only to the specific
Baswaraj, you have
damaged
taken
cells
more than 5 minutes.
using
It is 7 minutes now.
Suraj, please wind up yourself.
using yes ma'am, using scientists is a more effective way and also prevent from side effects and is generally observed in large drug dose supply. Taking large dose can harm so that's the damage cell. This is its apex cells. Without CNC, we may find many effects from these medicines. And the last topic is the targeted drug delivery. We can deliver the drugs to a certain point where these affected cells are there. And I would like to say that it is very important to use nanotechnology in the targeted drug delivery.
Okay, thank you so much.
These can penetrate our skins. And nanotechnology in chemotherapy, you as already told, this can be used in treating cancer in a more effective way. Nanotechnology in diabetes, you can also control the heart attack from this using nanoparticles and nanotubes. Nanosensing, these nanosens can help in mapping a DNA of newborn babies, which will help in prediction of diseases and their early treatment. We can treat the disease at very early stage. You can see figures by 2030, the number of deaths expected to be reached 23 million.
Please
So we
wind
are
up.
seeing the plaque, which, okay ma'am, only last slide ma'am.
Time is up, please.
You can see the
Stop.
yellow color plaque which blocked the artery.
Next,
Yes,
Kirtana, are you ready? Kirtana or the guy Madhusudan, are you ready?
I would conclude that nanotechnology will sustainably change the manufacturing process of every product in existence. Whatever happens, it is. I think it is likely to be a human race greatest scientific achievement to date and will be probably change all of our lives. At last, I would like to thank my teachers, my principal of my JNV, who helped me for doing this activity. And I also thank the officials who helped me for participating in this regional science congress.
Thank you, brother. Thank you so much, Mr. Raj. Sir, next presenter बना दीजिए वो बच्चा कौन है? Madhusudan, are you there? He's not there. Kirtana, are you ready with your presentation? Kirtana from JNV Wayanad.
Yes, ma'am.
Yeah, can you present? Sir, Kirtana को बना दीजिए. Madhusudan is not present, I think. Kirtana from JNV Wayanad.
Madam, this is the last presentation.
Yes, yes, this will be last presentation.
I guess 4:20.
Yes, sir. Kirtana Shiva, yes, sir. So she's the last presenter now. You are a presenter now, Kirtana.
Okay, ma'am. Thank you. Ma'am, is my screen visible?
It's visible. It's visible.
Okay. Good evening to everyone, respected dignitaries and my dear friends. Today, I'm very privileged to express my idea on implementing cloud computing in education system for many benefits, which leads to many benefits in children, especially of rural area. So I'm going in very brief. So considering the time limit, so this comes under the topic education through innovation. And let me introduce what cloud computing basically is. Cloud computing means it is an interconnected system of servers, databases, hardware, software, etc. It consists of a main server which can be used on demand by people. And as long as you have access to internet, you can provide and receive service through internet. So there are numerous advantages and benefits of cloud computing. Just like it is flexible, it is scalable, it has an unlimited storage, it is easily backed, and it has a high performance level. So due to the COVID-19 pandemic, this generation is facing a lot of problems regarding sudden change into online platform, just like lack of affordability, accessibility, digital illiteracy, technical issues, etc. So by implementing cloud computing in educational field, that will definitely benefit them to improve their academic background, which means cloud computing can be effectively implemented in online education system as it provides uninterrupted services across internet. All the students connected to the server will receive same and quick updations. It is operated and we can provide input in the gadget and we will receive the output also in the gadget, but the processing, everything will be done in the server so that the long life of the battery of the gadget will be assured. So if all the children of a school is provided with even low cost gadget, all the students will receive equal and quality education regardless of the quality and cost of the phone or the gadget he or she uses, and regardless of the place from which they are connected. So a cloud-based education platform also improves physical and digital access to resources. Hence, the overall result can be seen in their academic performance. So there are numerous educational benefits with cloud computing, which are provided in the screen, just like cheap gadgets can also receive same and quality educational resources, and it offers load balancing, hence reliable. Overall, this implementation provides quality education for everyone without differentiation of economic and financial status. So a coin has basically two sides, and implementation of cloud computing also has some limitations and or disadvantages, which include high energy usage in the server and initial investment. But that's actually not a disadvantage because investment in education is the best investment and pays the best interest, as we all know. So even if we invest in our children's education, it will definitely benefit in the development of the society and hence therefore the country. And one more main disadvantage is the network issue. For that, we have come up with some solutions that the Indian government will be implementing a scheme called K-Phone in the country, through which all the houses will be accessed with internet. So many new schemes and startups like geofibers and other optical fibers startups are being implemented. And we are also coming up with our next project, which is a gadget that can receive and also boost internet signals through it. So the limitations have solutions so that this implementation of cloud computing can be one of the best or effective solution for much of the problems faced by this generation due to the sudden change into online education system. So in order to know the opinion of our students, we made a questionnaire consisting of these many questions and conducted a survey of 230 students of our school, in which 92.2
in this valedictory event of a 3-day long RCSC, that is Regional Children's Science Congress 2022. Every journey has its destination, so is ours. So here we are today celebrating our concerted efforts into the form of a valediction today at this hour. We have the pleasure to have among us as the chief guest of the event, Dr. Tarush Sharma, Director of National Institute of Animal Biotechnology, Hyderabad. We are so delighted to have you here, ma'am, today. We extend our heartfelt gratitude and thanks to you, ma'am. Thanks a lot, ma'am.
Thank you very
Next,
much.
I welcome our Honorable Deputy Commissioner, Ma'am G. Anasuya Ma'am Garu, Regional Office, NVS Hyderabad, who is presiding over the function. Warm welcome, ma'am. It's very encouraging to have you here, ma'am, among us today in this virtual yet lively mode. Next, I welcome KV Subba Reddy Sir, Assistant Commissioner, Regional Office, NVS Hyderabad, who is the in charge of this 3-day long RCSC 2022. Warm welcome, sir. I welcome and extend my thanks to all the officials of the NVS Regional Office Hyderabad. Next in line, I welcome our principal sir R. Daniel Ratnakumar, JNV Rangareddy, and all the other principals of NVS Hyderabad region, all the vice principals, teachers and students of various Vidyalayas who are watching this valediction on their screens. Without you, this program could never have been a success. Here I am taking the liberty to acquaint you all with the life and works of our Dr. Tarush Sharma ma'am. Madam is an Indian biologist known for her studies on germ cell marker genes. Sharma ma'am is an elated fellow of the National Academy of Agricultural Sciences and National Academy of Sciences, that is NASI. Her doctoral research was at the Indian Veterinary Research Institute IVRI, and after securing a PhD in 1990, she did her postdoctoral work as a research scientist at the Center for Biotechnology of the National Dairy Development Board. Sharma ma'am's core area of research have been in the field of molecular reproductive physiology, oocyte and embryo genomics, as well as the stem cell biology. Dr. Tarush Sharma ma'am is known to have done extended studies on early pregnancy detection in water buffaloes and has developed various techniques for oocyte recovery, somatic cell development, and immunohistochemical localizations of the proteins. The award list is a long one, and Dr. Ma'am Tarush Sharma ma'am received 2 Young Scientist honors early in her career, the Young Scientist Gold Medal of the Society of Animal Physiologists of India in 1993 and the Young Scientist Merit Certificate of the Indian Science Congress Association in 1994. Professor Niels Lagerlof Memorial Award in 2001, Award of Honor of IVRI in 2002, the Indian Society for Integrated Women and Child Development selected Madam for the Livelihood Award WEAL at the World Women Summit of 2003. Indian Council of Agricultural Research honored Madam with the Punjab Rao Deshmukh Women Agricultural Scientist Award in 2004. The Department of Biotechnology of the Government of India awarded her the National Bioscience Award for Career Development Science Award in 2006. The Best Teacher Award of IVRI again in 2006. The Society of Animal Physiologists of India honored Madam again in 2012 with the Dr. A. Roy Memorial Award. She was selected for the Research Excellence Award of the Indus Global Organization the very next year. In 2016, Madam received two awards, the Lebhesthwar Award of the Indian Society for the Study of Reproduction and Fertility and Bharat Ratna Dr. C. Subramaniam Award for Outstanding Teachers of the ICAR. Rafi Ahmad Kidwai Award for Outstanding Research by Indian Council of Agricultural Research in 2019, which is the highest research award of ICAR. Ma'am, elected as a Fellow of NASI and 2019, Executive Member of NAAS from 2021. And there is still more about Ma'am, for which I am out of words to elaborate. I request this assembly to Google Ma'am on Wikipedia. We are really enthralled and exhilarated, Ma'am, to have you here today as our chief guest of the program. Now, without much ado, I would like to hand over the meet to our principal, sir, Mr. R. Daniel Ratnakumar, sir, who is like determination and dedication personified himself to present the welcome address. Daniel Ratnakumar, sir, for welcome address.
Thank you, madam. Most honorable and esteemed Professor Dr. Taru Sharma, Director, National Institute of Animal Biotechnology, Hyderabad. Respected Madam G. Anushya, Deputy Commissioner, NVS Hyderabad Region. Respected officers of Regional Office, Hyderabad Region, learned principals, teachers, and all my dear participants of the Regional Science Congress 2022, a very pleasant good evening to all of you. On behalf of Navodaya Vidyalaya Samiti Hyderabad Region, our Vidyalaya, JNV Rangareddy, is privileged to host the Regional Children's Science Congress 2022 from the 21st of February to 23rd of February through virtual mode, in which 115 students selected from different JNVs of Telangana, Andhra Pradesh, Karnataka, Kerala and UTs witnessed the events and benefited during the Science Congress. These selected students got a rare opportunity to listen to the lectures of learned professors, eminent scientists, to undertake activities and interact with renowned personalities from the institutes of national importance during the last 3 days. I consider it as our privilege and honor to have amongst us Professor Taru Sharma, Director NIAB Hyderabad, as chief guest of this function. She has instantly accepted our request to grace the function, even though engaged with her busy schedule. We are very much humbled with your graceful presence, and I welcome you to this function on behalf of NVS Hyderabad region and on my own behalf. I also take privilege to welcome our Madam G. Anushya, Deputy Commissioner, NVS Hyderabad region. Madam has always been a boon to the Vidyalaya in the management of our day-to-day affairs, and the Vidyalaya has been benefited a lot in the sustained development in different directions under her guidance and able leadership. On behalf of NVS Hyderabad region and on my own behalf, I welcome you, Madam.
Thank you, sir.
Next, I would like to welcome all the officers of NVS Hyderabad region. Their dedicated support and timely guidance for the successful organization of the events of Regional Science Congress is highly acknowledged. And I also welcome all the resource persons of different sessions present here for the valedictory function. It is my great privilege to welcome all the learned principals, staffs, and students who are here in the virtual mode and without whose participation and cooperation the events would not have been materialized. I take this opportunity once again to welcome you all. Thank you.
Thank you so much, sir. Thank you so much for this earnest speech, sir. Now, to proceed our program, I would like to request our Honorable Assistant Commissioner, sir, Sir K.V. Subbareddy, sir, NVS Regional Office, Hyderabad, who has minutely detailed to us every episode of the event to be executed in a befitting manner. I request K.V. Subbareddy, sir, to present the report and the brief account of this 3-day-long RCSC meet 2022. K.V. Subbareddy, sir.
Good evening to everybody. With the due permission of Honorable Chief Guest of the occasion, Dr. G. Taru Sharma, Director, National Institute of Animal Biotechnology, Hyderabad, and Srimati G. Ansuya, Deputy Commissioner, NVSR, Hyderabad. I would like to present a brief report on Regional Children's Science Congress 2022. In the context of quality improvement in Navodaya Vidyalayas, based on the abilities and potential of the children for creativity, innovation, research, questioning, critical thinking, and analysis, there is a need to harness the rural talent by organizing Regional Children's Science Congress with exhaustive activities to inculcate scientific temperament and promotion of scientific talent among the students of JNVs. Regional Children's Science Congress 2022 was conducted, spanned for 3 days from 21st to 23rd February 2022. The inaugural session convened at 9 a.m. on 21st February 2022 was graced by Srimati G. Anusaya Madam, Deputy Commissioner, NVS Regional Office, Hyderabad, and Sri T. Gopal Krishna, Deputy Commissioner, National Leadership Institute, Hyderabad. The inaugural session commenced with the invocation to Lord Saraswati and Navodaya song by the students of the Vidyalaya. The welcome address was administered by Sri K.V. Subbareddy, Assistant Commissioner. The officials from the Regional Office of Hyderabad were among the other dignitaries. The Science Congress comprised 115 students identified from 77 JNVs from Hyderabad region. It was conducted in virtual mode owing to the COVID-19 pandemic. Eminent scientists were welcomed to share their expertise all the 3 days. On the day one, the first session was dealt by Dr. Vivek, Dr. Manjari Kiran, and Dr. Shashi Kiran from School of Life Sciences, University of Hyderabad. The session comprised interaction with the students on recent trends in biological research. The pre-lunch session consisted of Dr. Sarita Week's elaborate speech on cosmic wonders. She further explained on the evolution of sun and planets, their characteristics, and about existence of life in space. Her discourse concluded with an explanation on the advancement of astronomy and astrophysics in the recent times. Dr. Ashwin Dalal, head of the Diagnostics Division, Center for DNA Fingerprinting and Diagnostics, Hyderabad, continued the session from 2:30 p.m. He shared his expertise with the children on various topics. The story of ATGC, DNA errors, personalized medicine, COVID-19 virus testing, and the role played by Center for DNA Fingerprinting and Diagnostics, Hyderabad. The day concluded with a written quiz online developed by Sri P. Bhaskar Kumar, Principal, JNV Mehboob Nagar. The quiz consisted of 60 questions wherein 101 students participated. The toppers of the quiz contest are Param Patel, class 11th JNV Chikmagalur, Ayush Kumar, class 11th of JNV Bangalore Urban, Sujan NP, class 11th of JNV Hassan. The second day began with the session from Dr. Manoj Kumar, Assistant Professor, Advanced Center of Research in High Energy Materials, University of Hyderabad. The presentation was on the visit to labs, which followed an interaction with Dr. M. Sri Ramana, scientist DRDO. Many thought-provoking questions were put forth to the students. The scientists were asked to reason out on the indiscriminate use of plastic and to minimize its use by the recycling. The interactive session with Dr. Sri Ramana helped the students in understanding the role of DRDO with respect to armed forces. DRDO is also researching on developing indigenous missiles and psychological issues faced by the soldiers. The takeaway of the session was immense career options near DRDO for both MPC and BPC students. Dr. M. Hanumantarao, project scientist, Advanced Center for Research in High Energy Materials, University of Hyderabad, took forward the session by introducing and explaining the importance of position of elements in the periodic table. The session focused on the study of boron, its importance, and application in various areas. Dr. G. Manoj Kumar, Assistant Professor, Advanced Center for Research in High Energy Materials, University of Hyderabad, set the ball rolling. He emphasized on the importance of observation skills in learners. The hands-on session reiterated on the importance of involvement of students in learning. The concluding session of the day was dealt by Dr. Sayyid Nizamuddin Kaderi, Associate Professor, IIT Hyderabad. He explained the concept of kinematics through demonstrations. The activities were clearly explained by the scientist. Paper presentation by participating students concluded the day. Sri K. Parthiban, Principal JNV Hassan coordinated the activity. Among the 44 entries submitted, 13 papers were selected after scrutiny for paper presentation. The best presenters were Vishnu Priya, class 11th of JNV Karaikal, Danyanta Gowda, class 9th of JNV Hassan, and Isha Rashid, KKR, class 9th of JNV Idiki. On the day 3, the first session was dealt by Dr. Ranjith Ramadurai, Department of Material Science and Metallurgical Engineering, IIT Hyderabad, and he instilled the curiosity of the students towards STEM activities, elaborating on his topic of scientific curiosity, a way of life. The second session was handled by Professor V. Chandrasekshar, Center Director, Tata Institute of Fundamental Research, Hyderabad. His topic was a journey through light. He talked and interacted in length and motivated the students, explaining the life and contribution of Sir C.V. Raman towards science. Dr. Sutapa Ghosh, Senior Principal Scientist, CSIR, IICT Hyderabad, took forward the session by introducing and explaining nanomaterials and composites for energy and healthcare. The Regional Children's Science Congress was organized in a very effective manner by the host Vidyalaya, that is JNV Rangareddy, and the children are very much benefited. With this, I conclude the report with thanks to the chair. Thank you very much. Thank you very much.
Thank you so much, sir, for this occurrent and elaborative report, which comprised of all the details of this 3-day-long RCSC meet, sir. Thank you so much, Subba Reddy, sir. As we all know that the game of life has two participants, spectators and players. And we too had our wonderful students as both from various Vidyalayas. A program is almost null and dull if it doesn't have its reflections in its participants. So I would like to call our students present their reflections of the event. In this line, as first 4 of the 5 reflections, I'm calling Kumari M. Namrata, class 11th from JNV Rangareddy, to present her views. Namrata.
Respected dignitaries, my dear friends from various JNVs, a pleasant evening to one and all. This is Namrata of class 11 of JNV Rangareddy. Today, I feel it's my privilege to be one of the participants of this RCSC 21-22. It is a great opportunity for me to listen to the lectures and to interact with the eminent professors and renowned scientists of the institutes of the national importance. All the sessions are of great benefits to me, and particularly the session on cosmic wonders. The session clarified many of my questions which I have no answers for it. The experience of these 3 days helped me in gaining a lot of knowledge. The lectures given lit the curiosity in me and also developed my interest among various fields. I take this opportunity to thank each and everyone for giving me an opportunity to be a participant in this great event. If I have to say all this in one word about this opportunity and all, I will surely tell that I'm blessed. Thank you, one and all.
Thank you so much, Namrata. Now, I would like to call Master Allah Prasant, class 11 from JNV Krishna, Andhra Pradesh. Master Allah Prashant. Yes, you can present. Yes.
Ma'am,
Yes, you are audible. Yes, Prashant, you are audible.
good evening to all the dignitaries, organizers, and my friends from all JNVs. I am Ala Prashant of 11th class JNV Krishna, here to present my speech. I am very excited when I was informed that I was selected for Regional Children's Science Congress to be held at Hyderabad from 21st to 23rd February. The change to virtual mode was saddening, but I was happy I can attend the meeting along with my friends in our school itself. All the lectures were interesting and planned very well. The lecture which I enjoyed most was The Cosmic Wonders by Dr. Sarita Vig of IIST about the space, in which ma'am had explained about the space, solar system, sun, universe, stars, and all asteroids. Ma'am had also explained the star is important source of energy and it is the vital source of our survival on Earth. Ma'am had also explained about Milky Way universe organization and consist its consist of helium and hydrogen gases and the elements present in it, and it is a vacuum. Ma'am had also explained about the extraterrestrial life maybe exist on the universe, and there are similar planets like Earth are researched and found true till date. Now, I have enjoyed ma'am's lecture, in which I have enjoyed most was the doubts clarification by ma'am, and I have gained I have gained interest in astrophysics, and I like to say that the study of astrophysics is very interesting. And I also enjoyed the lecture given by Dr. G. Manoj Kumar on the hands-on activities, in which we have done activities like free fall, pendulum, electrostatic forces, and convex lenses, in which I have learned that practical knowledge is important and very simple scientific experiments can be done of the objects that are available around us. I have gained. I like to say that I like to conclude by saying great thanks to JNV Krishna and Navodaya Vidyalaya Samiti for giving me this opportunity. Thank you and good evening.
Thank you, Master Allah Prashant. And now next in line is Kumari Ananya, class 9th, JNV Kalburgi 2nd, Karnataka. Kumari Ananya.
Respected DC ma'am and DC sir and our chief guest, all the principals and all the teachers and my dear friends. Good evening to everybody. I am Ananya from class 9 from JNV Kalburgi 2. From past 3 days, I was very happy and delighted to be the part of Regional Child Science Congress, and all these days were very interesting, exciting and knowledgeable for me, and and a lot of things I learned from these sessions. On first day, I learned about genetic blueprint, genome, gen bank, organ transplant, and some concepts about cosmic wonders, which I never knew earlier. And the mechanism of gene sequencing was really very interesting for me. And on second day, I learned about the plastics as garbage and their categories, which was very admirable. And process of recycling of plastic, spectroscopy about DRDO and chemistry of boron, pyrotechniques and kinematics were very new for me. Even I could not pronounce these terms, and but I learned many things from these things, and I really enjoyed the hands-on activities in which I made a pendulum and also saw different effects of lenses, and I performed the electrostatic induction and did many other activities also. And on third day, which is today, I understood about the translational energy and rotational energy and EM wave, the electromagnetic spectrum and the Raman's effect. and his life story was very inspirable and very nice, which I feel. And I got to know the classifications of nanomaterials, which I never knew and were captivative. And at last, thank you to DC ma'am and DC sir for giving me this wonderful opportunity to learn more things, and this experience was very nice for me. And I also want to thank our principal G. Valyamai ma'am, who nominated me for this program. Thank you, one and all.
Thank you so much, Ananya, for sharing your first-hand experience with us. Now, I would like to call Master Alan George, class 11th, JNV Kannur, Kerala.
A warm and graceful evening to our most valued dignitaries. Myself, Alan George, class 11, JNV Kannur. It's my privilege to share my experience on behalf of my school. Before that, I would like to express me and my partner Edwin Johnson's gratitude towards NBS for providing us this opportunity. A special mention to our respected Principal Sri Pushkaran K for being the catalyst that stimulated us to do our best. It was a great opportunity for me to take part in NCSC 2022. The Science Congress was for 3 days. Each day there was 4 sessions. On the first day, the session mainly concentrated on the topics like cosmic wonders, genetic order, etc. Each session was demonstrated by expert research persons. The entire session was valuable because of its detailed examples and explanations. The second day was mainly on the topic of different aspects of garbage and its disposal. That session was enriched with experiments and innovative examples. The third day was about the topics like a live talk on Dr. C.V. Raman and Raman effect, scientific curiosity, the way of life, etc., which were taken in an interesting way. I extend sincere gratitude to Regional Office Hyderabad, host Chandrasekshar Rangareddy, and resource persons for their valuable time and experience spent with us, which would enlighten our vision and view on science. Thank you.
Thank you, Alan. Now, last to share the reflections is Master Madhusudan Reddy, Prakasham 1. He is a very ardent and eager student. So, persistently, he was requesting us to share his reflections. So, yes, Madhusudan.
Respected dignitaries and my dear friends, a glorious good evening to you all. Myself, L. Madhusudan Reddy of class 9, studying in Jawahar Navodaya Vidyalaya, Ongole, Prakasham 1. I was so glad to be a participant of RCSC 2021-2022. Now, it's a golden opportunity for me to share my experience. Really, I collected more and more information from this. One of my favorite session was Mr. Manoj sir's session. Through this session, I got the information that how one can develop his interest in physics. In fact, all the lecturers and professors from various institutions had shared their knowledge with us. It motivated me to be under the science stream. Yet last, I would like to express my gratitude to my biology sir, Mr. N. Tata sir, for selecting me, for nominating me to RCSC 2021. And at last, I would like to express my great gratitude to Mrs. Manju ma'am for her kindness and for her support. Thank you for giving me this wonderful opportunity.
Thank you, Madhusudan. It's wonderful to have students like you. Okay, now the time is allowing us to listen to the most erudite and enlightening words of our chief guest ma'am, chief guest of the event, Dr. Taru Sharma ma'am, whose encouraging and stimulating words will surely stay with us for forever. But before that, I would like to request our PGT chemistry sir, Srinivas Rao sir, and who is there in ma'am's chamber, I hope, to felicitate ma'am with a token of honor and respect and our love. Are you there?
Yes, some people have come from, yeah, I think they should be here.
Yes.
Thank you so much, Manjurani ma'am. I think people are there. I just switched from one meeting to another. Please call people from the school. Yeah, I think we have some people from the school. Yeah, sir, kindly come in. Come in. Oh, that's namaste. Please come. Please come. Kucho. You want them here?
Yes, ma'am. They have come down here to felicitate you with some token of love and respect,
Oh,
ma'am.
that's so nice of you. Thanks to you to make a part of this. Thank you very much, sir. Please have a seat. So, very good evening to one and all, and thank you so much, Madam Manju. It is, it is a time to hear about children. Yeah, we are all, our words and their words were more precious. So I thank the respected principal of the school, Mr. R. Daniel Ratnakumar of this Jawahar Navodaya Vidyalaya, Rangareddy district, Hyderabad. Well, sir, this is something very different, and my cheers knows no bound when I hear these young boys and girls. And I'm humbled that your people are here. Thank you so much for being here to both of you. Madam Anasuya, I think who started this program and must have motivated the children on that day. All the administrative officials of Hyderabad, different principals who have joined in a virtual mode as I gather. And of course, the report which was read by Mr. KV Subbareddy was in fact very enlightening. And first, I would really like to congratulate, compliment, and applaud the principal and the team of this Vidyalaya for having conducted this Regional Children's Science Congress in a very effective manner. I was highly impressed by the fragrance of the scientists you chose from the different academy and institutes in and around the Hyderabad. And that's the beauty of being at Hyderabad, the most vibrant academic hub of the country, if I say. Nonetheless, I don't say the others are not, but the vibrancy is there. And you people very aptly chose correct fragrance. So wherein you gave them the lesson from biology, the DNA unfolding, and the cosmic rays, and what our children have told. In fact, it's an eye opener to us when we go in deep sciences. In fact, these are the roots which are being nurtured by teachers, principals, and mentors like you. So, all the resource persons, I shall really address them, esteemed teachers of this Vidyalaya and others, staff and students. With my applause, compliments, congratulations, 3 cheers to you all. The team led by very esteemed principal of the Vidyalaya and Manju Madam conducting it. I really offer my salutes for having chosen these things and to motivate, to give the inspiration towards be it the cosmic sciences or the biological sciences to these young minds. In fact, when I was hearing these selected students, and of course, I would like to congratulate the 150 selected students. You're the gems who are outshining and are being here. There are people, everybody together, but yes, some people get chance, and so you are here. I was seeing the enthusiasm of Madhusudan, how thrilled and he was in the end when he told that what all he does. Also, I was very careful.
Thank you, ma'am. Thank you, ma'am.
Yeah, God bless you, beta. I was very carefully listening the young and bright and upcoming students who have really shown interest. Someone has shown that how they got benefited with one talk or the other. These young minds are the ones which are future of this country. As we all know, this is the year being celebrated throughout the country as Azadi Ka Amrit Mahotsav. And to add up to that, a week has started from yesterday, 22nd to 28th. The 28th being the National Science Day. And I'm really thankful to the principal who has allowed his children to be amongst us, wherein we would have the esteemed speakers on different aspects. So the week has been named as Vigyan Sarvatra Pujyate. It is not that Vigyan has come now, or maybe someone who has shared a story of Sir C.V. Raman and the Raman effect with the group of children as a resource person. The Vigyan was always Pujaniya around the country, and India was leading and is leading, and we have had leaders and are having leaders in various areas of Vigyan or science, we say. Zero. If you get a number 0, nobody likes, not the teachers, neither the parents. But you know, the number 0 came from which country? Your country, our country.
Yes, ma'am.
So
We are
that
proud
is
of
how
that.
Our country, Aryabhatta.
Yes.
Aryabhatta introduced zero to the world, ma'am.
Wonderful. So it's not a small thing. It's not a small thing. But you know, the point to ponder is that why are we amalgamating? Why are we really thinking more and more about Vigyan? Had this Vigyan not been persisting at this country, the pandemic era, which we all have gone through, I will not say we suffered. I have chosen a word we have gone through. Whatever happens, we have to take is at a time grows, because the present moment is inevitable. Believe in looking at the half glass full, children, always, always. And the pandemic time was very tough time. But see, due to that pandemic time, we all, right from Kannur to Andhra to Telangana, we are all here at this virtual platform. And we are able to connect and reconnect more. Well, I was talking about the Vigyan and the science. The vaccine, India is a vaccine leader, not only for the COVID, but also, you must have seen the data. One child amongst 6 across the globe has had a vaccine shot developed in this country. Would you not like to feel and draw pride in it? You come from the country which has given different vaccines. Covaxin, right from your city. Professor Krishna Ella, how it came? Had the Vigyan not been with us, if we did not know how to decode, how to sequence the complete virus, how we would have understood this? Mutants, different variants of Omicron, Delta, isn't it? So that's the power of Vigyan. And this Regional Science Congress, Children's Science Congress, which has been arranged. What a correct time to choose, sir. What a correct time. 21st to 23rd of February 2022. You started Children's Science Congress on 21st. The country started the whole week for Vigyan Sarvatra Pujyate. It's not merely a coincidence. It's the power of science. Having said more about science, I will take another 2 to 3 minutes. Am I permitted, sir? 3 minutes more can I take?
Sure, ma'am. Sure, ma'am.
Thank you very much. So, what I would like to say to this young, bright mind, it's a parched land which has been. Kudos to the teachers who are building this nation through you all. Teachers are the ones who are allowing the seed, and they are the ones who are nurturing the young plants, and then the tree comes. So these young minds, science and biology, because I am a biologist, and the biology You need people, you need students in all the areas. But the pandemic time has also made it very clear you need more and more biologists. Of course, you need scientists in other areas also, because it's not only the vaccine, it is also the vaccine container. It is also the requirement of the oxygen. It is also the requirement of correct type of the incubation facility. So in all areas. What all the students gave feedback, it left me very impressed. And the credit, I shall give it to the organizing, teaching faculty and the team. Please accept my humble congratulations for igniting and bringing in the right resource persons. And really my joy knows no bound to be at this platform, because we sit with scientists, we talk deep science, but this is something very different. Thank you so much for having me here. In fact, this is privilege is all mine, and I look forward for having more and more interactive sessions, sir and madam. Kindly feel free to the people who are here. I also say in person, feel free to shake hand mode, and National Institute of Annual Biotechnology remains open. We also do the societal activities. We have developed a science museum for children at Yadgir district, wherein we have taken one village to our fold, and we are doing all the activities. But this Vidyalaya remains not only very close to our vicinity, but very close to our heart. With that, I thank you, and I wish each one of you a very bright path ahead. May you all stay happy, blessed, cheered, healthy, and safe. May God bless you all. May God bless us all. Thank you very much, Principal Sir. Thank you. I
Thank you
think
so
here.
much. Yes, ma'am. Yes, ma'am. Srinivas sir, are you there?
Madam, I'm here.
Please come this side.
Yes, please come near the screen.
I'll remove the chair.
Yes.
I think let's have the team join me. Oh, wow, this is beautiful. It's beautiful, beautiful. Thank you so much. Thanks a lot. Thanks a lot.
Pleasure, ma'am. Thank you so much, ma'am.
I'm humbled. Thank you so much for coming.
Thank you so much, ma'am, for your encouraging and inspiring words. And our students will definitely try to excel in science and whichever field they'll choose tomorrow. And they'll surely shine. And it's definitely our privilege, ma'am, to have you among us, to inspire us, to encourage us, ma'am. Thank you so much, ma'am. Thank you so very much. Thank you. Now, in this line, to listen to we are to listen to our patron, our sanguine guide, our beacon of inspiration, and our very own, our Deputy Commissioner, ma'am, G. Anusuya Garu, ma'am, NVS RO Hyderabad, to present the presidential address, ma'am. Respected G. Anusuya, ma'am.
Yeah. Thank you, Madam Manjurani. Good evening to one and all. Dear colleagues, Assistant Commissioners, Mr. Daniel Ratnakamal, the Principal of the host Vidyalaya, the principals who have joined in this virtual mode, the participating students, and all other students who are there in this online program, guest lectures, and last but not least, our chief guest of the evening function, Madam Taru Sharma. Really, it gives me immense pleasure to be here on this valedictory function of the 3-day-long Regional Children's Science Congress hosted by JNV Rangareddy on behalf of Regional Office Hyderabad from 21st February to today, that is 23rd February. Children, as I said, you are all fortunate that you are in Navodaya, and more fortunate that you have been selected for this Regional Children's Science Congress. In spite of this pandemic, since we could not do it last year, we thought to benefit the students, at least we should do it online. And we tried our level best to bring every feature of this Science Congress if it had been conducted offline. I think to the maximum extent, it has been achieved. Since the students had the experience of attending the online classes, it was very handy for them to join and to participate and to be a part of the program throughout the day. I was really impressed because if this program had been offline, probably I would have joined only for the inaugural and a few sessions and then for the valedictory. Because this offline program, along with my work, in and out, I was connected with this program and I was part of it. And I was also listening to the great lectures given by our guest lectures, and the questions that were put in by our students to them is really very, very, I was very happy. One of the guest lecturer was saying, a mother will never ask the scientist when he comes home, what did you learn? He will ask what question that you had put forth in your class. That I really got impressed, and I saw that in your questioning nature. We can identify the scientists by their inquisitiveness and their rapt attention and their questioning nature. That I could see in most of them. And you know the quote of Confucius, I hear, I forget, I see, I remember, I do, and I understand. I have seen this in schools, but even in virtual mode, it was really impressive to see the guest lecturer was taking this hands-on experience session and the students participating actively and doing the experiment and coming out with results and the paper flying and attaching to the plastic pipe, and children getting it so quickly, all the materials, whatever was essential for that hands-on experience. It was really enthralling. And children, the 4 samples, students, when you had given your reflections, I was really happy that the purpose of hosting this Science Congress online was completely served. And I should congratulate the team of JNV Rangareddy under the leadership of the principal, Mr. Daniel Ratnakumar, for having taken up the job very meticulously, have planned it, and without any hitches, the program for the 3 days had been conducted very, very effectively. And by sending responsible teachers and staff to the places where the guest lectures are there, made us to feel that the program was not online, it is offline as usual. Madam Tarun Sharma, it is customary for us. Every year we conducted 3 days, bringing the students all across the JNVs of South, and they stay here, and the stay will be mostly in the institutes, and they'll be visiting the laboratories, listening to the lectures, and we, as a reciprocation, present the paintings done by the staff and students of our own JNVs as a memento, which will be with our guest lectures forever in their life and remembering us forever. And it was rightly followed, even in the offline mode, by the principal and the JNV team. And thanks to them and students, this 3 days program was arranged only to motivate and make you to get inclination towards science more and more. So taking cue from the lectures and strengthening the motivation, whatever that you have received in these 3 days, you should complete your school education, and when you pass out, you should choose the STEM areas wherein you become a scientist for our nation. We have produced many engineers, doctors, IAS, whatnot, everything. We do have scientists, very few in number, but they have not been come to the spotlight. So I wish and expect all of these Children's Science Congress participant students, or at least handful of you, should become scientists and should serve the nation in a better manner for what you have received from Navodaya Vidyalaya Samiti. And I'm happy that it's not only the 150 students from the JNVs, more in number, participated in the program, and I believe that they also would have benefited a lot from this 3 days program. So my best wishes to all the students to continue in the field of science and to become a scientist who can do a great service to our nation. And my congratulations to the JNV team and my assistant commissioners who had been constant support for arranging this program. And this program actually became very meaningful and a successful event only because of the rightly identified guest lectures and their interest, the amount of preparation that had gone in their presentation, and their simple and humble nature to answer to each and every question of the student which is being posed by them in between of their lectures. I was really impressed by the simplicity of the great personalities. And I wish every one of the student for their bright future, and I thank all the guest lecturers and Madam Taru Sharma, who is here with us for the valedictory function. And thank you one and all. Over to JNV Rangareddy.
Thank you so much, ma'am, for your guiding words. We always feel so energized under your guidance, ma'am. Now, as we all know that no duty is more urgent than that of returning thanks. And for that, I would like to hand over the mic to Mr. K. Mattareddy, sir, our PGT History, JNV Rangareddy, to propose the vote of thanks.
Thank you very much. And warm good evening to all the dignitaries and dearmost children. I am privileged to present the vote of thanks at the end of this mega virtual event. And there is a saying, the water the root, taste the fruit. And you are the plants which are being watered by Navodaya Vidyalaya Samiti, and in future the country is going to taste the fruit of your human resources. So that is why, first of all, I would like to thank all the 115 students from 77 JNVs who participated and made this program a live and grand success. And I also, on behalf of Navodaya Vidyalaya Samiti, Hyderabad region, and on behalf of Java Navodaya Vidyalaya Rangareddy, I extend my wholehearted thanks to Srimati Taru Sharma ji, Director, National Institute of Animal Biotechnology, Hyderabad, for gracing the valedictory ceremony of this Regional Children's Science Congress 2022. I especially thank our Honorable Deputy Commissioner Ma'am, Srimati Anasuya Garu, for giving the opportunity to conduct this meet by JNV Rangareddy and also gracing the inaugural ceremony as well as the valedictory ceremony. Thank you, ma'am. And I also special thanks to Gopal Krishna sir, Deputy Commissioner, Navodaya Leadership Institution, Rangareddy, for his gracing the occasion on the inaugural day and continuous guidance. I also thank our Assistant Commissioners of Navodaya Vidyalaya Samiti Regional Office, Hyderabad, Sri Radhakrishna sir, Anuradha madam, and Benny Joseph sir for their continuous guidance. And I special thanks to Sri K.V. Subbareddy sir, under whose direct supervision this meet has been conducted. And I also thank him for his welcome address and present a overall report at the time of valedictory ceremony. Now the time for all speakers of these 3 days. There were 10 sessions conducted, and eminent speakers from the important institutions of the country, they have presented their messages and they inspired the students with their thought-provoking lectures. And I also, at this juncture, I also thank the heads of the institutions of national importance. University of Hyderabad, the Institute of Tata Institute of Fundamental Research, and Indian Institute of Chemical Technology, and IIT Hyderabad, and National Institute of Animal Biotechnology, Center for DNA, Fingerprinting and Diagnostics, Indian Institute of Space Technology, for sparing their eminent resources to make this Congress a grand success. And next, I especially thanks to Sri Bhaskar Kumar sir, Principal JNV Mahavanagar, and Sri K. Parthiban, Principal JNV Hassan, for their participation and active involvement in the meet. I also thank all the 77 JNV principals of Hyderabad region for making the arrangements for the children to participate in the virtual conference and encourage the children to participate in this mega virtual event. And I also special thanks to our leader, Daniel Ratnakumar sir, Principal JNV Rangareddy, who has taken much pain to organize this mega virtual event, a grand success. And last but not least, I thank the team of Rangareddy JNV for their tireless effort from morning till the night to make this every inch of this program a grand success. At this time I thank Bhop Singh sir, Mansurani ma'am, Srinivas Rao sir, Ramakrishna sir, Suresh Kumar sir, Aruna ma'am, Nirosha madam for their tireless efforts from minute program a grand success. Thank you, one and all. Thank you very much.
Thank you so much, Matareddy sir. Now to wind up the program, I would like to request every student to stand up at their places for Vande Mataram. It's evening now, sir. Vande Mataram, Vande Mataram, Sujalam, Supalam, Malayaj Sheetalam, Shasya Shamalam, Mataram, Vande Mataram, Shudra Jyotsna Pulakitayamini, Pulyam Sumita Drumadal Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram. Vande Mataram. Now, with the permission of our chief guest, ma'am, and president, ma'am, I would like to end this program, ma'am.
Okay, thank you so much. All the best. Yeah, bye bye from NIAB.
Thank you, ma'am. Thank you, ma'am.
Thank you so much, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Nambur Yavro.
Excuse me, ma'am.
Yes, yes.
Ma'am, when do we get our certificates, ma'am?
Certificates will be posted to you guys. Don't worry.
Nambur boy.
Yes, yes. Timely, they will be posted to your school mail IDs. Don't worry about that, okay? You participated, no?
Yes, ma'am.
Okay, ma'am.
Okay.
Okay, wish
Good
you all
night,
the best,
everyone.
all of you.
Thank you, ma'am.
Thank you, JNV Rangareddy.
Thank you, ma'am. Thank you, madam.
Thank you.
Thank you.
Thank you.
Nambur Yavro.
Thank you, ma'am.
Thank you,
Thank
ma'am.
you, ma'am. Thank you all.
Thank you, ma'am.
Thank you, ma'am. Ma'am.
Nambur. Where are you from?
Ma'am, are there
Okay.
any special
Principal sir,
certificates
can
provided?
we end the meet, sir?